The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone. Good morning, good afternoon. Welcome to PYRO Asia 2020. This is a second international symposium on analytical and applied pyrolysis. This is, as you know, this is a 3-day event and a purely virtual event today. I welcome you all for this 3-day event. Let me congratulate and thankful share my thanks to all the technical advisory committee who put together this event. Without them, this whole event is not possible. Okay, and I appreciate all, we have experts from the different parts of the world: Japan, Korea, China, and India, and also Singapore and Malaysia as well. Thank you all being supporting this event. And also, of course, our sponsors. Okay, the first gold sponsor, Frontier Lab, as you may know, is a small giant in analytical pyrolysis technology, which offers innovative pyrolysis system and also related accessory to advanced research in analytical and applied pyrolysis research and development. We're thankful to the Frontier Lab to take the lead in sponsoring this event. And of course, we have another gold sponsor, CDS Analytical from USA. It is also a leading global provider of innovative pyrolyzer, thermal desorber, and purge and trap concentrator for GC-MS in the analytical lab. So thank you CDS for supporting this event. And of course, Geol from Japan. It offers the innovative solutions for your material testing and applications, and also they are very good on the spectrometer systems. And thank you for supporting this event. And of course, SG Singapore Lab Forum, they put together inviting lots of people and appreciate sponsoring this event. And as an event manager, Technobase, I represent Technobase, and thank you for inviting us to be part of this event. And we are specialized, as recognized as International Resource Center for Polymer Industries and Process Technologies. We are based in Thailand, and we have a variety of webinars focusing on the technology, know-how, and research. Okay. This is me. I'm your event moderator. You will hear me these 3 days. Okay, I'm not opening my webcam. Okay, but you can hear my voice clearly. And my name is Peram Prashadara. I'm very much thankful to the organizing team to invite me to part of this event. I'm sure if you find all of you, this event is very useful to you. I work as a CEO for the Technobase. I have a 23 years experience in the polymers, energy, and environment. I'm a chemical engineering graduate, and also I have a master's degree in environmental engineering. Let's quickly give you the agenda. I have a different, we have people from different parts of the world, and but I make it as easy as possible. We are starting our time with Singapore. We start 1 o'clock and we finish around 8 p.m. today. Okay, and every day is going to schedule like that. And for agenda India time, of course, probably everybody knows it's at 10:30 now. It finishes at 5:30. And if it is Korean time, it's at 2 o'clock and finish at 9 o'clock. But that's the follow the timelines. But we start Singapore as the reference time, so that easy to follow. Yeah. I want to say that we have plenty of and excellent speakers. I'm happy to show plenary speakers. Professor Hajime Hotani from the Nagoya Institute of Technology, Professor Jaifeng Zheng from the Xiamen University from China, Professor Yong-Sik Okay is from the Korea University. We have excellent speakers, excellent talks. I'm sure you find it very useful. Of course, we have keynote speakers, Professor Kim and Professor Haiping Yang and Professor Lam from Korea. We have more keynote speakers, and also Professor Zun Ming Yu and Professor Bhaskar and Dr. Masek from the UK. She nice, good talks. I'm sure you find it useful. And also Dr. Arun Kumar, Professor Farid, Professor K. Mohanty, we're all invited speakers. More invited, Dr. Watanabe, Professor Guzin Hu, and Professor Abhishek Sharma from India. Okay, so these are, I'm just quickly give you the information about what kind of speakers are lined up for us in these 3 days. And please do join all the sessions. I know it's fully packed, but I'm sure you find it very useful to you all. Yeah. And not only this, we have there are 20, almost like 30 oral presentations along with all the invited keynote speeches. Okay, this is the agenda for today. and we have 3 sessions today. And after opening remarks, the first session starts on focusing on analytical pyrolysis, recent trends and advancements. The second session is focused on applied pyrolysis and biomass, and third is on analytical pyrolysis and also oral presentations. Tomorrow on Saturday, on focusing on the biofuels, biochar, biocarbon, and also we have oral presentations. And Sunday we have on the biochar and advanced materials, and we also have an excellent session with the editor from the elsewhere, and also for the people who would like to contribute papers for journals. And finally, we have panel discussions on the last session. So guys, it's fully packed. I'm sure you find really useful to you all. Just a few tips for you to follow. The people who registered as a delegate or viewing this event as a delegates, you can post your questions in the question box. And there is a question box on your control panel. Okay, and if you are addressing the question to a certain speaker, please put the speaker name in the beginning, and so the concerned speaker will be addressed that question. I will put these questions in the PowerPoint and discuss in the Q&A session. But during the panel discussion, all the panels members are required to open their webcams to have the panel discussion. Okay, and in the Q&A session speakers can ask questions directly to other speakers without typing in the question box. But for a plenary lecture, we have 5 minutes Q&A session, so you can ask questions immediately. Okay? And for the clear audio and time management and preventing external noises, I request all the speakers to keep the speaker on mute when they are not speaking and presenting. If any delegate is unable to hear properly, please check your audio settings, internet settings. You may select computer audio in the audio selection. If still doesn't work, please log off and log in again. Please check your internet stability and speed if you're experiencing problems with accessing the event. All speakers are requested to open their PowerPoint file ready and get it ready to share to the audience. I will send a request to share your screen after introduction of each speaker. Okay. I'll request all the speakers with reference to each session, please log in 15 minutes before the scheduled session, and during the break time, we will do any quick check on the connections. After completion of your session, please log off from the session as a panelist and log in again as a delegate. Okay. You must have received already, all the speakers must have received both the panelist link as well as the delegate link. Okay. And as you see, there are participants from the different parts of the world, and I request all the speakers and presenters to speak clearly, so the benefit of everyone. Okay. And of course, I request you all to manage the time as per the slots given. If you want to get the links for the for the delegate link, you can quickly go to the website at researchandinnovations-webinars.com, and you can apply for the webinar link, and as the link for the event, and you can get an email immediately. Okay, if you need any assistance, okay, you can email to me, or you can WhatsApp me, or you can send a message to me. But during the session when I'm speaking, I may not answer it, but once the program is running, I'm able to help you. Okay, these are quick. Look at your control panel. There are a few things you need to understand. If you're a speaker, you may see the panel is blocking your screen. So quickly click on this this arrow. It will hide the screen, hide the control panel. Okay, so it doesn't block your PowerPoint. Okay. For easy to mute, unmute, you see the speaker here. You can, if you mute it, it turns into red. If you unmute it, it turns into green. Okay, this is a quick tip for it. Okay, now I invite Professor Shogo Kumagai-san to give opening remarks. Let me brief you about Professor Shogo-san. His career history since 2018. He is an editor of the Journal of Analytical and Applied Pyrolysis. Since 2015, he is an assistant professor of Graduate School of Environmental Studies and Toho University. And 2012 to 2015, he's working in the Japan Society for the Promotion of Science Research Fellow. His research work is involved with the development of pyrolysis process for recovering valuable feedstock from plastic, biomass, fossil, and their mixtures and development of chemical and mechanical recycling process for the waste plastics. And he contributed so many publications and reviews, book chapters. He also have 2 patents, and he received 21 awards. So let's invite Professor Shogo-san to make a welcome remarks.
Okay, thank you very much, Pelam. So can you hear me?
Yes.
Okay, thank you. Thank you very much. So hello, everyone. I'm Shogo Kumagai from Tohoku University, Japan. So welcome to PYRO Asia 2020. And thank you for all for joining this symposium. So I'm honored to kick off this PYRO Asia 2020 today. And I very much appreciate all technical committee members from India, China, Korea, Malaysia, Singapore, and Japan to hold this event. Also, I'd like to express my great thanks to all sponsors. And don't forget, I'd like to express my appreciation to Katik, who takes the lead in arranging everything for this symposium. So the first symposium of PYRO Asia was held at the Indian Institute of Technology Madras, Chennai, India, and Professor Bin organized it. So it was a successful conference with about 100 participants from 5 different countries, including renowned industries. So it also provided us an excellent opportunity to interact with senior, middle, and junior researchers. So this year, due to the COVID-19 unprecedented situation, so this year must hold an entirely virtual event. However, we have invited distinguished researchers for the plenary, keynote, and invited lectures, and many short oral presentations from academics and industries. So also we have panel discussion events on analytical and applied pyrolysis, and a lecture about how to successfully publish in a scientific journal from Elsevier. So I'm sure that you all could enjoy this symposium, and I hope your active participation. So thank you very much. So now I'd like to open the first session, the analytical pyrolysis, recent trends and advancements. So can I start the first session, Pelam? Okay, thank you. So this session has 5 presentations. The first plenary lecture is about analytical pyrolysis for environmental microplastics analysis, challenges and solutions, from Professor Otani from Nagoya Institute of Technology, Japan. And the second keynote lecture is from Professor Kim from Daegu University, Korea. The next invited lecture from Dr. Kumar from SABIC Technology Center, and 2 short oral presentations from Dr. Nimura from JO and Dr. Tantri from SABIC Technology Center. So the first presentation is from Professor Otani. So let me briefly introduce Professor Otani's career. So Professor Otani, many of you know that he is a top researcher in the analytical pyrolysis field, and he was a chair of the International Symposium on Pyrolysis 2018 held at Kyoto. And they have many publications. He published more than 220 original papers and about 150 reviews and book chapters, and mostly on pyrolysis work of polymers. So he has also served on the advisory board of Journal of Analytical and Applied Pyrolysis, Elsevier. Okay, so Professor Otani, so please go ahead with your presentation.
Okay, let me ask you to share your screen, sir. Here I go.
Okay.
Yeah.
No. Okay. Thank you very much, Dr. Kumagai, for your kind introduction. And I would like to say thanks to the technical committee to give me a chance to talk as a first speaker of this PYRO Asia Symposium. So today, I would like to talk about the analytical pyrolysis for environmental microplastic analysis. So this picture is very famous and sensational, in which a plastic straw sticks into the nose of the turtle. And this picture also shows there are many plastic waste distributed on the seashore. So this plastic pollution problem is very severe. But more important problem is so-called microplastic problem. In this case, large plastic waste are mechanically fragmented into small pieces by sunlight or the sea waves, and then go into the microplastics smaller than 5 minutes, but it's still organic plastics. So it can absorb various persistent organic pollutant. So it can be ingested into some fishes or animals, and then in some cases it go into the humans. But the detailed situation or dynamics of these microplastics is still unclear. So to clarify the dynamics of microplastics, it is very important to analyze them precisely. This is the ordinary analytical procedure for microplastics. In this case, microplastics are collected by filtering the surface water on the sea, and then picked up the small pieces, and then it is analyzed by using typically micro FTIR or micro Raman spectroscopy. But when analyzing the microplastics by these techniques, the observed floating amounts of microplastics on the marine water surface is much less than that estimated from the eluting amount, especially for the smaller pieces like this. So this problem is called missing thing problem. And probably the origin of this missing things coming from the analytical method. So problem reason for missing things. One is because of the too much fragmentation, the microplastics is too small to detect by the ordinary analytical method. Or in some cases, some microplastics are sinking into bottom sediment and disappeared on the surface. And also ingested by some species or even by the smaller organisms, such as plankton. To clarify these missing thing problem, the ordinary techniques using FTIR or Raman is not suitable, because these in these techniques, much smaller species cannot be analyzed, and in this case, even for the smaller pieces, it must be isolated like this. So to solve these problems, analytical pyrolysis techniques is very useful because of its high sensitivity and its high selectivity. So in the case of pyrolysis CMS, smaller microplastic species, smaller than 1 micron, even smaller than 1 micrometer, it can be identified and in some cases quantified. And even in the mixture, we can select the some information for the each plastic species. So already in 201, about 20 years ago, this paper was published. This shows the usefulness of the pyrolysis CMS to analyze the environment pollution by synthetic polymers. And then nowadays, many publications are observed for the analysis of the microplastics by using pyrolysis method. And this year, this special issue on pyrolysis method for the analysis of environmental plastic contamination is published in a Journal of Analytical and Applied Pyrolysis as a virtual special issue. For example, to solve the problem from the sinking into bottom sediment, this paper has already published by Italian group in Pisa University. So in this case, sand sample is collected from the various part of the seashore. And then at first from the sand, the plastic species are extracted. And then the extracted species are analyzed by pyrolysis CMS. So you can see the results like this. So in this case, even for the very small pieces can be detected. And even in the mixed plastic samples, you can see the pyrogram like this. But you can see these pyrograms are very complicated because of it's coming from the mixed samples. So analytical pyrolysis techniques can be used for the smaller microplastic species. But in the case of smaller microplastic species, we cannot isolate each particle. So we need to analyze the complex mixture plastic samples. So this is not an easy task. So to get the reliable information from this complex mixture, there are some specialized techniques is often necessary. So we try to solve to this problem. We use a specialized GCMS technique. It is the atmospheric pressure chemical ionization and quadrupole time of flight mass spec system, and combined with the pyrolysis devices. So it's called PYAPDCMS system. So in this system, at first, the ionization technique is very special. In this case, using the APCI method. This method is ordinarily used for the ionization technique for the liquid chromatography combined with MS systems. But in this case, these techniques are used for the DCMS system. So in this ionization, this is basically the soft ionization technique by using the corona discharge with nitrogen plasma. So mainly during this ionization process, molecular or molecular related ions are formed. And in addition to these molecular ions, some specific fragment ions can be often observed. And then these specific ions are then analyzed by this time-of-flight analyzer. This is a very high mass resolution MS technique. So by using both functions, we can try the reliable identification of the microplastic species in the mixed samples. So here you can see the typical pyrogram of the, in this case, standard polypropylene samples by using the PYAPGC technique. This is a total ion chromatogram pyrograms, and you can see some specific pyrolysis products from the polypropylene like this. And these are the typical mass spectrums by using this APCI technique for peak 1 and 2. This product is this one and this one formed from the polypropylene. In this case, you can see the molecular or molecular related ions like this. And it is very interesting to note this specific fragment ion, 156.1390, is commonly observed like this. This is coming from the fragmentation process like this. And this specific fragment ion can be observed in the all of the mass spectrum for the pyrolysate from polypropylene. So by focusing on this specific ion, we can obtain the specific information for the polypropylene, even in the mixed plastic case. So we prepared the mixed plastic model samples like this using polyethylene, polypropylene, polyvinyl chloride, polystyrene, and polyethylene terephthalate. And this is the 5 major plastics and mixed in this ratio. This is corresponding to the production ratio in Japan. And then cryomid in fine mixed powder. So then we analyze this mixed plastics by using this technique. So you can see the extracted ion chromatograms at M-body 156.139 and plus minus 0.020 very narrow windows for polypropylene standard samples, and this one is for the mixed plastic samples case. So you can see, as shown here, the very similar pyrograms both two samples. Even for the mixed samples, this means the observed peaks are coming from the polypropylene species in the mixed samples. So you can we can extract the information for polypropylene even for the mixed practice samples. In the similar manner, the other plastic species can be specifically evaluated by using the specific observation of the typical ions for each plastic species. So then we try to analyze the real environment microplastic samples by using this technique. So this sample is collected at the, this position. This is a Pacific Ocean near the northeast area of Japan, and collected by the Houston net, and then picked up the microplastic species. In this case, 200 species are collected here. And then we mix these species and cryo-milled into the fine homogeneous mixture, and then analyzed by PYAPTC-MS technique. And here is the observed result. And the specific ion, selected ion chromatograms are compared for the microplastic sample and each standard plastic sample. So in this case, as for polypropylene, polyethylene, and polyvinyl chloride case, you can see almost the same paragonals observed for microplastics with corresponding standard plastic samples. So this result shows that at least these three species are involved in this microplastic samples. But as for the polyethylene terephthalate and polystyrene, we cannot see the specific extract ion chromatogram. So PET and polystyrene cannot be included in this microplastic samples. So this technique is already published in Journal of Analytical and Applied Pyrolysis. But this technique needs a very specialized equipment, so-called APCI and time of flight mass spec. This is a very high performance method. So this is not for the ordinary technique by using many researchers. So we also try to get another approach to analyze mixed plastics. In this case, by using ordinary quadrupole standard mass spec, but specialized data analysis technique by using a specialized identification algorithms. So this result is also published here. This is the collaboration work with Frontier Laboratory, and this detail for this result will be talked by Dr. Watanabe after that. And then I would like to talk to shortly the challenge to analyze the ingested microplastics by organisms, mainly for the plankton. So this picture shows the microplastics ingested in some sea plankton. This is copepoda. But in this case, this microplastic is not the standard microplastic, but it is a very specialized one because it is marked with a fluorescent compound. So you can see the fluorescence like this. So you can see here. But in the case of normal microplastics, we cannot see the microplastics in the planktons like this. And it is also very difficult to isolate microplastics from the planktons because this is very small. So we need to analyze microplastics with plankton. Very long ago, we tried to analyze plankton, in this case, Daphnia, a single species, single body of the plankton can be analyzed by the PYDCM method. In this paper, we did not focus on the microplastics, but in this case, focus on the lipid in the this plankton. But we can see the information in the one individual species in the one individual plankton. So we try to this technique to analyze the microplastics ingested in individual plankton. So we try to the model experiment like this. This is a collaboration work with Professor Tanaka in Tokyo University of Marine Science and Technology. In this case, we use also Daphnia. It is not the marine plankton, it is a plankton in the fresh sea. But this is a very typical model plankton, often used for the environment effect analysis. So in this case, individual plankton species are put in the cells of the microplate, 5 milliliter volume, one by one, and then cultivated in different conditions. In the case of series 1, it's a control, only cultivated in the tapped water. In the second series, cultivated with polystyrene microsphere. This is a model for the microplastics, 10 micrometer diameter. And third one is a polystyrene with chlorine odor, fragrance of chlorella. Chlorella is a typical feed for the Daphnia. So fourth one is the polystyrene with the real feed chlorella case. After that, we analyze each plankton by using PYDCMS. So you can see the typical patterns for the plankton individuals after cultivation, control, and only microplastics, and with odor and with feed. So this is the peak for the internal standard. So this peak intensity is practically the same. So you can compare with this peak intensity to the peak intensity for the that from the polystyrene. This is the polystyrene monomer and trimer. So in this case, this 2 and 3 case, this styrene related peaks is very larger compared to the internal standard. But in this case, this one is still smaller. And in the control case, trimer cannot be observed. But monomer is smaller, even for small peaks, you can see like this. This is probably coming from the plankton itself. So we determine the plastic species from the intensity of these primer peaks. And then determined like that. In the case of microplastic without feed, many plastics are ingested by the plankton, about 10,000 particles. But in the case of the cultivated with microplastic with real feed, in this case, plankton favors the feed species. So ingestion of the microplastic is very small amounts like this. So it is very interesting result. So the observed result I talked today is at the first step for the environmental microplastic analysis. So as for the future work, we try to analyze further work to solve what is the truth of environment microplastics. So in this case, we plan to analyze real plankton samples in the seawater and detailed analysis for the microplastics in terms of size and depth. And in some cases, we try to the long-term variation of the microplastic dynamics with the help of the collaboration with Tokyo University of the Marine Science and Technology. So I hope I would like to, I hope I can show you the further result in the near future. Thank you for your kind attention.
Thank you, Professor Jimmy.
Yeah.
Okay, Professor Shoga-san, you'd like to,
Okay, thank you very much for your very interesting presentation. So, do you have any questions from audience?
Still not received yet. Okay, yeah.
We have one question. So, from Kartik. So, how was the plankton sample analyzed? Dried one or wet one?
In this case, we picked up the wet planktons and then dried, but lightly dried, not so severely dried.
Okay, thank you. So, any other questions from audience? Okay, so I have, so do I have time for Q&A?
Yeah, yes, please. Okay, we have two questions. Let me put the questions onto the screen.
Okay.
Okay, let me put the questions. Yeah, just a second. It takes a few seconds so that everybody can see the question. Oops. Okay, let's try this one first. Okay, yeah.
Okay. Oh. First question is very difficult to answer. So I cannot answer the first question. And the second question for the detection limit. So it depends on the plastic species. In the case of polystyrene case, in our experiments, even for the 1 microsphere for 10 micrometer diameter, we can detect the microplastic species. But it depends on the plastics and depends on the DCMS apparatus. Mm-hmm. The third question is also very difficult. So this is still, I think this is not clear yet. So we need to analyze microplastic in the real marine world. So I think.
Okay. I see now no further question here. Would like to add anything, Professor Shogo-san?
Okay, so all questions? Okay.
Yeah.
So how about the time?
Okay, we are on time. Yeah, so thank you.
Okay.
Yeah.
Thank you very much, Professor Otani.
Thank you very much.
Thank you very much. So let's move on to the next speak. Yeah. Yep. Okay, so the next talk is from Professor Kim. The title is The Effective Use of Tandem Microreactor on the Catalytic Conversion of Waste to Energy. So let me briefly introduce, Professor Kim. So Professor Kim, so yes, he has many publications in SCI journals, such as Applied Energy, Chemical Engineering Journal, etc., and also Journal of Analytical and Applied Pyrolysis. So now he is focusing on the research related with catalytic conversion of waste, biomass, and plastics, and the quantification method development of microplastics. Okay, so Professor Kim, so please go ahead your presentation.
Okay, let me share the screen. Yeah, just a second. Okay. Yes. Can you please share your screen? Okay.
So can everyone see my screen?
Yes.
I cannot see.
Yes.
Okay. Oh. Okay, thank you so much for to giving a chance for the presentation on this great conference. So mainly my application area is related with the applied pyrolysis. However, in my cases, I used my analytical pyrolysis technology for the study of the conversion of waste to energy. So today I would like to explain about one of innovative system. Its name is Tandem Microreactor. It was developed by Frontier Lab Japan, and I will explain some example application that I published in other journals. Okay, in case of biomass pyrolysis or catalytic pyrolysis, many people is worried about the environmental contamination and fuel shortage and the increased waste masses. The microplastic accumulation is the typical example of these problems. So many researchers are considering the production of valuable gas, liquid, and solid products by the various kind of thermal conversion technologies. One of that is the torrefaction and the pyrolysis, gasification, and other catalytic related workers. So in case of catalytic pyrolysis, in my review, more than half of researchers are focusing on the catalytic in situ and ex situ pyrolysis. And some researchers are considering the co-feeding of hydrogen sufficient feedstock, such as waste plastics and methane or methanol, something like this. And also, some people are considering the high pressure catalytic hydrodeoxygenation of lignin model components, such as guaiacol and ethanol, like this. So their final goal is to produce the high quality oil production, having a low oxygen content and can produce high heating value. So from when I was master degrees, I also focused on the pyrolysis technologies, but at that time, I used this kind of reactors in my laboratory. So we call this is lab size or lab scale reactors. So in that case, normally long time is required, and also it's a little difficult to recover all of the products. For example, after the reactions, the inner surface of the condensers, the residual oil is difficult to be recovered. So total weight balance is also difficult to be analyzed. So that was my problems. And also even in the high pressure reactions, such as hydrodeoxygenations, the long time is required for the stabilization and reactions cleaning after the proper analysis. So I and Frontier Laboratory considered the developed of the tandem microreactor, which can be directly coupled with conventional gas chromatography technologies. So we call this is rapid catalytic screening device. So tandem microreactor is consisted with two individual reactors. First reactors is normally used for the pyrolysis. So in my case, I put the solid sample and free fall to the first furnace. And as the product of first furnace reactions, the pyrolysis vapor, so we call pyrolysate, can be transferred to the second furnaces. So, and also I load the proper catalyst to the second furnace and set up the optimized temperatures. Then the pyrolysate can be converted to the target components. So final products also can be transferred to the GC, and the final result can be monitored in your computer as a chromatogram. So I will show the example experimental result. First one is very simple catalytic pyrolysis. So there is a very interesting stories. So this is Korea, and there is a small beautiful island. We call this is Jeju Island. It's very famous as the citrus field. So citrus field has the pectin and hemicellulose, cellulose lignin as biopolymers. And our purpose to produce the aromatic hydrocarbon from citrus peel to produce bio oils. So I applied three kinds of different catalysts, which has the different PET surface area and pore size, and also acidities. So I saw one presenter used the pyrolyzer GCS technology to check the acidity of ammonia for the ammonia TP measurement. So I think it's also very interesting presentation, especially to me. So this shows the result of catalytic pyrolysis of citrus peel. So I wrote 2 milligram of citrus peel sample and pre-fall and pyrolyzed it at 500 Celsius degree on the helium atmosphere, and the product to meet the catalyst, and we can get this kind of chromatograms. So as you can see, in case of non-catalytic pyrolysis, many kinds of oxygen-containing products can be obtained. So of course, if some, for example, popular and monophenol guaiacol can be effectively used the chemical feedstock. However, the product is so many kinds of oxygen-containing products is generated by the simple pyrolysis of biomass, and it is very difficult to be commercially used. So many people apply the catalyst. So in my case, I use GLSM5. So as the result, most of the product is the aromatic hydrocarbons. So also I calculated the yield of BTX, monoaromatics and polyaromatics. So as you can see, over H-beta catalyst, total aromatic hydrocarbon yield almost 10%. But as you can see, the coke amount is also high. So one of the interesting point, for example, if I submit some papers, many reviewers request, how about the lifetime of the catalyst? So if you repeat the experiment without changing the catalyst, the yield of aromatics will be decreased. So please show me the result. So they want this kind of result. So as you can see, over HDLSM5, so it also, the efficiency also decreased. However, it maintained the higher performance than H-beta catalyst. So I also want to compare the accumulated coke amount. So in that case, I introduced air to the tandem microreactors and continuously monitors the thermal emission profile of carbon dioxide and water. So by comparing the peak intensity for the selected ion chromatogram, I can conclude the HZSM5 has the longer lifetime than H-beta. The main reason is the smaller amount of coke formation during the continuous reactions. So I think this kind of application is very helpful to estimate the catalyst lifetime during the continuous catalytic pyrolysis reactions. So this is the very famous reaction mechanism for the catalytic pyrolysis. So I think most of the researchers for the catalytic conversion of biomass may be well know this. So I want to briefly pass for the detailed expressions. And in case of second example is the co-pyrolysis of hydrogen sufficient waste plastic film to the catalytic biomass of biomass. So as I already mentioned, many people want to produce high quality oil by the simple pyrolysis of biomass. However, the yield of target products is still low, and the coke amount mainly produced by the phenolic components. So I consider the co-feeding of hydrogen sufficient feedstock. So like high density polyethylene and polypropylene can be the good candidate. And some researchers also applied the methane or methanol as a co-feeding feedstocks. So I checked there is a synergistic formations. So which is the best catalyst among that I applied. This is the result. In case of the non-catalytic pyrolysis, So we can see this kind of a typical biomass pyrolysis chromatogram. And this is the waste plastic film. So actually, my students collected various kind of waste plastic film and milled. So this kind of typical pyrolysis of polyethylene and polypropylene and polystyrene. And starch is monitored as the main pyrolysis product of waste plastic film. The important thing is if I don't use the catalyst, the kinds of the product and the peak intensity is almost the same. So this indicated that there is almost no advantage by co-feeding on the co-feeding of waste plastic film to the simple pyrolysis of catalytic coke. But if I apply the catalyst, so this is the in situ catalytic pyrolysis. The interesting point is this point. So over HLSM5 compared to the theoretical yield, which is calculated by the experimental result of individual feedstocks. So if I apply the catalytic co-pyrolysis, the actual yield was increased. So now many researchers are investigating this kind of catalytic co-pyrolysis technologies, and the main mechanism is proven as the catalytic co-interactions between the pyrolysates of different feedstock. For example, light olefins such as ethylene and propylene from the plastic waste, and the fuels and furan components from biomass intermediate. Okay, third one is hydrodeoxygenation reactions of lignin model components. So I use the guaiacol as a feeding materials, and I use different supporting materials. So the metal is ruthenium. So in case of these reactions, I inject 0.5 microgram of guaiacol to the first furnace. So for the HDO reactions, I applied the different temperatures from 200 to 600 Celsius degree, and compare the final products. If the effective HDO reaction can be achieved, the guaiacol will be converted to the benzenes. So my reaction is not a high pressure, just the conventional pressure of gas chromatograph. So the main product is the benzene. So as you can see, if I use the 5% ruthenium supported TiO2, the final yield of benzene is much higher than obtained over ruthenium HLSM5. So final example application using tandem microreactor is for the high pressure reactions. So actually this was very difficult because the high pressure, for example, 3 or 4 megapascal can be achieved by the conventional pyrolysis systems. So we developed the individual high pressure flow controllers. So by using these systems, the reaction pressure of tandem microreactor can be increased up to 3.5 megapascal. And also I can use the different kind of reaction gas. So mainly hydrogen gas is used. Also, even in the different tandem microreactor reaction pressures, the column head pressure can be maintained by the control of back pressure, individual back pressure controllers. So we can get almost same retention time chromatograms. So I want to make the large amount of oil from lignin, because lignin produces almost 50% of solid char as the product of simple pyrolysis. So I introduced different kind of reaction gas. One is helium and the other one is hydrogen. And the pressure is 3 megapascal. And the temperature is, one thing is 500 Celsius degree, and the other one is 700 Celsius degree. So as you can see on the hydrogen atmosphere, so pyrolysis product of lignin, even in the high pressures, almost similar with the typical pyrogram of lignins. So this kind of product is related with the phenolics, such as cresol, guaiacol, and alkyl guaiacols. But if I increase the temperature, the char amount was also reduced from 40 to 22 weight% of initial mass, and the additional production of aromatic hydrocarbon can be achieved under 3 megapascal hydrogen atmosphere. So this kind of application is almost the same as the high pressure cracking of solid fuels. So I think this kind of reaction can be efficiently used by other researchers participating in these conferences. So my conclusion is the various kinds of reactions can be achieved by the tandem microreactor efficiently, especially the time saving function is the beneficial effect, especially to me. So thank you for hearing my presentations.
Okay, thank you very much, Professor Kim. Guys, I'm sure that you find this presentation useful. If you have any questions on this presentation, please post these questions in the question box, and we'll take these questions in the question Q&A session at the end of the session. Okay, thank you, Professor Kim. Let me go to the next presentation. Okay. Okay, the next talk is on the is an innovative lecture, and its presentation is on the rapid evaluation of acido-basic properties of the solid catalyst using automated pulse reactor. The presentation will begin by Dr. An Kumar, a senior manager in analytical separation of science and technology at SABIC Technology Center based in India in Bangalore. He is an industry expert. Let me brief you about his experience. You can see he has plenty of experience in the industry. He was currently is working as senior manager at the SABIC Technology Center. He was with he was a lab manager at the GITC in Bangalore in 2002 to 2012. He was an assistant manager in the Recon R&D Center in Bangalore in 1995 to 2000. He was a research officer, Superfine Aromatics R&D Center in Bangalore, and he got a PhD in chemical sciences from the Manipal University in 2013. Now I welcome Dr. An Kumar to make a presentation now. Then I will give him a request to share his screen. Okay. Okay, can you open your PowerPoint, please?
Yeah. Yes, I do. Yeah, can you see the screen?
Yes, clear.
Okay, good, thanks. Thank you very much, Param, for the kind introduction, and I thank the organizers for giving me the opportunity and inviting me to talk about the research work that we have been doing in our lab. So this is a great opportunity for all the people who are working in the area of pyrolysis to be interacting not only from analytical but also from the applied areas, because there is a lot of synergy between the analytical and the applied pyrolysis. So let me start with my presentation. So the topic of my presentation is rapid evaluation of acido-basic properties of solid catalyst using automated pulse reactor. So this pulse reactor is an in-house pulse reactor which we have built in our center. And my talk basically sort of overlaps with the previous presenter, Young Min Kim, who actually had used the tandem microreactors for the pyrolysis. So in my talk, I will be talking about the catalyst which actually Dr. Young has used. So that plays a very important role, because the catalyst that is being used, that decides the specificity and also the yield of the product which we want to make. So in a way, the pyrolysis now will require a better catalyst or a suitable catalyst to be used. So for using a suitable catalyst, we need to ensure that we have tested or screened those catalysts so that it does the intended job. So in that particular scenario, we have, I'll change my screen. Yeah, so this is the content. I will be talking about heterogeneous catalyst, giving you a brief background about the basic concept and the techniques for evaluation that is being typically used for the screening of heterogeneous catalyst. And I'll be taking you through the automated in-house system that we have built. This is somewhat similar to the Frontiers Lab tandem microreactor, but the only difference is we have built it in-house. And there is sort of automation that we have introduced, which will be good for others also to know, and also if they can do it in a similar fashion using the available resources within the lab, similar things can be set up. And after having set up, we have studied two model reactions which are well known, mainly the dehydrogenation and dehydration of alcohols. In our case, we have used isopropanol and benzyl alcohol as probe molecules, and I will tell you the reasons why we have used this. And finally, I'll conclude with results and discussion and summarizing the overall work. So coming to heterogeneous catalyst, this as far as the basic concept is concerned, heterogeneous catalyst is a catalyst where one of the phase is different from the reactant of the product. So in this case, we have used the heterogeneous catalyst, which is a metal oxide catalyst, and the reactants and the products are in gaseous phase. So coming to the factors which affect the catalyst properties, so these are various properties which actually changes the catalyst effectivity or the activity, mainly the chemical composition, the surface area, porosity, the bulk structure and crystallite size, and the surface chemical properties, location of oxides, oxidation state, and active metals of the active metals. And the other important factor which I'll be talking in detail is acid-base property, and the oxidizable and reducible properties are also important depending on the nature of catalyst. So the catalyst basically has these around 7 steps. Mainly, first is when the molecules or the reactants has to diffuse, and they have to hit the right active sites inside the catalytic pores. And then there's adsorption, chemisorption, followed by the reaction that happens. And then once the reaction has happened, there's a desorption and again diffusion of the products back out of the pores. So why is the acid-base properties amongst all the other properties that are listed here so very important? Because the 3 major important steps, which is to do with the adsorption, the reaction, and the desorption, are very much dependent on the acidity or basicity of the active sites that are present on the surface of the catalyst. So In order to now look into the acidity and basicity, we need to have some means to measure that. Only then we will know which catalyst is active or which catalyst will be active at what conditions. So typically, the conventional techniques that are used are non-aqueous titrations, where people do titration using N-butylamine and find out what is the acidity of the catalyst. And similarly, they can use a acidic titrant to find out what is the basicity. The other most important one, which is widely used, is temperature programmed desorption. Here, the ammonia or carbon dioxide, depending on the acidity or basicity, is adsorbed on the catalyst, and then it is dissolved at a period using a temperature ramp. That gives us information of about the total acidity and also the type of acidic sites, acidic or basic sites. The other useful techniques are spectroscopic techniques, which is pyridine FTIR, CP-mass, NMR, and XPS. All of them have some advantages and some disadvantages, but these are being widely used. And then the last one is test reactions using probe molecules. So this is the one which I am more interested in, to look at how we can use probe molecules to look at the acidity or basicity on the surface of catalyst. And the reason why this is going to be important is the other techniques typically are done at a different temperature than the actual conditions of the reactions. But whereas if you want to use the test of probe molecules, you can actually find out the acidity or basicity at the conditions of reactions. So if you are doing at reactions at say 300, you can find out what is the activity at that temperature by using this probe molecules. So that's the advantage of using test reactions for probing the acidity or basicity of the catalyst. So I will dwell more into this aspect. So as I was explaining, these are the typical techniques, which is the FTIR, wherein we use pyridine and it adsorbs differently on the Bronsted acid or Lewis acid, and they have different bands, and depending on the bands, we can find out whether the acidity is a Bronsted type of acid or a Lewis type of acid, and then we can conclude on the overall the nature of the acid sites. But the only issue here is the extinction coefficient when it adsorbs on different catalyst surface. That may not be known, and to do the exact quantification, sometimes it becomes difficult. The other one, as I was talking about, is the temperature desorption, programmed desorption, and in this case, ammonia or carbon dioxide. So it is typically adsorbed at around 50 or 40 degrees Celsius over a period of time. And then it is ramped so that all the temperature is ramped so that all the physisorbed ammonia or carbon dioxide is removed. And depending on the desorption pattern, we can conclude whether it has more of low, medium, or high acid sites, or depending on the strength of that acid of the catalyst. So, but the only issue here is if you want to know both acid and basic sites, so you have to do two experiments. First, you have to do with ammonia, then you have to do with the carbon dioxide. Then you will get to know what are the relative acidity and basicity on the surface of the catalyst. So moving on to the next one, as I was talking about the probe molecules, so there are typical reactions which are carried out using these probe molecules. One is butene isomerization. Depending on the cis or trans formation, we can conclude whether it is the acidic or basic, depending on the ratios that we form. And it's a well-known technique introduced way back in 1971. And the other reactions, the more reactions that are typically used is alcohol, wherein it dehydrates or it dehydrogenates. So it dehydrates to if you are using IPA or isopropanol, it dehydrates to propene, or on the acidic sites, and on the basic sites it dehydrogenates to acetone. So the ratio of the dehydration or dehydrogenation products that are formed gives us indication about the acidic and basic nature of the catalyst. So this is widely reported, but one of the things which people tend to do is they do this using a solution phase, or where they do at a low temperature, and the products are analyzed offline on the GC. So that is what typically people have been reporting, and that also gives us a good indication about the nature of acidic and basic sites on the surface of the catalyst. So now we have gone one step ahead, wherein we try to use these alcohols and try to use temperatures at which the reactions are done and monitor the dehydration and dehydrogenated products. So that gives a very accurate way of measuring the acidic and basic sites at the reaction temperature conditions. And that's how we will be able to find out as to what will be the good temperatures to use and how it behaves at different temperatures. So to perform this, we have set up our own setup for the doing these reactions, which is, I would say, fully automated in a way wherein we only have to load the reactants and we get the results without any issues. So it's all done in automated mode. So this is the schematic. So what we have done is we have used a headspace GC accessory of a GC, which has the capability to generate vapors, and you can load more than 20 or 30 samples depending on the number of available auto the wires that you can load in the auto sampler. And then you can take different reactants in the headspace vials that is shown here. And this is now connected to a very small micro reactor, which again is fabricated in-house and which has the capability, which has a U-tube and which has the capability to hold the catalyst. So we can load up to 150 milligrams of the catalyst in this. So we typically use around 30 to 40 milligrams. So it gives us a provision to use a little bit higher quantity of the catalyst. And this in turn is directly connected to a GC with an FID. And if you use a DIN switch, this can be, we can measure both the gaseous thing and also the organic species that are coming out from the after the reaction. So this is the typical setup which we have built, and this gives us a good control on the type of reactant that we are injecting, and also the content and the concentration that we want to inject. It is all controlled. And once you have loaded all the reactants, and if you start the auto sampler and then the GC, so you can do around 30 to 40 screening in a single shot. So you don't have to worry, you can just load it and the next day all the reactions would be over and you will get the results. So this is the beauty of this particular reactor. So in actual, how does it look? I'll just show you. So this is the headspace auto sampler, and we have this small reactor, and you can see that they're all heat traced, the lines, so that we have used heating tapes with good precautions, and so that there is no condensations. And then this is directly connected to a GC. In this case, we have used the Agilent GC. And this can also be connected to a GCMS. Then you will know what are the different products that are formed, and you can characterize if you are trying to do a reactions using a high temperature on the catalyst bed. So after having set up this, we have studied 4 different catalysts. So in our case, we have used gamma alumina, and then montmorillonite clay, zinc oxide, and iron oxide. So we use this with which actually have varying acidity and basicity on their surface. So we try to pick up different catalysts, and you can see the gamma alumina is very strong acid. Then the clay is medium acid catalyst, and then zinc oxide amphoteric, and then iron oxides basic catalyst. So we try to use a variety of catalysts, and then we did reactions at different temperatures. In this case, we have selected 250, 350, and 450 degrees Celsius. And for the probe molecules, as I said, isopropanol is widely used. So we used isopropanol for doing the reactions. Along with that, we thought, why don't we use aromatic alcohol, benzyl alcohol, because that also undergoes transformation to toluene and benzaldehyde, so that we could study we could compare the products that are formed with isopropanol and benzyl alcohol, which would be giving us more information about the nature of catalysts. So this is the experimental procedures where we have used the catalyst and studied at different temperatures, and then we used around one microliter of the isopropanol and benzyl alcohol taken in different vials to generate the vapors, and known quantity of those vapors are passed on the catalyst bed, and then the products are monitored on the online GC with FID and TCD. So this is the overall details of the setup. And you can clearly see when I use propanol on this is a representative chromatogram where isopropanol, when it is used, it converts to acetone and propene depending on the catalyst that has been used. So mainly, as I said, propene is formed on the acidic surface and acetone on the basic surface. So this directly gives me an indication of what is the acidity or basicity at different temperature conditions. And similarly, we use benzyl alcohol to compare the difference between the alcohol that we have used to see how it behaves on different catalysts and what is the type of catalyst structure, or not structure, basically the acido-basic properties of the catalyst. So here we could see a benzaldehyde, toluene, and benzyl alcohol, which are clearly separated. And now coming to the actual results, when we have used isopropanol as the test reactions, you can see these are the 4 different catalysts on the x-axis: alumina, IMM clay, zinc oxide, and iron oxide. So this gives the conversion. So first we have to study the conversion, and then we also look into the selectivity. So in the conversion 250, 350, and 450, you can see for the gamma alumina at all the steady temperatures starting from 250, 350, or 450, the conversion is almost close to 100%. So the gamma alumina, the activity does not depend on the temperature. And when I look into the clay, the conversion is low at 250, and it picks up at 350 and 450. It's almost 100%. So this is a bit of a different catalyst compared to gamma alumina. So this is also clearly visible. And when it comes to zinc oxide and alumina and iron oxide, I'll club both, and you can see at low temperatures they are less active compared to the higher temperatures. The activity improves as we go to a higher temperatures, and that's how the conversion changes. And this is the corresponding selectivity. So in this case, we have used propene, and as we can see, for the gamma alumina, when the conversion happens, which is close to 100%, the specificity of the selectivity for propene is also very high. So this clearly indicates that this has highly strong acidic sites, which actually converts everything into propene at all the steady temperature. And when it comes to clay, again, you can see the selectivity is low, slightly low at 250, and then it almost increases to 100% at higher temperatures. So this gives an indication as to what is the type nature of the surface acidic and basic sites at low temperature, and how it changes at a higher temperatures. So same thing, we can also look into how the selectivity has changed at low temperatures, and it has gone to a different selectivity at higher temperatures. So this is very specific for the acidic and basic sites. But one thing which we could learn from here in this is, why is the propene in the selectivity of propene increasing at higher temperatures? So one of the reason which we have found is the nature of sites at low temperature. It's acidic sites which are very active, and which converts into propene. And as the temperature increases to say 350 or 450, the basic sites also converts the isopropanol to propene by a mechanism called E1CB mechanism, wherein it also tends to behave dehydrogenate, and dehydration is done where it converts into propene. So both acidic and basic sites gives rise to same type of products at higher temperature in case of IPA. So that is one of the deficiency when it comes to IPA. So when we move to the next probe molecules, which is the benzyl alcohol, as I was explaining, that we have tried to use the aromatic alcohol to see how this reacts at different temperatures. And here again, when it comes to the alumina, you can see the conversion is almost 100%, and the selectivity is also 100%. So this almost matches with the selectivity and conversion that we saw in the case of IPA for alumina. And when it comes to clay, zinc oxide, and iron oxide, here you can clearly see that the conversion is quite high even at lower temperature. The earlier ones, for IPA, the conversion was around 45%, and in the case of zinc oxide and iron oxide, it was even low. So, but in this case, benzyl alcohol shows that even small amount of active sites is good enough for it to give good activity, and then it converts into the corresponding dehydrated and dehydrogenated products. And here we can see that the dehydrated products at higher temperature is not substantial like we saw in the case of IPA. So this clearly shows that in the case of benzyl alcohol, it is sort of more dependent on the actual acidic and basic sites, unlike the IPA, where at higher temperature, even the basic sites tend to participate and convert IPA into propene. And that also has been reported widely by other researchers, and we also see in the case of IPA. And whereas in benzyl alcohol, we see the corresponding product of toluene is, I would say, concomitant with respect to the acidic and basic nature of the catalyst. So this are the typical model reactions, which helps us to find out what will be the nature of acidic and basic sites at high temperatures, at different temperatures. So we can use appropriate temperature for doing the pyrolysis of any material, either it could be biofuels, biomaterial, or the other fossil fuels. So we know what type of pyrolysis products can be obtained using this particular catalyst. So this is the comparison of IPA with benzyl alcohol, as I was explaining. So 2-propanol undergoes dehydration on acid surface and dehydrogenation on the basic surface. And similar is the case with benzyl alcohol. And the isopropanol is best suited for studying the acid catalyst, like we did for in the case of alumina. And when it comes to the basic catalyst or catalysts which are not very active, isopropanol tends to give issues when it comes to lower temperature, and it's also less selective because as the temperature is increasing, the products tend to give us I would say it does not differentiate the acidic and basic sites that very well as the benzyl alcohol does, because benzyl alcohol is more selective towards acid and basic sites at almost all the studied temperatures. So these are some of the studies that we have done, and now to summarize. So we have established the fully automated in-house setup by coupling headspace auto sampler with microreactor and the GC, which gave us good information about the products and also the quantification data. And sequential injections of probe molecules on catalyst surface at elevated temperatures was possible, and it was very rapid, and there was no manual intervention, so everything was automated, wherein the reactant and the products could be monitored within I would say 25 to 30 minutes of time, and we could study the reactions at 250, 350, and 450 degree, but there is a provision that we could go up to 900 degrees Celsius. The only thing is we have to then switch from the from glass U-tube reactor to quartz reactor so that it can be used at a higher temperature. And all the results that we got were good. It had good repeatability and reproducibility. And also we found that the catalyst that we had studied, the gamma alumina, clay, zinc oxide, and iron oxide, the activity of the catalyst, you can see the order alumina was very reactive compared to clay and zinc oxide and iron oxide. So this is the order that we could find, and this is very helpful when we are trying to select a catalyst for its intended use. And also the reactive probe molecules methodology is very sensitive and selective to reactive sites. almost like a fingerprint of the catalyst, because the reactions you can clearly monitor, and we can say what is the nature of this particular catalyst. So this is in brief the overall summary of work that we have done. And finally, these are some of the references which we have used to look at the typical probe molecules which people have used to study and then derive the equations. And finally, I would like to acknowledge my team members, Vinod, KN, and Ganesh, who have done all the lab studies, and they were fully involved in setting up the equipment for us to do the reactions. And a SABIC leadership team who have been very helpful and encouraging for us to carry out the research work that we have done here. So this is the overall thing that I wanted to present in this particular occasion.
Okay, thank you, Dr. Arun Kumar. I'm sure that you find this presentation useful to you all. Do you like to ask questions to Dr. Arun Kumar? Please post your questions in the question box. Please attention to him at Dr. Arun Kumar so that I take these questions for him only. Yeah, thank you. Let me take over my screen.
Sure.
Okay, the next presentation is a oral presentation. It's on the application of pyrolysis GCMS to ancient lacquerware. And the presentation will be given by Dr. Noriyasu Nimura-san from JOL Limited from Japan. Let me brief you about him. He has extensive experience, more than 30 years experience actively conducting applied research on various analytical instruments such as MS and XPS at JOL Limited. He has contributed a number of papers. You can see the list of the papers what he has done related to his research work, and he has a PhD from the Meiji University, Japan, finished in 1999. Let me welcome Dr. Nimura-san to make a presentation. Let me send a request for your screen. Yes.
Thank you, Chair. Good afternoon, ladies and gentlemen. I'm Noriyasu Nimura from JOL. Today, I will talk about the application of PYGCMS to ancient lacquerware. Here is the outline. At first, I'll talk about the natural lacquer, and secondly, about samples, which is ancient lacquerware, and thirdly, analytical conditions of XRF and PYGCMS. And finally, results and conclusion. Natural lacquer is a sap. Tapped from lac tree, it dries into tough film. So there are lots of historical art objects coated with natural lacquer. This table shows the composition of lacquer sap. The main component is phenol derivatives, showing about 60%, and about 20% is water, and about 5% is plant gum, and so on. This table shows the classification of lacquer tree. There are 3 types of lacquers used for coating. One is Toxodendron phalangisticum, which grows in China, Japan, Korea. Its phenol derivative is urushiol. Another one is the Toxodendron succedium, growing in Vietnam and Taiwan. Its phenol derivative is lacquer. The other is Glutayustata, which grows Myanmar, Laos, Thailand, and Cambodia. Its phenol derivative is titiol. This table shows the composition of urushiol. Urushiol is saturated and monoenil and dienyl and twenyl catechol. Luciol polymerized into tough film by the lacquer's catalyzed oxidative coupling, producing these CO coupling dimer. The samples in this study is a flake peeled off from an ancient eared cup excavated in China. It is analyzed by using XRF and PYGCMS. By using radiocarbon dating, the age was found about 500 to 400 BC. Here is the measurement conditions. Anode material of XRF was rhodium, and the atmosphere was vacuum condition. And the pyrolysis temperature of PYGCMS was 400 degrees Celsius, and the electrolyzation energy of MS was 70 eV. Next, I'll talk about the XRF analysis. These spectra are XRF spectra of black parts and red part. And the upper one is a different spectra obtained by subtracting the spectrum number 1 from number 2. In this spectra, iron was detected. This result indicates red pigment is hematite. On the other hand, in the black part, lead was detected. Red lead is reported to be turn black in the natural lacquer. So red lead must have been added to obtain the black lacquer. Next, I'll talk about the PYGCMS analysis. These are extracted iron chromatograms of the flake, upper one, and toxidendrin felaniscium lacquer film as the standard sample, lower one. In respective spectrum, in respective chromatograms, these alkyl phenols were detected. These are pyrolysis products of Luciol polymer. This result indicates that the coating material is toxidendrin felaniscium lacquer. The pyrolysis mechanism to produce C7 and C15 will be shown in the next slide. The heptanyl phenol and heptyl phenol, which are detected as the peak C7, are preferentially produced by the thermal cleavage at the acyl bonding of the catechol ring and alpha position to the double bond of side chain. So the relative peak intensity of C7 is the highest in the EIC. On the other hand, 2-pentadecylphenol, which was detected as a peak C15, is produced from the terminal groups, such as saturated Luciol. Now I'm concluding my presentation. PYGCMS reveals that the coating material is toxidendrin felaniscium lacquer. And XRF analysis reveals the red pigment is hematite. and red lead must have been added to obtain the black lacquer. In archaeological research, this information is useful to study the lacquer culture and process technology. We would like to thank Professor Miyakoshi of Meiji University and Dr. Miyazato of Urazoe City Museum for providing the sample and genius support. Thank you note to all audience.
Thank you, Dr. Nimura-san. Guys, I'm sure they find it useful. And if you'd like to ask some questions on this presentation, please post your questions in the question box, and please make sure your attention to the Dr. Nimura-san. Thank you, sir. Let me take over my screen. Okay. Okay. Now we are into the next presentation, and this is on the development of micro ultraviolet irradiation approach with the pyrolysis GCMS for rapid evaluation of photo and thermal. Okay, just a second, let me. Okay, now unmute him. Okay, I repeat again. Sorry for the interruption. The presentation is oral presentation on the development of micro ultraviolet irradiation approach with the pyrolysis GCMS for rapid evaluation of photo and thermal degradation of polymers. The presentation will be given by Dr. Sudha Tantri. She is also from the SABIC Technology Center, Bangalore, India. Let me brief you about her experience and knowledge. She has a master's degree in organic chemistry, and she worked in many pharmaceutical industries, having years of experience in analytical chemistry, worked in Recon Pharma, Jadis Cadilla, GE Healthcare, and now in SABIC. Currently, she's working mainly on the chromatography area, pyrolysis GCMS, TDS GCMS, HS GCMS, GC, GC, and developed many methods. I'm sure you find her presentation very useful, and so now I invite Dr. Sudha to make a presentation, and let me send her a request and to share her screen. Yes.
Hi, everybody. Am I audible?
Yes, you are. Yes.
Thanks for the introduction, and also thanks for the organizing team for giving me the opportunity to present in this Symposium. So my presentation topic is development of micro UV irradiation approach with pyrolysis GCMS for rapid evaluation of photo and thermal degradation of polymers. So this is our SABIC Research Technology Center in Bangalore. And we are working on various chemical, petrochemical fields. For example, chemistry, process engineering, application technology, catalysis, and sustainability, etc. And I'm working in the analytical science division. And move to the next page. This is content of my presentation. I will start with brief history, then micro irradiation technique, concept, etc. Then application and a couple of examples. So move to the history. So analytical pyrolysis concept started in 1948, and mainly like pyrolysis GCMS useful for deformation study, and the polymer sample is instantly subjected to a temperature high enough to break organic bonds, and it will give pyrolyzers and it will give the information about the organics, monomers, volatiles, semi-volatiles, additives, etc. And after that, this micro-UV concept with the pyrolysis GCMS was initiated by Watanabe in 2009. After that, many industries as a complementary technique, they started using mainly the polymer industries, petrochemical industries, and paint industries, etc. And it started evaluating from there. So this is the microwave radiation technique and the instrument established in STCB, that is the SABIC Bangalore Center. And we have the full capability of doing the microwave radiation technique along with the pyrolysis CMS system. And also we have the selective samplers also available with this system. And why we need this technique? So polymers, when used in outdoor applications, it will undergo degradation due to sunlight, humidity, and air. So that's why it is necessary to understand the degradation products or the mechanism to overcome this problem by adding required additives or completely modifying the process. So what are the essential elements for getting this results by microwave radiation technique as a complementary technique? So first one is the sample amount and the state. For example, what kind of sample you are using? Is it in the film form or in the pellet form, and also the particle size, homogeneity, etc. Everything will play important role when we are doing this technique. And also when we are conducting this experiment, so we are dipping our column inside the liquid nitrogen. So column is also playing very important role. So we are using frontier ultra-alloy metal capillary column because of the inertness, temperature stability, and also the mechanical durability. And also the third point is the irradiation time. So each polymer, when we are taking for the study, so the irradiation time is very important. For example, if we start with 1 hour, then also we need to study at second hour, 5th hour, 10th hour, like that, when we are establishing the method. Because each polymer will have its own properties, and under this microwave irradiation, so it will give different types of results when we are exposing for longer hour. So while establishing the method, we need to focus on the irradiation time, then we have to set up the time. And also next thing is the effective purging of air or the helium, because since the system connected to both pyrolyzer and the microwave UV, so when we are using the helium or the air, so we need to make sure that we are purging the system thoroughly, because otherwise it will not give the reproducible results. Next one is the temperature. So when we are selecting the temperature for micro UV technique, so we should not use more than 100 degrees centigrade, because typically the polymer for the microwave irradiation, the typical temperature range is starts from 60 degree and not more than 100 degree. This actually suggested by Frontier application team itself, and because after doing the microwave irradiation, anyway for the thermal degradation study, we can take that residue and we can proceed for thermal degradation. So in the UV, we need to set up the temperature as low as possible. So move to the next page. So this is a concept of microwave irradiated technique, and people in the industry, usually they will use the conventional techniques and for evaluating this degradation study of polymeric material, and they require several weeks or the months to study, and it will not provide the complete information about the chemical reaction occurs during the degradation. But in case of microwave irradiation technique, this is kind of an in situ kind of system, because when we are doing the irradiation, you can change the time and you can set up the parameters, and within an hour or within a day you will get the results, and also it will give the complete information about the chemistry of the degradation process, like what are the chemical components are coming out, and how you can set up the process in the later stage. So this is a schematic diagram of the microwave irradiation technique, and this I have taken from the Frontier operation manual. And how it works, it mainly involves a xenon lamp there, where the UV intensity ranges from 280 to 450 nanometer, and it's delivered via an optical fiber cable. So the volatile degradation products will be cryotrapped during this irradiation time, and at the head of the separation column, what I mentioned was dipping in the liquid nitrogen, and then later it will be analyzed. So moving to the next page, I will not go into the detail of the theory or the mechanism. So because everyone knows the degradation starts from initiation, then it will follow the propagation step, then finally it will end up with the termination step. So all the steps depends upon the individual stability or the thermal properties of the material. So it's not one set of parameters will work for all kinds of polymers. For each polymer, we need to fine tune the parameters and we need to study. Then we have to conclude the mechanism and also what are the degradation products are forming. So moving to the next page. So when we are starting with this micro UV radiation experiment, first actually we need to validate the system. For this validation purpose, Frontier itself, they are providing the polystyrene standard in the form of film. And before starting any experiment, we need to validate the system using this polystyrene disc. And I have started with the experiment using this polystyrene disc film provided by Frontier, and I have matched with their the profile. Here I am highlighting only the benzophenone, benzaldehyde and acetophenone. Those are the major components, and we have matched with the Frontier profile. After this confirmation only, we are proceeding with the further experiments, whatever the internal polymers or whatever the other polymers we are subjecting for the testing. So moving to the next page. So here, because of additional approval process, I am explaining only the one example, that is the polycarbonate in general. So this is a commercial sample I have taken for the analysis. And if you look at the first part, this is a micro UV radiation experiment results. Here the polycarbonate will undergo photooxidation, then followed by photoprise rearrangement, then finally cleavage of covalent bonds. Here we are focusing only on the photooxidation components, and after doing the experiment, the product developer and also the technical team, they will look into the components and they will decide how it will undergo oxidation, that's photooxidation, and based on that scientists will move into the next process, like how we can arrest these kind of photooxidation process. So the bottom one is the pyrolysis GCMS experiment. So after doing this micro UV experiment, then we can take out that residue and you can further do the deformulation study to understand the thermal degradation process. Here, if you look at the mechanism, it will go chain session, then followed by transesterification, that is hydrolysis, then rearrangement of carbonate linkage, and finally the coupling will happen. So here we are focusing only on the backbone information, that is is kind of a complete deformulation study. So moving to the next page, here I am highlighting, so what are the advantages of micro UV technique in comparison with the conventional technique. So these are the main advantages. For example, flexibility on the temperature selection for photothermal study, and then the speed of the analysis. As I mentioned, within a day or within few hours, you will get the preliminary information on the photooxidation process, what are the components are forming. Then also the sample amount with the use of sub-milligram level, for example, from 0.1 to 0.1 mg level, you will get the complete information on the photooxidation process. And also the residual, whatever left over, we can again subject it for pyrolysis GCMS, that the complete deformulation study parallelly. And in the conventional technique, these things are not feasible. And also, as I mentioned, it will take several weeks or the months for the complete understanding. And also it requires some specific dimension based on the industries, what type of polymer or the paint or whatever the type of samples they are using, it needs some kind of specific dimension. And also chemical components details, it's not feasible to get immediately from this conventional technique. And what are the industries, different types of industries they are using, and also started developing the methods using this micro UV radiation technique. That is the automotive industries mainly, and also the petrochemical, then polymer industries, paint, coating, and even pharma industries also, they started utilizing this technique. Mainly to design, use and understand the effect of additives, mainly on the antioxidants, UV stabilizers, pigments, etc. And based on the photooxidation process, they will modify or they will develop a new type of UV stabilizers or the pigments in their formulation. And also they will get the information on the photochemical reactions, what type of mechanism is happening, and also based on that the UV curing they will examine. And also people are using for volatile analysis and also for the unknown analysis after degradation. So after I have conducted the experiments for a few different types of polymers, and going forward, my aim is what are the limitations of this microwave irradiation technique in comparison with the conventional techniques, because conventional techniques, they are telling the wavelength range is 295 to 3000 nanometer, and also they are keeping it for longer time. However, what are the differences and also the comparison results it will give? So that is my next path forward action. And with this, I am concluding my presentation, and I am acknowledging SABIC management for giving me the opportunity to present in this e-symposium, and also my manager Arun Kumar and other leadership team. And also, finally, I would like to thanks Frontier and LCGC team for helping me with the technical support, and also where and all I was asking for some queries. Thanks.
Okay, thank you, Dr. Sudha. I appreciate the presentation, and guys, I'm sure you find it useful. Now we're almost finishing the presentation part of the session 1. Now we're open for Q&A session. Okay, so please post your questions in the question box. Okay, I have received a number of questions already for a number of speakers. I'm going to screen, and I request all the speakers, please put on your in the session from Dr. Kim, Professor Kim, and Dr. Kumar, and also Dr. Nimura-san and Dr. Sudha. Please be on, show your webcam so that I can, show your questions and you can answer them appropriately one by one. Okay. Let me take over my screen for a minute. Okay, we have your Q&A session. Okay, I'm going to post the questions what I received. Okay, and also for Shagos and also could kind of moderate this session together. Yeah, let me post my questions first. What participant asked, right? Okay, now the beginning questions are for the Professor Kim. Yeah, it's all yours, sir. Now. Okay, if you don't mind, can you briefly make it quicker, summarize the question, and also summarize the answer also as brief as possible. Yeah. Okay. Yeah.
Okay. So so actually I use the nitrogen and helium. So 25 bar is it's not a batch system. So we use the very narrow restrictor to maintain the high pressure. Yes, also in the continuous process is possible because it's not a batch reactor type. The second question is, I think almost the same. Inline steam is also possible, but yes, so the liquid feeding is a little limited. So it's also possible, however, you have to use the vaporization and the large amount of liquid injection has to be avoided. So you have to need the syringe type in syringe needles for the continuous injection of a small amount of feeding liquid feedstocks to the system. Okay, that's all.
Okay, let me post the next slide. Okay, here.
No, it's back pressure to control the head pressure of the main column. So even in the different main reactor pressures, the column head pressure is maintained. So I couldn't check any material lost until this time. Catalyst characterization. Okay, so in my case, the lifetime of catalyst is compared with the yield of products. So if you need the different characterization of the coke formations, so I use our system by switching the carrier gas from helium to air to burning out with heating the catalyst temperatures. So it is possible. And also if you want to characterization, further characterization of coke with other technologies, you can collect the used catalyst after the reactions, and you can do your own analysis technologies. Okay. Oh. Yes, so it was well known the hydrogen content of plastic is larger than the biomass normally. So you can compare the effective hydrogen to carbon ratio by the specific calculation equations, and you can apply any kind of plastic to as a hydrogen source if their hydrogen content is high. And the last question is, so, okay, the carbon yield is calculated based on the initial materials. So the product is divided gas, liquid, and solid. So this is not a yield of total liquid, just for the aromatic hydrocarbon. So normally in case of biomass conversion, less than 10% can be achieved. But some papers use the large of catalyst. For example, for the 1 milligram of biomass catalytic pyrolysis, they use 20 or 30 milligram. In that case, the yield can be increased up to over 20%. But in my case, I minimized the catalyst use amount. So 1-to-1 feedstock to catalyst ratio was maintained. So that was the reason the lower yield of carbon in my research. Oh, so many questions. So in the slide is maintained water. Yes, it's other aromatic, monoaromatic hydrocarbon is except to the benzene, toluene, ethylbenzene, and xylenes. The main product is BTEX, and the other alkylated aromatic monoaromatic hydrocarbon was contained in these other aromatic hydrocarbons. And the next one is the...
Okay, it's for the Dr. Arun. Yeah, thank you, Dr. Kim.
Okay, thank you so much.
Good.
Okay.
Yeah, it's for you.
So what are the key properties of any catalyst to be considered for any applications? So basically, there are physical as well as chemical properties. So as far as chemical properties are concerned, the acido-basic properties is one of the key factors. The other properties which one actually looks into is what is the surface area, and also the strength of the catalyst, because catalyst should not, there should not be any attritions. So those are the other criteria which people tend to look into, because these are the ones which decides the catalyst property. And also the catalyst should be effective for long life. It has to have a long lifetime. So that's another area that people will have to be looking into when they are selecting a suitable catalyst. And are acido-basic properties taken into consideration while selecting homogeneous catalyst? Yes, in homogeneous, the catalyst typically are either acidic or basic. Either it could be as simple as sulfuric acid, or it could be caustic, or it could be sodium borohydride. So these are depending on what are the requirement, they will have to select whether it is acidic or basic. Yes, the criteria will have to be applied there as well. What is the particle size distribution of catalyst? Is it powder sample? Could you mention the pressure and flow nature of input and output? Thank you. So as far as particle size, we have used these are around 1000 microns. These are not very highly powdery, because if you have a lot of powder, it will generate a lot of back pressure. So we have used around 1000 microns. And the back pressure is not that much, because we have connected this in line with the GC. So typically the GC will have around 5 kPa back pressure, so it continues to be the same, unless like the earlier speaker Youngman, who has used a the restrictive type of column which generates back pressure. So in our case, it is not, we are not doing under pressure. And what are the key properties of any catalyst to be considered for any application? I just mentioned it's the surface area, the porosity, the acidity, basic properties, and also the lifetime of that catalyst, which is going to be, and also the physical properties like attrition. It should be stable for a long period of time, and it should withstand pressure when the reactant is flowing on the catalyst bed. So these are some of them, but there will be many others when you are trying to do the scale up in the plant. And are acido-basic properties taken into consideration while selecting a homogeneous catalyst? So basically, catalyst, either you take a weak acid catalyst, or a strong acid, or a weak base, or a strong base. So these are very much important, because not every catalyst will be suitable for all. Sometimes it may be very highly acidic, but may not be suitable, because it will generate more of byproducts than the main product that is required. So for any catalyst, there has to be a good understanding of the strength of the catalyst in terms of acidic or basic property wherever we are using catalyst, either it could be homogeneous or heterogeneous.
Okay, it's not a break yet. I think that Professor Shogo-san, you have some questions to Dr. Nimura-san. Yeah.
Okay, so Dr. Nimura, thank you very much for your great presentation. I have very simple question. So based on XRF analysis, so I could find several inorganics. So is there any catalytic effects on the pyrolysis of Urushiol? I cannot hear.
Just a second.
Okay.
Okay, yes, now it's okay, yeah.
So you're asking about the XRF analysis? Yes,
the XRF analysis found several inorganic compounds in the material. So that's why I am wondering the catalytic effects of inorganics on the pyrolysis reaction.
Okay. In the pyrolysis analysis, I use samples top surface.
Okay.
So top surface has no pigments, only lacquer. So the sample has not inorganic.
Okay. Okay. Thank you very much. Thank you very much.
Okay. I have some more questions from the audience. Okay, this is for Dr. Sudha.
Yeah, the first question is, can we use a microirradiation technique for characterization of environmental microplastics? definitely we can use it, because any type of like solid polymer or the plastics we can use and we can study. But we need to see the end application, what end application they are looking, and also what type of information they are looking for. Definitely we can use this technique. And next question is, have you used titanium oxide in any application of micro? No, till now I have not used. Only plastics and the polymers, that type of samples.
Okay, there's another question. Do you have a plan to design U-tube reactor that can withstand higher pressure? So as of now, our type of application, we have no plans to do a high pressure reactions, because we'll have to ensure that it is withstanding, and then all the safety aspects have to be ensured. So at present, there is no plan, because our application does not need that type of thing, unless we are going in for the pyrolysis of biomolecules or some other waste plastics to study what happens under high pressure. So at this point in time, I would say no.
Okay, that's all the questions we have here. I think Professor Shogo-san would like to summarize this whole session. Yep.
Okay. So thank you very much, and I'd like to express my thanks to all speakers. All the lectures should be useful to all of us to know the recent trends of PYGCMS applications in the field of environment and archaeology and material characterization, and also new instrumentation such as tandem microreactor GCMS and automated online reaction screening reactor for rapid evaluation of catalytic reactions. It should be a promising approach to accelerate research and development in the applied pyrolysis field. And also, the UV PYGCMS allows to direct analysis of volatiles during the UV irradiation, so which will open the new insights to understand photo-oxidative deterioration mechanism. So that this session was really fruitful, and again, I much appreciate all presenters and active discussion. Thank you very much.
Okay, thank you very much, Professor Shogo-san. Thank you all for joining this first session. Now we take a break for a 15 minutes break. Okay, and we start the next session in 15 minutes. Okay, thank you.
Thank you.
Everybody can get drink some coffee or have quick lunch, whichever the way. Okay. Okay, good. Yes, fine. Yeah. Okay, thank you. I still have one speaker. You know Dr. Farid Nazir? He's not registered. I cannot hear you. Self-muted. Can you? Okay.
Yeah, sorry. Yeah, I sorry. I don't know him personally. Maybe I can ask to Can we ask to Karthik?
I tried to
Dr.
reach
Karthik?
Karthik. He's not picking up the phone, and
Okay.
he
Ask,
actually he has to. I could not find his mobile number to call him, but I'm not sure he's checking my my emails or not. Okay, because he logged in as a delegate, and I could not make him as a panelist.
okay.
So he has to log off and log in again. I sent him the request, but I'm not sure he checked it or not.
Okay, because maybe Arshad, Dr. Arshad knows him. He has a meeting, it seems, at this point of time.
Okay.
Okay,
Let's see what happens. Okay, I'm trying to reach him. Yeah. Okay. Thank you. I will be, another few more minutes. We have to start. Time flies so quickly. Eh?
Ram, can you hear me? Hello?
Professor Mohanty, yes, I think I can hear you.
Yes, Suchitra, how are you?
Good. How are you?
I'm fine, I'm fine. So
Okay.
what is the presentation time for me? 15 minutes if I
Yes,
am
15 minutes.
correct?
15 minutes presentation.
Okay.
That's right. Yeah.
It's a very odd time in India. It's lunch time. It's 1 p.m. now. Yeah, it's okay, fine, no problem. So we'll go by that sequence, correct? Yeah.
That's right. Yes.
Yeah, sure. Okay, fine. So the first talk will be around 20 minutes, then 15, then 15, right?
Yeah.
Okay, okay, fine.
Because this session okay. Here's the
Yes, you are telling something.
okay. Just a second. This session has only 3 lectures, 3 presentations, and the Q&A session. Okay, so it's allocated 2 hours time. So if there are some more questions, or if you we have some additional points, you can at the end you can also add if you're required. Yeah.
Yeah.
All the speakers are
So
open.
actually, my talk will begin at around if we are going to start at another 5 minutes. So my talk will be 20:30. At around Indian time 1:30 onwards, my talk will start. Probably correct.
That's right. Yeah. Okay, I'm a bit confused
Yeah.
with the
So
different
I
time
may
zones
just
now.
go.
Yeah.
I may just go for a quick lunch and come back. Yeah.
Okay,
I'll be
but
online.
there is a situation right now. One of the speaker, he is still not log in yet, and the
Then you
second,
can put me as the first speaker.
the
Is it
second,
possible to put me in the first speaker? Yeah.
the second could be second. The first is a keynote lecture, so let's keep that keynote speech.
Keynote. Okay, fine, fine,
Yeah,
fine.
yeah, yeah.
Second will be fine for me. Yeah.
Okay.
So then I'll go for a quick lunch and again join for the question and answer.
Okay.
Drop me a message. Yeah, I'll be ready. Yeah.
Sure.
Anyway, I'm there. I'm sitting here only. No.
Sure.
Thank you. Yeah.
Professor Haiping, are you there?
Yeah, hi.
Hi there. Okay. Just want to make sure you can hear me. I can hear you. Yeah. Okay. You had your lunch already? Yeah.
Yeah, it's 3:30 now for
Oh,
us. It's afternoon.
okay. Somebody is hungry. Somebody is okay.
Yeah, Indian friends is hungry now.
I know. Let's. I have the. We have one speaker who's still not. Okay. Now let's see. Still use the. Professor Farid Hani, if you hear me, can you please log in as a panelist, please? I sent you the link. Okay, I have sent you link. Kindly log in as a panelist. I have sent you just a send you link. Please click on that link, panelist link, and you can access into the presentation format. You have logged in as a delegate now. Kindly log in as panelist. I have sent you an email just now. I hope you hear me. Okay, we get started for the next session. Welcome you all back to the Pyro Asia 2020. I'm thankful to all the sponsors and the speakers for joining and contributing to this virtual event on the Pyro Asia Forum 2020. Now we are into the second session. Okay, I will now invite Dr. Suchitra Gopakumar to chair this session, and she is currently working as Associate Professor in Chemical and Environmental Engineering at the University of Nottingham, Malaysia. Her research focusing on the development of liquid biofuels and extraction of chemicals from various biomass feedstocks through the thermochemical conversions and catalytic upgrading. She has been part of organizing some of international conferences and actively presented in the exhibitions as well. And also she's a recipient of some of the research grants at the university and national levels. And she received the status of Fellow of the Higher Education Academy UK. She's also an associate member of Institute of Chemical Engineers and Indian Institute of Chemical Engineers. Now I invite Dr. Suchitra Gopakumar to introduce and discuss about this second session. Dr. Kumar, all yours now.
Hi, good afternoon. Good afternoon, everyone. Today we have session 2 on Pyro Asia Symposium, e-Symposium. We have 3 experts talking about biomass pyrolysis and the 3 different aspects of biomass pyrolysis. Professor Yang from Hasong University will be discussing about pyrolysis polygeneration. And then we have Professor Nasir Eni. He will be talking about microwave pyrolysis, and we have Professor Mohandi from IIT Guwahati will be talking about co-pyrolysis. So let us hear for these three exciting speakers. Thank you. Here. Okay, we have
the keynote lecture. Okay, now introduce the professor. Yeah. Okay, let me introduce Professor Haiping Yang. She's born in 1997. She received her PhD in 2005 from the Department of Energy and Power Engineering, Huazhong University of Science and Technology. Then she joined HUST in 2000. Okay, I'm sorry. Okay. I guess it became the professor in 2016. Her research is focused on the biomass pyrolysis and gasification for hydrogen enriched as gas fuel, liquid fuel, and carbon nanotubes, carbon contained materials and chemicals. So far, she has published over 100 papers, and 6 were cited in ESI, and highest SCI cite for one paper is over 3,300. Now she owns a Newton Advanced Fellowships and the most cited Chinese researcher elsewhere in 2014-19. She gained the National Science Fund for Excellent Young Scholars Program in China. She is an associate editor of Fuel Processing Technology and also the member of the editorial board Fuel and Journal of the Analytical and Applied Pyrolysis, and also the guest editor of Fuel and Journal of Analytical and Applied Pyrolysis and Bioresources Technology. Professor Haiping, when I read this bio, I'm sure so much information in your experience, and I'm sure you find her presentation is very, very useful. You can see her her citations are super. I welcome Professor Haiping to make a presentation. Let me ask her to share a screen. Just a second. Okay, here I go. Yep. Can you share your screen, please? Yes. Okay.
Can you see my screen now?
Yes. Now I can see you. Yes.
Okay. Okay. So good afternoon, everyone. Also, thanks for the organizer for the introduction or the invitation. I'm very glad to be here to show what we have done recently. So my presentation is about the biomass pyrolysis and multi-generation and on the biochar upgrading. So firstly, let's go to the not only energy resource, is also environmental issues because it has the carbon neutral, the carbon recycle things. So we say it's carbon neutral. Also, another point is because the biomass for the process technology is conversion technology mostly is similar with fossil fuel. So I mean we can use the technology from fossil fuel. If we go to the point about the carbon neutral one, so we can see if for the we know in China, the Chairman Xi already announced in 2060 we will have the the carbon neutral in the 2060. So so if the CO2 issue is very critical for us now. But if we converted the other biomass to the carbon to the biochar, so it's only in China we can reduce the CO2 emission in over 3,000 million tons for the carbon equivalent. So it means if we use we combine the pyrolysis, so we combine with the biochar, so we can input the biochar to the soil admission. Also, maybe it's for the pollutant control, so we can keep the CO2 inside. I mean, we have the for biomass is some kind of carbon negative one. Also because technology development, we know now we need a lot of the materials, also like the battery for some smart instruments also for the bacteria. Also we see like a fuel cell, we need to have storage hydrogen, we need a storage energy. We also have needed some catalyst. So the biochar is also can be used for energy storage, or what's called catalyst also for the other options. So it means the biochar production and the functional application is also one of the most promising technologies. So for China, for China, we know in China, because we are the agricultural country, so we have a huge amount of biomass resources. It's like now, maybe in 10 years, we can have the, I mean, each year we can have 10,000 million ton dry biomass. So it's most 2 times about the primary energy consumption we use. But now currently, is the utilization ratio is quite low. Also for the biomass resource, we in China mostly have agricultural waste. So the mean in China, we for the agricultural waste utilization is very important, also urgent for us. For the biomass utilization, we know that it have for the same chemicals one, it can be the combustion, also combustion to the CO2 to heat. I mean, we can have a heat, we can have power. So we also can go to the gasification part to syngas. It means after that we can synthesize to different kind of like the liquid fuel, like the machination to ethanol. Pyrolysis is mostly quickly, fast and efficient. So you can see pyrolysis, we can convert to biomass not only to gas fuel, we also can go to the liquid oil, we also can go to the solid char. So solid char can be, if we have the other upgrading method, so we can go to the biochar, we can go to the carbon contained materials. So it's been biomass for the pyrolysis can convert biomass to energy very efficiently, very quickly. Also, so now we go to our main part is about biomass pyrolysis for multi-generation. I mean, the technology we developed recently. We know that pyrolysis normally, the conventional pyrolysis normally is go to the, if we have the low temperature, we have the very low heating rate, we can get the main product is about the solid char is named carbonization. But if we go to very fast heating rate, also the very short time in 1 second, so we can get half like the over 50%. We can go to bio oil, but if we go very high temperature, so the main product is for gas fuel. So for the pyrolysis mostly is for a single product, like for carbonization, mostly for solid char. Fast pyrolysis mostly more focus on the bio oil. But if we go to a high temperature, mostly we want to get the gas fuels. But we know that biomass pyrolysis normally can go to the 3 types different products. This means we can get the gas. We also have the liquid fuel. We have solid char. But if only for product, this means maybe we will cause other like waste, like the gas or solid char to burn directly for heat. So it means the efficiency, the system, the overall efficiency will be quite low. So we are thinking about, is it possible we can get the oil, gas, char as a product together? It means is it possible to control the process or control? We add some catalyst or other autonomous different. We can get these 3 kind of products, get some kind of a high value one. So based on this one, we go to the product, I mean, we go to a process to check how about the product, about the value is very low. Also for the liquid products, is mostly is like the dehydrosugars. So for the solid char part, is also okay. So the chat parts is mostly we have high yield, but the heating value and the subsidy is quite low. So if we go to the 500 to 600, we can get the large amount of hydrogen methane gas. So the heating value will be quite high. Also in the liquid part, you can see we can get the benzene, we can get the fluoride chemicals can be upgraded for the high values one. Also for the solid char part, you can get the heating value is 28. For the char content is over 19%. All this means this one is very close to bitterness coal. It can be used as coal directly, or if you can want to upgrading, you can add activation. You can get a high value of software for active carbons. But if the temperature is more think about maybe if we can focus the temperature at some kind of middle heating values, gas bill. Also, we can have the liquid oil is enriched of fluoride, enriched or benzene, or enriched of the some coals. For the solid char part, we can get the kind of high heating values carbon materials. Adding in, then after drying after pyrolysis, then they can go to the solid char. So the gas, the volatile will go to the top after the after the then go to the conditions, and then go to the gas cleaning. And then this one can be storage in the gas tank, then can supply to the so you can see for this system, the heating is from the some kind of we have like the gas like 30% too. So one part is like mostly for the fertilizer or some pesticide. So for this one, we have designed, we have built some demonstration parts for the in those the near Wuhan in the torrefaction. So after torrefaction, it can be uploaded to the top. To this reactor, here, so we can go to the pyrolysis. Then the third chair can go to the top, the water like the downside. Can here is our system is like this one. Okay, so for the gas, mostly we storage it in tank. After storage, we can go to the locally just 2 kilo far away. The town, they have the villages, they have farmers here. They can be used for cooking. So for this system, the chair. Made so the biochar from our products like the wood chips, like here, also some bamboo chips, also some rice husk carbons like this. Here, maybe after that we will grinding, then grinding we will made the pellet. Then can store it, can keep in some box and in for the barbecue, for some heating. There also can be some arts for the maybe also for the air cleaning. Also, we tried for the for the soil emulsion for the potatoes. So it seems.
Professor Hyping, I had to apologize. There is an interruption with your internet connectivity. And if you don't mind, I need to stop your presentation here because we can't hear anything. Professor Hyping, can you hear me? Professor Hyping, can you hear me? Professor Hyping, are you there? We lost your audio and also the internet connectivity is very not smooth. We need to find some other solution to do this again.
Professor Yang?
Again?
Hello. Yeah, we are not able to hear you.
Yes, we had. You had.
Okay, so you mean cannot hear me? Oh, okay.
I need.
You mean my net is too slow, or?
Yes, I think your internet connection is pretty poor condition, I think, and we can't hear anything. Yeah.
Oh, okay.
Now it looks clear. Okay, I don't know how long. Yeah. Actually, we lost a lot of your content. Actually, I don't know how I'm wondering how to interrupt you. Okay, but it's we are unable to hear anything. Yeah.
Yeah, we didn't hear about your reactor also.
So, I mean, it's possible we. Okay. So it's possible we so where we need to repeat to continuously go.
Okay, now it is
Can
clear.
You start,
now.
yeah,
Now
it is clear. Can you go to from the moving bed reactor slide? We lost
Okay, so this one.
Yes.
Okay. So is there any problem? So you can interrupt me. Sorry.
Okay.
Maybe it was in a campus, the university's website, the internet is not very good.
Okay. Okay. Thank you.
Okay. So I can start. I can continue on.
Yes, please.
So for this one, Okay, so we use the moving bed. We design the moving bed is like because firstly we use biomass from the rotary some screw like rotary clean for the torrefaction. So after torrefaction, your biomass go to the top of the moving bed. So this one, the biomass from the top to the bottom, we will heating up. The woolen tail will evolve out. Then the biomass will go to char. So the char will go to use a screw. After water cooling can be go out when it can come back pack like this. We have the biochar like here. Then for the gas part for the woolen tail is to go to the top. Then we go to the condensation with the water or with the air cooling. So we can have the two parts of oil, like the heavy oil, also the light oil. So the light oil is most like the water and some parts of sulfur and phenols. After the conditioning, it can go to the cleaning with water spray. Also with another part is with active carbons or the substance. So after that, the biogas will send out for the for cooking. So here we have the product like this. For the gas, we have the 30% of the gas. It have the heating value is like the over 10 million joule per cubic meters. For the biochar, we have like 35% of biochar. Also for the oil, is one for the we have 25%. So we also analyze the economic issues. So it seems for this system, the economic issue is okay now. So we have designed build demonstration parts in the although it's just 1 hour from the far away from our campus, is for the 110 per hours. So from the right side, you can see we have biomass here. So you can biomass will go to the belt, then will go to the rotary clean to torrefied. So after torrefied, it will be uploaded to the top of our moving bed reactor. So after reactor, so we can go to like we have here, we have the whole system is like this one. So we have the different kind of like liquid products, also our solid product like here. So for the gas one, firstly we will store it in a gas tank. Then we will send it to the 2 kilometers away the villager here. We have the small tank here, so we can use for the cooking parts. For this system, after building and running, the chairman C have great idea. So for the char parts, so firstly we get the particles char, like the rice husk, like some straws, we will get the char particles. Also like some wood chips, we have some blocks. Then after that we grind, we have some, then we made the pellet, then can be used stored in a box for to add products. It can be like barbecues. Then we also made some biochar for the us. We also have soil emulsion. So respect to the biochar part, so we know that from the moving bed or from the direct pyrolysis, we know the for the char, the surface area is very low, is like only 200 something. If you it only can be used maybe for the burning for heat or in the power plant, also in the in the barbecues, but it's still low quality one. So if possible for carbon materials, if we want carbon materials, it means you need to do a lot of upgradings. So based on the upgrading here, they have so you first one you need to activation to open the pore. You have the physical one, also chemicals one. Another one you need to active side, like use ammonia, use metal doping. So first, based on the pyrolysis, we also tried like use the ammonia, use the CO2, use the potassium hydroxide to active the to open the pore. So you can see really we have some after the CO2 ammonia activation. So we have the larger surface areas. Also, we have some more nitrogen on the surface. So we tried with the CO2 adsorption because we are in our lab we are co-combusting, so we have large amount of CO2. So here we tried the CO2 adsorption. So you can see with the ammonia doping, also with CO2 activation, you can see the CO2 adsorption increase greatly. But one thing we need to know that because this one is firstly we pyrolysis first, then we go to the modification. So this process we think is a little bit complex. So we think about is possible we can combine the pyrolysis with the activation or with this downstream some upgrading process together. So we tried we designed this one-step method. So we during the pyrolysis we had a mix with the activator, we mix together inside the together to use pyrolysis. Then we checked the porous carbons. So here we tried the two parts. One is two step, also one step. So from the two-step compression, we can know that after one step, we can get a higher
Professor Yang? Professor Yang, we are not able to hear you.
Is cannot hear.
Okay, I think. Hello, Professor Yang? Hello, Professor Yang, we are not able to hear you.
I think her internet is not stable at all.
So maybe we are stopping here.
Yeah, I think we let her. We stop. We let other presenters to. Professor Hyping, are you able to hear me? Unless you're offline now.
Oh, okay.
Okay, I'll take over screen, and we apologize, for all this inconvenience, all participants. Okay, it looks no choice. Okay, and I'm going to take over the screen.
Now?
I'm sorry, we're unable to hear you, Professor Hyping.
So now you cannot hear me?
Now I can hear you, yes. Okay. Okay.
I changed because just now maybe the internet is too poor, so I changed to my handphone website in the internet.
Okay.
So maybe we try again. So from this slides still from this slides.
Yeah. Okay. Yes. Now you can start now. Yeah. Okay.
Yeah, this current slide you can start.
Okay. Okay. So just now we mentioned about because if we get the first pyrolysis, we get the charge, then we go to the activation, we go to upgrading. It means we think we have two steps. So the process we think is too complex. So we think about it is possible for one step. So we tried the one step firstly. So when we here. So you can see the one step one, the software have a very large one. Is most double compared with double or triple compared with or two steps one. Also, the pore size is different one, different greatly. So you can see for the one step one, mostly they are mesophore. but for the two-step one, mostly they are like the micro. So in this because pyrolysis parts, the activator will react with the oxygen content, the active parts. So later we will explain the mechanism. Also, we compare the nitrogen doping parts. You can see that from the two-step one, the nitrogen doping, the efficiency is very low. It means only 1% or 2% is can be adopted to the carbon. Also, also on the surface part is not a lot on surface. When we go to the one-step one, so you can see the nitrogen increase to 3 or 4. Also, mostly they are on the surface. It means because we know that on the surface is more active. Also, when go to see the right side part of the picture, you can see to the one step, they have a large amount of the pyrolytic nitrogen they used here. So it means pyrolytic nitrogen sold to the one steps one. Okay, so we also, after the calculation, we also go to some electrochemical properties, like as supercapacitor to see their properties. So when we see that they all have for the one steps one, they have the very good specific capacitance, like over 300. Also, they have the very good reach for the capabilities. But another thing is because from the just last one process, we only focus on the nitrogen. We only focus on the solid charge. I mean, we use the slow heating rate because slow heating rate, the char part is have a high yield. But we know for the biomass pyrolysis, we also can get the liquid part. I mean, is together. It means we can get this one solid part, also for the liquid part together. So we tried the fast pyrolysis, also combined with some catalyst together. So you can see this one shows the ammonia concentration. So you can see with the we have the this means the ammonia utilizes over 50% ammonia can be in the liquid and in the solid char parts. But some, like another parts, we cracking in the high temperature, go to nitrogen and hydrogen. When we go to the nitrogen species in bio oil, you can see with the ammonia past the pyrolysis, we can have a lot of nitrogen contained compounds. So you have over 50% have the nitrogen content. You know, neither in the aquaculture space, also all in the non-aquaculture space. Another nitrogen space in the bio oil. I mean, also with the concentration of ammonia increase, the cycles increased a lot. Also, we go to the char part. You can see we chart the elemental analyzer. You can see that because here you can see the char have nitrogen is about 10%. So is much higher than just now. It's just 3 to 4% in the char part. Also, you have a lot on the surface and in nitrogen on the char surface to show their active side. Okay, so based on also we checked the surface area. Here you can see they still even in the lower amount of activator, lower amount of potassium we used here, we still can get the 1,800 for the micrometers for the cubic meters for the surface area is still have the very high surface area. Also, they have the, here is a micropore, is have a lot of micropore. It can be form a lot of micropore. It means if in the fast pyrolysis part, we have ammonia, we have the potassium hydroxide together, so we can get the goods for the softwares. So we also compare, based on the product, then we want to know how about the mechanism they worked. So we checked the elemental distribution. We also check the like the oxygen containing groups for the chart. So you can see with the potassium increase, you can see the oxygen content here is increased. So it means even you have the activation, your oxygen content increase. Also, for the oxygen species, you can see here the oxygen species all increased with our action. Is if you the temperature, if you increase the too high temperature, it means the oxygen will be even it's a little bit stable. But if you go to the 800 or something, the oxygen content still can be decreased. So quite like the firstly to check the firstly we have nitrogen doping, then we have activation. It means during this process, if you nitrogen doping first, you get activation then after that. It means activation will destroy, will remove our nitrogen group on the surface. But if you activation first, then you have nitrogen doping, because so here with the oxygen content will be a little lower, so it will difficult to use the nitrogen will be ammonia will very difficult to doping on the surface. If we go to the simultaneously nitrogen doping and activation, so we can get the higher nitrogen content, also the higher surface area. So we also try to use the use simulation, so we can see like the mechanism is like this. During the activation, the potassium will will work with the carbon, then we'll have form some oxygen vacancy, like some free radicals. After this oxygen vacancy forms the ammonia, will go to this oxygen vacancy, can go to doping outside the char, and we will have nitrogen drops. So through this process, this way, so we can get the large amount of nitrogen on our char surface. Okay, so this idea, so we developed the method is like the nitrogen containing chemicals and nitrogen char materials. So we also in the have all the solid parts, we can be like the software can go to 2,100 2,000 parameters. For the nitrogen content, it can go to the 10%. Also for the super capacity properties, it can go to the 300 something. So based on this one, so we the liquid nitrogen content and the together. Another issue, because we also think about to increase to produce some biomass through graphene. So this one is synthesize the biomass through the catalytic pyrolysis to get the porous graphic carbons. We added the iron oxide. So the iron, they working through with carbon, they can have some carbon iron carbon, so they get the graphene structures. Also, they have some porous carbons like this. So we tried different temperature, even here the the ET software is not very high, but here you can see the graph analysis, like the graph degree can be go to from the 40% to 100%. We can control the like the graph degree. Then because the graph degree is for the biochar materials, it will be important to the downside, like the electrochemical properties. So also based on that one, we combine some like the melamine together. We can get some nitrogen, iron nitrogen carbon catalyst for this one to the battery or to OR or OER. So here we saw the very good case compared with with industrialized one. So this side you can see based on our carbon like case, we can get good carbon nanotubes on the top. And carbon distribution were goodly on the even the and you can see they on the carbon nanotube here, so they can be in the nature, so it can be accessed carefully for some other systems. Okay, so this is the main work. So because the now is really very hot, it can be for many things.
Professor Hyping,
structure.
my apologies, Professor Hyping, my apologies. I think we are not able to hear you. Sometimes we hear you, sometimes we are unable to hear you. Can you summarize it quickly? Yeah. Okay, you're almost in the summary. Yeah.
Okay.
Yeah, please.
Summarize very quickly because yeah, it's like okay. So from the how to control nitrogen chemicals, also control the quantitatively control our products is still a long way. So we need in the future, we think the green process, also the pore distribution and nitrogen space controlling is very importantly. So this is from the biomass pyrolysis go to this chemical, this materials. So it's have still great challenges. So we need a lot to do. Okay, thank you. Sorry for the poor internet.
Thank you for hyping. I'm sorry that there is a kind of connections problem. Interrupt you a number of times. It's unfortunate. But guys,
sorry.
Guys, if you like to ask questions to Professor Hyping, you can post the questions onto the question box. I'm hoping that she will able to hear and when the quick Q&A session. Yeah. Okay. Let me take over my screen. Okay. Thank you, Professor Hyping.
Thank you.
Now the next talk is on the microwave pyrolysis of waste palm oil shell to value-added products. This will be presented by Professor Farid Nazir Ani. He is a professor at the University of Technology Malaysia, based in Johor. Okay, let me invite Professor Farid to make a presentation. Okay, let me share his screen. Okay. Professor Farid, can you please share your screen, please? Professor Farid, are you there? Yes. Okay. Okay, just a second. Let me. Okay, you're in. Yes. Can you hear me?
I can hear you.
Okay. Yes, we can hear you too. Yeah, go on, sir. Welcome. Can you open your PowerPoint, please?
How to connect the PowerPoint?
You open your PowerPoint file.
Okay, I open already.
Yeah, that's it. And you put in a presentation mode. Yeah.
Okay, it's okay. Eh?
Yeah. You can work. I can see you, but you need to put in the power presentation mode. Yeah.
Okay, okay. So this I've got to put on the presentation mode, eh?
Yes.
Hmm. This one here.
Yes, that's it. Click that one. Yes.
Okay.
Not yet. You did not click yet properly. Can you click, please?
I don't see it. This one here.
Okay. That's right. Yes. Go on, sir. Yeah. Welcome.
Well, I can't see my presentation, PowerPoint.
We are seeing your presentation now.
Yeah, but I can't see my PowerPoint here. Can I speak? Okay, I speak with the PowerPoint, eh?
Yeah, go on.
Okay, so right. Okay, my talk. Can you hear? Can you hear me?
Yes, please. Yes.
Okay, good. Good evening, everybody. Now, what is the present point gone?
You can use you know, the scroll down buttons on the keyboard. Yeah.
Okay. All right, I'll be talking about using microwave technique to pyrolyze biomass. Basically, here I'm talking about oil palm waste, especially palm shell. So we are working on oil palm waste, and how can we, what I call this, produce value-added product. Where is the next one? Right, this is my research talk using microwave processing of biochar and bio-oil, producing adhesive and resin, and how can you use microwave in processing of this biochar into activated carbon. Okay, so we are having a tropical climate here in Malaysia, so we have a lot of green scenery. If you have come to Malaysia, you see a lot of forest, tree, and we also cultivate palm, oil palm for our needs, food as well as other material, and also biochemical application. So oil palm as bioresource, so this renewable source of food as well as what call this other product. We can use for energy also. So what basically happened is the palm oil fruit bunches being taken from the plantation into the mill, and this mill is self-sustainable. It's all run by the we have excess energy from the biomass, so it's situated very far from the city, and the mill is inside the plantation. So basically, palm oil in Malaysia is grown for the oil, and also the oil comes from the mesocarp and the seed. Right, as what this Prof. Yang talked, we are talking about carbon recycling. Okay, so we have a lot of carbon waste, carbonaceous waste. So we can recycle this by physical recycling, biochemical recycling, thermal recycling. So what I mean by this physical is, you know, we just do mechanical recycling without what I call is changing the structure of the carbon material. And thermal recycling is like combustion, combustion of the biomass. We produce heat, and of course, in the end, we produce CO2. CO2 being taken by the plant. So this is what carbon recycling about. Right, this is important how we utilize bioresource. Okay, so we have the higher value product up there and the lower value product at the bottom. So as much as possible, we go to the high end for higher value product like pharmaceutical, cosmetic, etc. So this is extraction of chemical from this oil or biomass. And the last end is to burn it. So this is the end, low end value. The waste you can just produce heat or energy. And in between you can use as food, bioplastic, and pulp chemicals, etc. Okay, so this is a carbon cycle. We have the plantation, taken CO2 taken by the plant. The plant produce oil. Oil can also produce biofuel, biodiesel, ethanol, bioethanol. But it's better to use the oil as food. So our priority is use the food and also energy and some other products. And then the biomass also, with some technology, we can convert into biofuel. In our palm mill, the effluent are producing biogas, and this biogas being burned in what we call this engine or the boiler or some other bio CNG. Okay, so this is a typical background. Is the plantation, which covers a lot in Malaysia. And basically, this palm trees, they have this is a mass balance. If we have taken the fresh fruit bunches, let's say 30 ton, so we send the bunches, fresh fruit bunches to the mill, and this is the breakdown of the fraction in the mill. So what we have here, of course, we produce the palm oil and palm kernel. These two are used for what I call this producing palm oil and palm kernel oil. The rest are all being waste. So we have a lot of empty fruit bunches, shell, the palm shell, the palm fiber, and the effluent. So these waste are all energy. We can turn into energy. It's more than sufficient to run the mill. Or empty fruit bunches and the fiber is sufficient to run the mill. So the shell is a bit hard because it will cause what I call it black smoke. So we preferably not to run on shell. So this shell can be used for other purpose. Okay, so the typical, if you go under the trees, you see all this what I call this plant being planted in a what I call this proper manner. Okay, so these are the fruit. Okay, the fruit basically is in between the frond. This is the frond and the stem. So we can just, the farmer will chop this fruit and then being taken out of the plantation. So out of plantation using lorry, and then this being taken to the mill. So this is a mill yard where they just dump into the mill yard every day. So every day, because this palm fruit doesn't have a season. That's all the year round. Is basically the fruit is there. Only the high end or the low end, but basically you have this what we call this palm fruit available year round. Okay, this is a typical huge amount of what we call this fresh fruit bunches. Okay, so this is taken to the mill yard and waiting for processing. So basically, if you taken one of the fruitlet, it will look like this. Okay, so basically you have the oil. The oil comes from this part here, this endocarp. So basically, what they have to do is they have to cook the fruit, sterilize the fruit, and then press, and the oil comes from this endocarp. And then we have this palm shell here and the palm kernel. So this palm kernel, they produce palm kernel oil. The palm oil comes from this side here. So in this endocarp, we have this fiber. Okay, so the fiber is there. After pressing the oil, there is a fiber, and we left with the nut. Inside the nut is a kernel. So this is after the fruitlet has been removed. So what you have, the empty bunch. So these are the empty bunch that need to get rid from the mill. So this is partly used for the mill to run the boiler. Okay, to run the boiler, we have a steam turbine to generate the power to run the process, and partly is sent to the plantation just to act as mulch. So just every day is you have this kind of thing happen, and this is the operation of the mill. Okay, so this is what we call this like pump shell. This is a pump shell. Pump shell being what we call this separate from the fiber. So a lot of pump shell and a lot of fiber. So this fiber after the press, and they also have a lot of this, and these are being used to fed in the boiler. So basically, this biomass, they are high moisture content, low bulk density, and also low calorific value is about 20, around 18 to 20, half of that of coal. Half of that of coal. So the waste size is consistent and not much sulfur. Okay, so you can see from here we have the cellulose, semicellulose, and lignin. Palm shell constitute a high amount of lignin. So this is which cause black smoke, and better to they use fiber and also empty fruit bunch for their installation for the combustion in the boiler. Okay, so this is the elemental analysis, proximate analysis, and their calorific value is about 2019 megajoule per kilogram. Okay, so the ash content, the high water content is about 77% water content, and carbon content about 50%. Right. So what I did so far on my research on pyrolysis is that, of course, we characterize, and then we do some pre-treatment. What I mean pre-treatment is by slicing, grinding, and then we use fast pyrolysis technique to convert into this three. We have the bio oil, we have the biochar, and we have the gas. So just like Prof. Young also mentioned, he got a very huge vertical reactor. Ours is a small reactor, but we produce bio oil and also biochar and gas. So basically, a gas we just flare off, we just remove, and the biochar we do some work on active carbon molecular storage, also this microwave adsorbent, carbon electrode and carbon supercapacitor. The bio oil, okay, you can use it as upgrading to produce high-grade fuel, but of course it's quite expensive because you use catalyst. But what we go to this route to produce adhesive. Okay, so this is our way to produce resin and adhesive. So the heat. Okay, in the medium of heat transfer for pyrolysis, there are many methods. Okay, and earlier we worked on electrical heating using conventional heater, and also like Prof. Young, they used to burn the char and the gas. You can use the heat from the waste of the plant to get the heat. You can use thermal oil and molten salt. Later on, we use microwave heating. There are some people working on a solar heating technique. Why microwave heating? It reduces reaction time very fast, because you need a fast pyrolysis, not a slow pyrolysis. So we are in fast pyrolysis. We produce more oil, bio oil. reduce site reaction, increase yield, improve reproducibility. Right, the microwave heating advantage. Okay, the microwave compared to conventional microwave heat from the center of the sample, as compared to conventional electrical heating is from the outer to the inside. So that's the difference. And the frequency that we are allowed to use is the microwave frequency, 2450 megahertz. So these are two, but these are the common heating frequency used in domestic microwave oven. So basically it's a rapid, selective, and also volumetric heating. Right, so this is our a small rig that we have. We have a microwave. Inside here we have, of course, we have the what we call this our reactor, and we produce the water vapor into this fractionation. Fractionate. You can fractionate whatever you want. You can control the what we call this the temperature here. So basically, there are basically four design. For design, one is the top removal, the side removal, the bottom removal, and one is the what is a fixed, no closed system. It's a closed. So basically, you have these four design, and you can collect your bio oil here, and also your gas coming out there. So this is just like Prof. Young fractionation tower. So we have our own small tower here. Okay, so this is the bottom design. So we have a stirrer there. So this is our quartz reactor here, and we have a chiller here, and also we control the chill water, and we produce the oil at the bottom there, and of course we remove the gas. Okay, so we have the controller of the temperature of our reactor. So basically, the heating profile is like this. If we use activated carbon with our biomass, it will help in enhance the heating rate. So this profile here, without this one, the light green is without mixing with activated carbon, and the dark one, if you mix with activated carbon, it will enhance the what we call this heating rate. So basically, this carbon, they can also use as absorbent, microwave absorbent. So basically, this is the typical fast pyrolysis. You have more yield, bio oil yield, and less gas and char. So depending on the temperature, how you control the reactor. This is typical bio oil. It's dark brown color. So what we have here is EFB means empty fruit bunches. I told you that we have a lot of these big bunches. So I think some people from Canada, from Holland, from Korea also, interested in doing this pyrolysis, and we use microwave here, and we can see, we can test their phenolic compound, phenol and phenolic compound, and using microwave, because it's a selective heating, it produces higher what we call this phenol and phenolic compound. So maybe it can reach to up to 90%. So you can look from our paper. Okay, so phenol compound in palm shell. This is palm shell. Of course, in palm shell we have high lignin. Compared with fixed bed, fluidized bed, and microwave, this palm shell give higher amount of phenol and phenolic resin, phenolic compound. Okay, so what we have is the palm shell. We have the pyrolysis oil. We convert into palm phenol. Okay, the technique here is already I think well established. You can just get from the journal, and and then you can produce from this palm phenol to palm adhesive, and also resin. Okay, so what is this? Okay, this biochar. So basically, this what I call is the resin is much cheaper than what I call this petroleum based. So we have make a study is much cheaper, and the strength is comparable. Now go to this biochar. Okay, we also get this what I call this biochar, and looking at the conventional electrical heating and also microwave heating, we found that the conventional heating have a higher what I call this surface area compared with microwave heating. Okay, so here you can see what I call this producing activated carbon using microwave at different power level and their surface area. So at low power level, using chemical activated, giving high surface area. So it's much faster and also giving higher surface area compared with physical activated carbon. Physical processing. Now, also use biochar. You can also what I call this make this bracket. So this is the end, the lowest end. Because we have a lot of what I call this carbon resource. One way to use this what I call this biochar, you just mix with the clay and dry it, and you can use for cooking. I think I missed some slide which is not coming out from my presentation. I think this is the last conclusion. So sorry. So my conclusion: palm cultivation holds an important asset for food and other application from its oil and biomass. The choice to use biomass for fuel, power, and biomaterial depend on various factors such as availability, policy, cost of biomass, capital cost of processing equipment, infrastructure, and market for alternative energy and material. The application of microwave assisted processing of biomass, biochar, activated carbon, and its biodiesel show a great potential in a sustainable integrated processing plant. I think that's all I have. Thank you very much. Okay.
Thank you very much, Professor Farid. Guys, it's an interesting presentation on the palm oil, in the palm oil biomass, and I'm hoping that you find it useful. Please, if you'd like to ask some questions to the Professor Farid, please post questions in the question box. We discuss at the end of the session. When you ask the question, please mention you're asking to which speaker, okay, so that easy for them also to follow the question. Okay. Thank you. Let me share please wait, sir. Now we have question and answer session as well. Okay. Let's finish the third presentation of this session. Let me take over my screen. Okay. Okay. The next presentation is on the co-pyrolysis of waste biomass and plastics into renewable fuel. The presentation will be given by Professor Mohanty, Indian Institute of Technology, Guwahati, India. Let me brief about Professor Mohanty. Just a second. Oops. Okay. He has obtained his PhD degree in chemical engineering from IIT Kharagpur and is currently working as a professor of chemical engineering at IIT Guwahati. His key research areas are in biofuels, biological waste treatment, membrane technology, microalgae, biorefinery, and biomass pyrolysis. He has published more than 150 research papers in many international journals, edited book on the membrane technology and applications. He is also the Associate Director of the Journal of Chemistry, Associate of the Journal of Institute of Engineers, and associate of the Research Journal of Environmental Science, review editor for the Frontiers in Bioenergy and Biofuel, and editorial board of number of various journals. And he is a fellow of Royal Society of Chemistry UK, fellow of Institute of Engineers, and a life member of Institute of Chemical Engineers. Currently, he is holding a post head of the department at the head of the Center for Energy at IIT Guwahati. Guys, you see, he's taking lots of activity, lot of roles, a lot of publishing, and I'm sure you find this presentation very much useful. And let me ask Professor Mohanty to share his screen. Okay, yes, okay. Okay.
Is it fine now?
Yes, good. Yeah.
My slides are visible?
Visible, yes.
Okay. So shall I go ahead?
Yes.
Yeah. Thanks, Param, for the introduction. And it's a pleasure again giving the talk in the second PYRO ASIA conference. The title of my presentation is Co-Pyrolysis of Waste Biomass and Plastic into Renewable Fuel. So, as you know that we can, there is a lot of talk about wastes. Okay. Now, basically two types of wastes, fossil-based wastes and then bio-based wastes. So, inside this fossil-based waste, something that comes and takes a major chunk of it is the plastic waste, which we use on our daily life. And of course, many of that are getting discarded without any proper treatment. So higher amounts of wastes are also generated after harvesting and post-processing of the crops. So these are basically agri-based wastes. So that need to be disposed properly. There is a big problem of the stubble burning and all in the northern states of Haryana and Punjab, for which Delhi also suffers a lot during the winters. Every year this happens. Now government is also giving a lot of emphasis on how do you manage stubble. So bio-based waste upon proper conversion has the potential to produce renewable fuels. Therefore, the proper management of both plastic waste and bio-based waste is essential for environmental sustainability as well as the economic growth of any country. So if you look at this projected waste generation by the region, that's in million tons per year, you can see that East Asia and the Pacific probably is generating more. I'm talking, of course, I'm talking about the solid waste. Okay, and South Asia, so they are the topmost. If you talk about the 2050 projection, brown color, deep brown color, this one graphs, you can see that. And if you look here in the global waste composition, in the past, it is in percentage, you can see that this one 44% is food and green wastes, right? So most of the bio-based waste comes under this, a huge amount. And then plastic, almost 12%. So today my focus talk of this one, my presentation is focused on these two waste, addressing how do we actually take care of both these wastes. One is the bio-based waste, another is the plastic waste. So if you look at the global treatment and disposal of the waste, again in percentage, you can see that there are many different technologies. So starting from the sanitary landfill, okay, sometimes also there is a provision of landfill gas collection. Otherwise, only there is no such provision also. Most of them, most of the time, there is no such provision. It's only the landfill. Then we have composting, incineration, open dumping. Few is getting recycled. You will see only 13.5, and this is what actually we want. More and more of recycling, and unspecified landfilling is also there. Controlled landfilling results in some value addition. Okay, so yeah, coming to the plastic. So you can just understand this image. Everybody, we are all aware of this plastics. PET. Okay, every second we throw away about 1,500 bottles. It's a global figure. Okay, so what is the solution? And over 30 billion liters of bottled water is consumed annually. So we are looking for a solution. Today morning, one of our speaker was talking about microplastics. Now, these plastics, when they are degrading under the sun and getting inside to the sea, are getting degraded years by years together. Okay, it's not that today we dump it and tomorrow it's get degraded. It's not like that. Okay, so it takes years together to degrade and form microplastics. Now we are talking about nanoplastics also. Okay, so this microplastic, nanoplastic business has become a serious issue. My group also works working on this particular topic of microplastic. So we have, I'm just telling you that we have scanned a whole lot of salts, edible salts, the sodium chloride, okay, of various brands, non-brands, everything. And you don't believe that every single salt has certain microplastic content present. So basically they are coming from the source of the sea, and the sea and the plastics which we have thrown to the sea, years together they have degraded, and they are getting resulted in microplastics. Microplastic has started coming in air also. It is becoming a big menace. Okay, so we need to take care of this plastic business. So I'll straight away, this is PYRO Asia conference, so obviously I'll straight away go focused about the talk directly about the co-pyrolysis without introducing anything about pyrolysis and all these things. So it's a simple and safe production process for high quality fuels, since it does not bring in high pressure hydrogenation. So hydrogen transfer may also be involved in the co-pyrolysis under ambient pressure conditions. The synthetic plastics are typically organic polymers derived mainly from the petroleum products with high carbon and hydrogen contents, having little or no oxygen, and also offer a comparable high heating value to the conventional fossil fuels, just as such as our diesel and gasoline. Now, the co-pyrolysis process of biomass and plastic has been reported as an effective upgrading method that will not only increase the quantity of the oil produced, that means the yield, okay, but also improve its quality in terms of high calorific value, in terms of fuel properties enhancement. So I'll present you a few of the results which my students have carried out, okay, during their graduation work. So this is a simple fixed bed reactor that we have used for the co-pyrolysis process, okay, and we have used non-edible seeds. Now let me tell you a little about this non-edible seeds. Some of them are, and these seeds, whatever I have shown here, Mohua, Karanja, Niger. So these are non-edible oil seeds. Okay. Now all seeds do not contain oil, and these seeds contain oil, and they are non-edible. So we have used it as it is, without removing the oil or without extracting the oil. Right. So we have mixed them with the waste polystyrene. So these are the representative images you can see. It's a simple semi-batch reactor. The feed size is less than 1 mm. Heating rate was kept constant, though in this particular presentation I'm just showing you one heating rate results. There are many other things also, other heating rates. This is 25 degrees centigrade per minute, and there are 4 different ratios that we have used and studied. 1:1 ratio of the biomass to waste polystyrene, 2:1, 4:1, and 8:1. And temperature is 550 for Karanja, Niger, and 525 for the Mohua seed. And this temperature what we have got is basically from the thermal pyrolysis of the singular individual biomass. So this is the TGA and composition and analysis. So you can see that you will have a flat profile. Of course, the red one is for the waste polystyrene, and other biomasses, they are all mostly in the same range of degradation. So the carbon percentage is higher, 91.5%, hydrogen is 8.5, moisture 0.5, and volatile is 99.5%. Right. So let me try to explain you that what has happened and what has changed when we added waste polystyrene to the biomass, and we have carried out the co-pyrolysis. So let us look at this result. So these are the three different types of feed that I am talking about. Mohua waste pyrolyzed with the waste polystyrene, then Karanja with the waste polystyrene, and of course again Niger with the waste polystyrene. The three seeds and the plastic. And you can see in the second column this talks about the yields. So I'll talk about only the oil yield, because our major emphasis and focus of the work in our lab was to generate, to have a better yield and better fuel properties of the bio oil or the pyrolytic oil. Okay, now here you can see the last column. This is the thermal pyrolysis results. Okay, that means this is only the biomass. There is no plastic has been added and no catalyst has also been added. And in today's talk, I'm not discussing about the catalytic co-pyrolysis, though we have done a lot of work on that also. So let us try to understand that how the oil, what has happened actually when we go for co-pyrolysis. So this is 40.71, the percentage, weight percentage is the yield for the thermal pyrolysis when you for the only the Mohua seed. Now when we added 1:1 waste polystyrene, the average oil yield has become 59.8, so close to 60%, almost 20 weight percentage increase. Now the same result you can see, the same thing you can see for the Karanja and Niger also, 32.9 to 60, 33.39 to 61.31, right? So this clearly shows, and if you closely look at the table, this is 1:1 ratio. So when we increase the biomass, kept the polystyrene constant. Okay, there are some certain changes, of course. Okay, so in terms of calorific value and fuel properties, this 2:1 has given us better properties. Okay, with a little compromise on the oil yield, but that's not a big thing. Okay, so 53, 59, not a very significant difference in terms of yield percentage. Okay, when we went for adding more biomass, keeping the polystyrene constant, 4:1 is 8:1, the calorific, the oil yield has decreased. Now, why the oil yield is more in 1:1? That's because of the huge amount of the polystyrene, which immediately decomposed to give us different types of hydrocarbons. Okay, so I'm not discussing about the one thing what we have done here. If you see most of the works, they report actually oil which takes into account the aqueous phase. Now please note here that whatever I am talking here, we have actually taken out the aqueous phase out of the pyrolytic oil or the bio oil, and oil whatever I am showing, it is only the hydrocarbon rich portion. The aqueous part has been presented separately. So if you look at that, then the total yield is extremely high, close to 82%. So now I'll talk about this fuel properties, what is happening to the fuel properties when we have added the waste polystyrene, right? So again, the properties which are in blue, light blue color, so these are thermal properties. That means they are only biomass, right? So the second row is the biomass for the Mohua. Here again the Karanja thermal, this one, and then the Niger thermal is presented. Now let us concentrate on the calorific value. That is because if we think about bio oil to be used towards some sort of combustion process. Okay, so the calorific value is the most important thing that we should look for. And of course, there are other fuel properties like viscosity, pH, and water content, right? So if you compare the thermal and co-pyrolysis, that means only biomass and then biomass plus polystyrene, you can see that there is an increase in the calorific value at 2:1 ratio. Now this is what I was just mentioning you that let me go back here. Okay, if you see here that 1:1 has given us better result in terms of the oil yield for all the biomass and waste polystyrene ratio. However, when I talk about calorific value, we have always seen that 2:1 has given us higher calorific value. Okay, now these are some interesting results, but what it is happening exactly and why it is there, that mechanism part is still not, still we are trying to find out, but it is still understood. As you know that biomass pyrolysis is a very complex process. There are hundreds of reactions, sub-reactions that happen simultaneously. So predicting the mechanism is extremely difficult. We are still working on some sort of theoretical analysis to understand actually what is happening. So hopefully we'll try to give you a better analysis of actually why this is happening, maybe sometime in the future. Okay, so again, if you look at this viscosity, you can see that viscosity has drastically reduced from 33 to 3 point in the 1:1, 5.21 in the 2:1 ratio. Okay, now again, when you increase the biomass, again the viscosity has started coming back to its original figure. Okay, so water content is almost negligible or almost zero. Okay, not detectable, or I can say the below detectable level for the instrument what we have used here. Okay, for the copyrolytic oil. And okay, so let me go back to then another analysis, which is called the carbon residue test. Now this is a part of the bomb calorimeter. Now we try to understand actually what is the unburned carbon left out once we burn it. Okay, burn the copyrolytic oil. So you can see that for the Mahua Karanjanizer, all the three copyrolytic oil, 1:1, it is 3%, almost same 3% for all the biomass. And when you increase to 2.1%, we get a better result in terms of the carbon residue test. However, it is so less when we talk about only biomass. Okay, so hardly any carbon is left, and whatever the biochar little is there, that also been taken out, and then we have gone for the fuel property testing. That's filtered out properly. Okay, so this is also very important when we talk about basically combustion properties. Now this is an overall GCMS comparison, and we try to plot it like this, combining hundreds and hundreds of different types of compounds into their particular groups, like alkane, alkene, amide, aromatic, acid, ester, nitrile, and not groupable to something, we call it others. So you can see that in terms of Niger and this one, our Mohua as well as Karanja, you will see that the aromatic contents and the alkene contents are higher. Okay, ester is very much prominent in case of the Mohua copyrolytic oil, and as I already told you that why actually somewhere alkene is more, somewhere ester is more, that basic understanding is still missing. So that means I mean to say that fundamental understanding, because unless until you predict the reaction, what is happening and what has happened, it is extremely difficult to tell that which component has converted to ester. So we can tell that okay, this acid has converted to ester, that has probably, this is all probable. Okay, 100% confidence you cannot say. So so for that you can you'll appreciate that few people are working on this particular area to give us a detailed insight of actual pyrolysis mechanism. So what you do basically, what they do and what we also do is basically to take individual components. Okay, suppose cellulose, hemicellulose, lignin. So these are the major components of the biomass, any biomass. Now these seeds which we have taken here, the non-edible seeds, they have huge amount of the volatile matters, because the oil is still remain inside that. We have dried it and we have used it. Since these are waste seeds and their oil do not have so much of commercial value except for certain applications of lighting lamps and all these things, so it is better that we have to use it in as a whole without extracting the oil. Okay, so then we have carried out so many other analysis. I'm not going to show everything here. So this is a representation of the DSC and the difference in scanning calorimetry. Okay, so the DSC analysis of copyrolysis oil at 2:1 ratio is compared with the thermal copyrolytic oil. Right, so the red one you can see is the Karanja copyrolytic oil, and the black one here in the top one is the thermal only Karanja. That means no, there is no plastic in that. Similarly, here it is the for the Niger also. So what we observe is that since both the crystallization peaks were in the high temperature region, it can be predicted that the amount of saturated hydrocarbons and ester were comparatively more. And that is also what we have seen from here. Okay, for the Niger, you can see the ester is higher. For Karanja, also the ester is it's a good amount of ester. Okay, compared to other alkane and alkene and acids. And the peaks from the co-pyrolytic of Niger, you can see from here, the polystyrene is also agreement in the Karanja, the same thing. Mostly it is same. Okay, we have a better peak here in case of the Niger, distinct peaks. So then we carried out something interesting that many people ask, okay, bio-oil, pyrolysis oil, everything is fine. You want to use it in engine. So what about the stability? So we carried out now actually more rigorous work is going on for this particular work, topic. This is what was being done by one of my PhD student, Dr. Sarangi. So he tried to find out the stability analysis of the Mohua co-pyrolytic oil. I'm only presenting Mohua co-pyrolytic oil here. Okay, so let us try to understand what is happening when I'm aging it. So these are the results. Aging time 0, that the day we produced it. Okay, viscosity, pH, density, calorific value, these 4 properties we have measured. So on the day 20, after 20 days of storing it, okay, the room temperature storing, nothing is being added, and no special, it is only closed, okay, in a proper vessel, airtight vessel, and sealed. Right now on the 28th day, you can see that the viscosity is increased. On day 30, viscosity still increased. Day 40, viscosity still increased. Okay, now the viscosity is the measure parameter that is getting increased with the aging. Some sort of secondary reactions are still going on when you store it. Okay, pH is more or less okay, but on the day 4 pH, there is a slight drop in pH from almost 6 to 5.4. Density also little drop. Now, it's a nice thing is that up to 20 days, there is hardly any change in the calorific value. Okay, so 20 days of storing, though viscosity has increased, but the calorific value remains more or less intact. But when you go beyond 30 and 40 days, the calorific value decreases. So stability is certainly an issue. Okay, need to be worked more on that. So I'll try to conclude whatever I have just shown you. Most of my works, my group's work is focused on the non-edible seeds, and I already told you why, because of the higher extractive content, and these are out of the food chain, so no question of any food versus feed problem. Non-edible oil seeds are one of the suitable raw materials for the bio-oil production due to higher extractive content, higher volatiles, and low moisture content. Among the various seed to waste polystyrene ratio studied, co-pyrolysis at 2:1 ratio was suitable to produce higher calorific value pyrolytic oil and low carbon residue. The viscosity was also reduced significantly compared to the thermal pyrolytic oil. Co-pyrolysis resulted in enhancing yield as well as the fuel properties of the pyrolytic oils. Compared to thermal pyrolysis, co-pyrolysis with waste polystyrene was proved to be better in terms of reducing the viscosity and increasing the calorific value of the pyrolytic oils. Further GCMS analysis confirmed that the use of catalyst has resulted in the reduction of the oxygenated compounds with an increase in alcohol and aldehydes in co-pyrolytic oil. So this work concludes that co-pyrolysis can be an important tool or technique towards proper waste management of both the waste biomass as well as the waste plastics. So the data that I presented belongs to 2 of these papers produced in published in Fuel and Waste Management, and this is my research team. I'd like to thank all of them, those who are work for this particular presentation what we have carried out today, and thanks to the organizers of PYRO ASIA. Of course, I am also an organizer myself, right? So thanks to Param and thanks to Dr. Suchitra Gopakumar. Thanks to all other speakers and listeners, and also thanks to Dr. Karthik. And thank you very much. So this is a snapshot of our beautiful campus. So we do also host so many conferences, and I also look forward to host PYRO ASIA sometime down 2-3 years down. I'll be very happy to host you that time. Of course, we don't know when it will happen, but of course it will happen definitely, maybe after 2 years or something like that. So thank you very much for your kind attention.
Thank you very much, Dr. Mohanty. And guys, it's a very, very interesting presentation, co-pyrolysis of waste biomass and plastics. Now it's time for the Q&A session. Let me take over my screen. Yes, and I request all this, the speakers of this session to please be online, okay, with your webcams on, so that I can show you some questions what people asked. Okay, Professor Hyping, are you there?
Yes, I'm here.
Okay.
Should I share my screen?
Can you show your screen, please? Yeah. No, your
video.
Yeah, webcam. Yeah.
Yes.
Okay. Okay, I have some questions already. I'll put them onto the screen so that you can answer one by one. Let's go with the Professor Hyping. Can you see the screen?
Yes.
Okay. Are you there?
Yes.
Okay. Yeah. Would you like to answer?
So question is the first one?
Yes, that's yours. Yeah.
It seems not a question, it seems a comment. Because yes, for the moving bed one is the scale is not very large. Normally now we are limited to like 1 ton per hour. So I think it's okay for the farmer, for the local farmer, like 1 ton, one village, 2 village, so you can have 1 reactor, then to go to the solid carbon. Also the gas you can, for cooking, for around the site for the resident. So it's possible. It's now we already have some commercialization to the reactor. That one is also for the firstly for the gas fuel for local farmers, and the solar charge is for for the normally is for barbecue, because barbecue char is expensive one. But if we have, if you will use water, use some steam or CO2 to active, you can have other solvent, you can have active carbon. So this one is can be used maybe for the for the filter, for the water profile. Yes.
Okay.
So it's okay now.
Yes, thank you. Okay, Professor Farid, the second question is to you. Yes, okay, please.
Okay, so I told before the mill produce 4 kind of waste. We have the fiber, the oil come from the fiber, and the fiber is normally used in the combustion, in the boiler. Okay, so basically this is a good fuel. You will not produce much smoke. And then we have the what we call this effluent. Okay, the effluent now is regulate that you have to produce biogas. So biogas being used also in the boiler or some other industry nearby, where you can use clean fuel, gas fuel. And then we have the empty fruit bunch. Yeah, empty fruit bunch also being used in the boiler. Okay, together co-firing with the fiber, and plenty of empty fruit bunch. Some of them being sent into the the plantation as a mulch or making what you call this fertilizer, some sort like, you know, they just keep it and then let it rot and then become what you call this fertilizer, some sort of fertilizer. And the last one is the palm shell. The palm shell is this thing that they don't like to use in the combustion process because of the smoke. They produce a lot of smoke. So this one, people are taking making what they call this some other kind of product, maybe active carbon, biochar, whatever. I'm not familiar with this what they call this this industry, but they remove from the what they call this. They are not used for combustion, but they use for other purpose, for active carbon and so on. For making briquette also can be used for making briquette. So I think so that's my answer.
Okay, thank you, Professor Farid. Okay, next slide. Okay, it's for Dr. Mohanty.
Yeah. What are the factors taken into consideration before selecting any feedstock for co-pyrolysis? Okay, fine. So first, what you want to do by co-pyrolysis? The first major important thing is that what is your intended product? Are you looking for oil? Are you looking for biochar? So based upon that, your feedstock selection will vary. Correct. So let me come back to my presentation where I have presented feedstocks, whatever it is. The sole aim is to produce a high quality bio oil or pyrolytic oil or pyrolysis oil. Many people call it in different names, right? So and how do you choose it? So when you talk about waste plastics, as you know that waste plastic is having huge hydrocarbon content. Okay, so the addition of waste plastic, even in slight percentage, 10%, 5% to something like that, also has resulted in beautiful result, enhancing the fuel properties like calorific value, because more hydrocarbons has been added to that, right? And my lab usually actually focusing on the non-edible seeds. Now I have already told you, again I'll repeat that, why I have chosen non-edible oil seeds, because first they are out of the food versus feed business. Most of them are waste, okay, though some of their oil is being traditionally used to light lamps by people, okay, in villages. Now nobody is using it. And it has huge extractive contents. Now that amount of extractive is actually getting, when it is getting pyrolyzed, are giving us good oil yield. Okay, so I'll go for the generally co-pyrolysis is reported for types of feedstock like waste polystyrene and any seed. How many types of feedstock we can mix before doing co-pyrolysis? Oh, this is a very good question.
Dr.
Okay,
Mohanty,
so whatever.
Dr. Mohanty,
yes, yes.
You have quite a number of questions in line for you, so try to please to be brief and concise so you can address all the questions.
Sure. Okay, this is a good question. So how many different types of feedstock? There is no thumb rule like that. It depends upon, actually you have to do some experiment to find out actually what feedstock is producing and what the yield and the oil. I'm talking about oil. Okay, I'm not focusing my answers on biochar, right? That's a different story. So can we go to the next one?
Yes.
Which solvent did you use for GCMS analysis? Or that I am not able to, I'm sorry, I cannot answer this. Okay, because I don't remember. This is being outsourced. Our GCMS was not done and we outsourced, and I am sorry, I cannot answer right now, but I'll come back to you maybe sometime tomorrow during the panel discussion. Okay, suppose I have feedstock to do co-pyrolysis for which earlier details are not available. How to decide the feed size, heating rate? That's okay. So feed size, heating rate, temperature, everything you have to carry out the thermal pyrolysis experiment. That means only biomass. because your plastics will degrade much faster and much lower temperature zone. Okay, so you have to optimize the biomass pyrolysis, carry out at that temperature. That's what we did. Okay, anything else?
Okay, I have a few more. Let me put that onto the screen, please wait.
Sure.
I'd like to answer all the questions as much as possible, as quickly as possible as well, so that everybody can answer. Yeah, thanks.
Is it possible to upgrade bio-oil using melt form of plastic separately? I didn't understand this. Melt. I think probably the question is asking about only plastic. Okay, only plastic is also available, but the aim is to use biomass, waste biomass, so that the quality of the fuel will be also good. Okay, water content reduce. It is known that burning of plastic produce PCBs and dioxins. I am wondering if these pollutants are produced during co-pyrolysis of. Yes, very nice question. Good. Okay, so we are actually doing this. And thank you for pointing out again. We are trying to do this because there are two things. When you pyrolyze, the vapor is coming, part of it is getting condensed, part of it is not getting condensed. Whatever is not getting condensed, we have also analyzed it. Carbon monoxide, carbon dioxide, a very minor quantity of hydrogen, and there are so many other gases. But we have not noticed dioxins and all these things, because the reason is that the amount of polystyrene that we have used is very less. Why water yield? Is it possible to upgrade? Okay, no. Can you please share some details on the size of these PY studies? Any reason why 2:1 gives better result than 1:1? No, 2:1 has given us better result in terms of fuel properties like calorific value, but 1:1 has given us better yield, higher yield, 59-60, almost that. The reason that more hydrocarbons have been added. Now fuel properties has been significantly enhanced. I don't say significantly. 41 to 43 is that range, right? It's not significant, but there is a enhancement. As I told you, exact reason it is very difficult unless until you predict the reaction mechanism. So I cannot give a straight answer about that. Is it possible to upgrade bio-oil using melt form from plastic? Yes, it is possible. But upgrade bio-oil means you have to go for some hydro deoxygenation type of work. Okay, using catalyst. Okay. Thank you.
I have some more questions.
Anything else is there?
Still there? Please wait.
Yes, sure.
Let me put in here.
No problem. No problem. Heating value of PY oil is generally reduced by the presence of oxygenates. Is it possible to get PY oil of reduced oxygenates? Yes. Yes, of course it is possible. So you have to do some process optimization. You have to do some further upgradation. Okay, it is possible. So that's what I was talking now. Hydro deoxygenation you have to do. What was responsible for the increase of the bio? Yes, this we are still studying. So when we store it up to after 20 days, okay, 10 days, viscosity has increased. Now some secondary reactions still happening, even if in the ambient temperature when we are storing. What is that? It is very difficult to tell right now. But our understanding is that some secondary cracking reaction is happening without the presence of any catalyst and all. Okay, though it has been removed, we have whatever today I presented is not catalyst related. What are the possible control measures for bio-oil? See, to make the oil stable, there are additives available. Okay, all these additives are also added to diesel, petrol, and your gasoline, everything. You know that, to make it more stable. Now we have not added anything. Whatever I have presented is the first-hand information about the stability of this co-pyrolytic oil. We are working more into that. Okay, so we are very hopeful that if you go for a secondary bio-oil upgradation, okay, what is that I cannot say right now. We are doing it. Okay, then the stability issue will come down. Okay, the next is for Dr. Farid.
Yeah, Dr. Farid, it's yours now.
Hello?
Yes.
You're talking about the binding agent. All right. When you're talking about binding agent, I mean, you are talking about the cost of briquettes. So the cheapest cost is to use sustainable material like clay clay the best. But if you want, you can use also what I call starch or other binder, which is costly. But what we did is using clay and bind with the biochar to produce and then mold to this briquette. The other one is how much water content in palm oil. When we are talking about palm oil, in the commercial palm oil, it should be no water. There should be no water inside the oil. So in the processing of the meal, they make sure that the water is removed. So then you can you can have a longer shelf life. I hope I answered the question.
Okay. Dr. Mohanty, it's yours now.
Yes. Okay. How to trade off between yield and heating value for the same ratios of the feedstock in okay, so yield and calorific value are of course not directly related to each other. So if you go for if my results, if you look at that closely, you will see that the yield is higher in 1:1 because of more amount of plastics into that, which are resulted into hydrocarbons directly. Now, but when I'll definitely tell that our results at 2:1 is best, though we compromise little on the yield from 59 and 60 to 53. The reason is that when this oil will be burnt for some purpose, okay, in some engine, so calorific value will be more of importance rather than that of the yield. Yield is a commercial importance thing, right? So calorific value is a technical importance thing. So we need to concentrate more on the calorific value rather than this one. So you need to choose your processes and process parameters like in such a way that you get a better fuel properties. Okay.
Okay. I think we end the question Q&A session here. Thank you very much. Dr. Suchitra, I'd like to add a few comments here.
Yeah. Thank you, Professor Yang and Professor Farid and Professor Mohanty for exciting talks. Though Professor Yang, we had some interruptions, we were able to see your one-ton pyrolysis plant and also to know more about nitrogen and pyrolysis. Professor Yang, are you still here? I think she is not here. Professor Varid, can I ask you, can you tell us
The last was another clear.
Hello, Professor Yang? Professor
Yes.
Yang? Yeah. Okay. Can we know about when you did the nitrogen pyrolysis?
Okay.
Can we know the more about bio oil? What are the studies have you done with the bio oil?
For the first pyrolysis, yes, with ammonia, yes, it have bio oil.
Yes, and the bio oil, you mentioned that there are like more you have pyridine and other chemicals, right?
Yes, because a lot of nitrogen is inside. We have pyridine, pyro is all nitrogen content. Also, they have large amount of phenol.
Okay, okay, phenol also. So the heat, how about the heating value about as compared to normal inert atmosphere?
You mean for the because it have the alpha nitrogen inside, we are not supposed to use as a liquid fuel. So we mostly that's why is we want to use for the chemical to like the waste separation the pyridine, the nitrogen contained chemicals.
Okay.
So this is the point, because it have nitrogen, you will have the for fuel is you combusted, you have NOx will evolve out. So this is the concern.
Yes. Okay.
Yeah. For the without. Oh, okay. Yeah.
Okay. Thank you, Professor Yang. It was really exciting to see the plant and everything.
Thank you.
Okay, thank you.
Thank you.
Professor Farid, can you tell us, because we saw your microwave pyrolysis, and we are doing with our normal home microwave using as a heating medium. So can you tell us the challenges if we want to make microwave pyrolysis as a scale up while scaling up? What would be the challenges we have?
Yeah, yes, you can use the domestic oven, but you must have someone to renovate it.
Yes.
Because sometimes you do not want any leakage, microwave leakage, so you have to be careful.
Okay.
So you must have a good electrical technician who can, prevent microwave leakage. So that is very you have to be careful.
Okay.
I think you can do it, no problem.
Okay. So what? So you have shown that the phenol amount is higher than phenolic. Other phenolic compounds, right?
Yeah. You can check. You can check that because of the what called the lignin. They're selective to the lignin component. Yeah.
Oh, okay. So what was the yield, overall bio yield for your microwave pyrolysis?
The yield depend on the biomass. For palm shell, I've got the data, but maybe around 30%. 30%. The oil, the bio oil.
Okay.
You can check on my paper. We have already mentioned in one of our paper. It's around 30%, 30 plus 35 around it, if I can remember well.
Okay. Thank you, Professor Farid. It was nice to see the biomass related to palm oil industries and your microwave pyrolyzer also. I have a question regarding. Thank you, Professor Mohanty. What was the temperature you stored your bio-oil for aging test?
No, it's ambient.
It's ambient, so you kept it in room temperature.
It's ambient, room temperature. Just sealed it, nothing else. Yeah.
Okay. And can I know how did you separate the aqueous portion and non-aqueous portion? Because
only by gravity separation.
Oh,
and
gravity
then we used this one. We filtered up the this one. What is that? Is called a little amount of the biochar. Very less, very less. Because here plastic is there. No, so plastic is hardly getting any char. Everything is getting evaporated, and the char is coming basically due to the biomass. So very finer, very small amount. Yeah.
Okay.
So actually, before we wind up, I just answered that question. I just looked at it. The GCMS solvent. Now, GCMS solvent, what we use for this particular analysis, why I skipped the question, the result is that the reason is that mostly GCMS are outsourced, and in particular, whatever I have presented here, we have used hexane. Otherwise, alcohols are also being used. So I just confirm that it is hexane.
Okay. I think there won't be much questions, and thank you, Professor Mohanty, for the co-pyrolysis. It was to see many studies. I think thank you, Mr. Param, for organizing and helping us all technical issues. I think now we are done with our session 2, and I would like to thank all the audience who were present. Okay. I think we Mr. Param.
Okay, thank you, Dr. Suchitra. Thank you very much. Okay, let's take. I like to take the break too, guys. Okay, thank you very much.
Thank you, Param, for all your help. Very nicely you are managing the session. Thank you.
Thank you very much. Thank you. Okay, guys.
Thank you very much.
Okay, thank you.
Bye.
Bye. Let's take the break for 15 minutes. We start in 15 minutes. Yeah, please put on your timer on 15 minutes exactly. Thank you. Is Dr. Vinu is on the line? Dr. Vinu? Okay, Dr. Watanabe is all day, right? I wanted to check everybody's on. Dr. Watanabe? Hello?
Hello. Hey, Farhan. This
Yes,
is
hi.
Neil. I just logged in the conference call.
Okay, hi there, Dr. Mewang. So you got up early, yeah? Can you hear me? Dr. Binu, are you there?
Yes, I'm there.
Okay, super. Okay, you are going to have the next session taken care of, yeah? And
And can you just tell me the so the invited lecture is for 20 minutes, right?
yeah, invite lecture is 20 minutes. Yeah, that's right. Oral presentation.
And
Oral presentation 8 minutes, 8 to 9. Yeah.
8 to 9 minutes. Okay.
Yeah.
And I don't think I'm going to take care of the timing of the presentations, right? Because after introducing the participants, I'm going to hand over the introductions to you, correct?
Yeah. I think the first you do the first introduction. After that, oral I will take care. Yeah, so that I can do the faster. Yeah.
Okay.
Okay. But I want you to engage in the question and answer session and the panel discussion.
That I'll be.
Yeah. Okay.
I'll be there.
Okay. Super.
And what about the panel discussion following this session, the short oral presentation?
Yeah. They have the Professor Shogo-san. He will take care of it. He's a moderator for the.
Okay.
Yeah.
Great.
Yeah.
Thanks.
Okay. Super. Okay, and we start in a few more minutes. Yeah, we are running a little bit late, but I think we can catch up. Yeah.
Yep, sure.
You are based in Chennai?
Yes, I am from IIT Madras.
Yeah. So how's the situation? The floods is completely over. Everything normal now?
That is quite okay. Chennai is not that much hit. There were good rains.
Yeah.
Yeah, but probably the southern part of Tamil Nadu is what is being severely affected by the cyclone.
Yeah.
Couple of cyclones that struck.
Yeah, I was wondering whether it's it would be like in 2015. You had a hell of rain and floods.
Yeah, it is not like that. It is not like that. We had good rains. No doubt.
Yeah.
But it wasn't as bad. And I think this time the the overall control activities were also good. That we did not face any bad effects.
Yeah, better managed, I guess. We still need to learn more.
Yeah. Of course.
Yeah. I'm from Andhra Pradesh, but I lived in Chennai for a short while. Yeah.
I see.
Yeah. Okay, cool. So you're in the office, or I see the.
I'm in my office. Yeah.
Well, so you use a
Started
white.
working from office.
You are very good now using the whiteboard. I see there's so much black color there behind you.
No, it gets rubbed up.
Yeah, it means working
gets rubbed
hard.
up a lot. And yeah, trying to do something.
Very cool, man. Cool. Okay. 2 more minutes. We start the third session, last session. Yep. So your specialization on the biomass conversion to biofuels and intermediates and the microkinetic modeling of polymer reactions for photocatalysis.
Yeah.
And you from IIT.
Last time around the same time, I organized this event in Chennai at IIT Madras.
Yeah, I saw the picture.
We had the first PYRO Asia at IIT Madras last year.
Okay. Your internet is stable in IIT?
Yeah, pretty good. And I also have a geo connection, so I think it should be fine.
Okay, super. Okay. I guess you know the Dr. Watanabe before already, right? You met him, I guess?
Yeah.
Okay.
Yeah.
Okay, we get started. Yep. Welcome you back, all of you. I hope you get some coffee, maybe nature calls. Okay, so get back to our third session today. It's focusing on the analytical pyrolysis, and basically it has both oral presentation as well as panel discussion. Now I invite Dr. Vinu to chair this session, and Dr. Vinu, he is a professor at the IIT, assistant professor in chemical engineering department, IIT Madras. We call it currently Chennai. His research areas are focusing on the biomass conversion to biofuels and intermediates, microkinetic modeling of polymer reactions, and also the photocatalysis. He did his PhD from IISc, Indian Institute of Science from Bangalore. Dr. Vinu, it's all yours now.
Thank you, Parag. Thank you very much. A very good afternoon, good evening to all the participants and the invited speaker and the short oral presenters of this session, and all those who are attending this PYRO Asia second version around the world. So it gives me great pleasure to chair this session, and I really thank the organizers, especially Karthik, for making this Pyro Asia 2 e-Symposium possible. And in this session, we have one invited lecture and 4 short oral presentations, followed by, we will have a discussion of, if you have any questions, you can ask the presenters. And the invited lecture is going to be given by Dr. Atsushi Watanabe, Ichi-san of Frontier Laboratories, Japan, on analytical pyrolysis GCMS system. So there will be in the development of microlyzers. I'm sure the lecture is going to be very interesting. And followed by that, we have 4 short oral presentations by Adriana Burada Shravani, Jinan, and Mr. Jun Tamura. Right. So I now invite Ichi-san for the presentation.
Yeah, let's brief his profile.
Okay, so it gives me great pleasure to introduce Dr. Atsushi Watanabe. So he received his PhD in engineering from Nagoya Institute of Technology and is currently a vice president of Frontier Laboratories, as well as he holds a guest associate professorship in Graduate School of Environmental Studies, Tohoku University, Japan. He is responsible for international marketing in Frontier Lab, which produces micropyrolyzers, microfurnace pyrolyzers. His areas of interest, areas of research include analytical pyrolysis and development of analytical pyrolysis systems to study both material characterization and also to study a variety of reactions, starting from plastics, polymers, and a variety of other industrial reactions. So a warm welcome to Ichi-san, and let's look forward to his presentation.
Okay.
Over to you, Ichi-san. So I think you have 20 minutes for your presentation.
Okay, can you please accept my request to share the screen?
Yep.
Okay, you're on.
Okay, thank you very much for kind introduction, Professor Vinu. So I'm Watanabe from Frontier Lab. So I'd like to thank you all for giving me this opportunity to share my research. So since my title is a recent advancement of pyrolysis gas chromatograph system for analysis of microplastics, it will focus mainly on the advancement of analytical instrument. So I hope this study will be helpful to your research topics. So this is a table of the contents of my talk. So I begin with the background and then analytical methods for microplastics, what kind of methods are used, and then talk about the optimization of PYGSMS system for microplastics. So Professor Otani already explained about what is microplastics, but let me explain that again. So well, our lives have become more and more convenient as time goes by, firstly because of polymer materials. So here are data of the polymer material. Here are data of types and the use of the plastics in Europe in 2015. So within global annual production of 322 megatons, 40% was for packaging, and 20% was building, and 9% for automotive, 7% electronic, 3% agriculture, and then the rest. So when they are wasted, no, wait, again here. So speaking of polymer type, 20% was polypropylene, about 30% for polyethylene, and 10% PVC, and then so on. So when they are wasted, these polymer materials are wasted, some of them turns into microplastics, which would cause global environmental issues. So what is microplastics? So in this study, the definition of microplastics are the particle size, which has the in between 1 micrometer and 5 millimeter. The microplastics categorized into 2 parts. One is primary microplastic, which are pellets and fibers. Another is secondary microplastics, which is degraded pieces of primary microplastics. So I believe that our ultimate goal is to analyze nanoplastics because it may have the organic pollutants on the surface, which is called the POPs. But our scope in this study is limited to microplastics. So here are some examples of microplastics in the picture here. As you can see that each plastics are very unique in terms of the surface area, shape, size, dispersion, diameter, and color. So why do we need to analyze microplastics? Well, because there are so many things that we need to know about. We don't know about microplastics, so many uncertainties. WHO has announced that the further assessment of microplastics in the environment and their impacts on human health is needed. Therefore, it is very important to know the present situation and should be analyzed. What is present situation? Well, for example, it is about the distribution survey in the sea or seabed. But in order to do that, we need to establish the basic analytical methodology, of course, qualitative and then quantitative method. This table explains common analytical methods used for microplastics analysis based on the particle size. So x-axis is the particle size, and then here is analytical methods. The major analytical methods is spectroscopy techniques, so FTIR, Raman, micro-FTIR, micro-Raman, and optical. These analytical techniques are very effective methods for qualitative analysis as they are non-destructive analysis and independent of particle and fiber mass. However, the challenges are, for example, a longer analysis time, about 2 and 8 hours, if the sample amount are large. Also, the limitation by particle size. And then especially the quantitative analysis. The values are expressed by the number of particle per square meter. So with respect to the volume of the sample collected from on-site, or seawater or soil. So what about the pyrolysis techniques? So pyrolysis, GCMS, and TED GCMS. It doesn't really matter about the particle size actually. Their features are destructive analysis, also destructive analysis independent of shape and size, and inorganic contaminants do not disturb the analysis, the result. And then also the shorter analysis time, about 40 minutes to 3 hours per sample run. Okay, let's look at more details about TED GCMS system and PY GCMS system. So TED GCMS system. TED stands for thermal extraction and desorption GCMS. So this system consists of 3 parts: TGA system, and this is robotic arm, and then here a thermal desorption furnace and GCMS. So the analysis process is that a sample is placed or in a sample pan and then heated in a nitrogen atmosphere here. And then the volatile components generated are absorbed on a small element device, maybe the twister, which has a silicon film on the surface. After that, the element is moved from right here to left and heated again for thermal desorption. And then the thermally dissolved components are trapped here in the PETV injection, where it is cooled by liquid nitrogen. Then here is reheated again, and then the trapped components are introduced into GCMS. Other features of TED GCMS system is the total analysis time is about 3 hours per sample, and sample amount they can take maximum 20 milligrams. But there is a concern that if you thermal dissolve 20 milligrams, it may contaminate the flow path. Let's look at the PYGCMS. Here is a PYGCMS system configuration. It consists of a pyrolyzer installed on top of GC inlet. Here is a GC and an MS. This is very simpler flow path configuration than TED system. In this method, basically you place a sample and then introduce to the pyrolyzer and then pyrolyze it, and then pyrolyzed components are introduced into GCMS. And mass step. Okay. All right. So, well, when we analyze microplastic sample, of course, we conducted a trace experiment of analytical methods published in this paper. The reference paper is the work of Dr. Barbara of the ICBM Institute in Germany, and then who is also our collaborator. They use the pyrolysis together with TMH. So they use the single shot, the flash pyrolysis method. At the same time, they use the reactive agent, TMAH, tetramethyl ammonium hydroxide, and then to do a thermally assisted hydrolysis and methylation technique. Here is a pyrogram when we analyze or pyrolyze a polymer mixture sample. So the biggest challenge with this analysis is that the methylation agent does not work with the polyurethane here. So here, this graph tells you the reproducibility of each polymer based on pyrograms here. And when we look at the polyurethane, you can see that the reproducibility, by the way, reproducibility is y-axis. Reproducibility is over 70%. So to improve the reproducibility, we use the quartz filter. This is sample cup and then sample and then quartz filter to increase reaction efficiency in between TMAH and polyurethane. But however, it didn't work. As you can see, this red line is the result. So based on the trace analysis, the experiment, we thought that the optimization of PyGCMS system is important. So in this study, we tried to develop a couple sample prep techniques and then also the system measurement system as well as the data process system. So sample preparation for reference polymer sample. So we targeted these 12 polymers. We selected these 12 polymers as a reference polymer mixture for calibration. So due to the reproducibility as shown in the previous slide, it is important to use a as small sample as possible. So regarding, so we categorize those polymers into two parts. One is poorly soluble polymers. These are polyethylene and polypropylene. So in this sample, we decided to use the particle size of 30 micrometer or less. Actually, we used the at first we used the 200 micrometer size, particle size polyethylene and polypropylene, but the reproducibility was very bad. So we decided, we tried again and again, and then we decided to use this size of the particle size. And then another is soluble polymers. These polymers are dissolved in this solvent, THF, dichromazine, and HFIP. Then this is how we prepare the sample. So you place a sample, polyethylene, polypropylene sample in a sample cup, and then add those dissolved polymers, and then we just analyze and then create a calibration curve for quantification. Another development for sample prep is the use of inorganic diluent, which has two benefits. One is to improve reproducibility of a polyurethane. Okay, here's the example. So when we pyrolyze polyurethane sample at 600 degrees C, it produces the MDI and 1,4-butanediol. And if water is present, and the end of the MDI easily becomes an amino group, and MDA and MAI are generated. So we tried many types of inorganic diluents, and we decided to use quartz as a diluent. So the quartz, the size, particle size is 6 micron. And when the quartz fine powder is washed or actually untreated, MDI, our target peak, is not detected. And MDA is slightly detected, as shown here. On the other hand, if we use the deactivated quartz, what happens is that the MDI is detected clearly when the silanol group on the surface of the fine quartz powder are deactivated. And then we also tested that the diluent does not react with pyrolyzed products of other polymers other than polyurethane. And as a result, the deactivated quartz fine powder was selected as diluent. And then also, don't forget, another benefit of using diluent is that you don't need to use ultra micro balances. Just use the semi-micro balances. There are as many peaks appear on pyrogram on the microplastic samples. Simplification of pyrogram is very helpful for the interpretation. This is a chromatogram of mixture hydrocarbons in hexane solution. Suppose that this is a pyrogram of microplastic samples. For this analysis, reactive agents are used. So large and broad peaks derived from a reagent are observed usually here. Also, polymers such as polyethylene generates high boiling compounds peaks, which can be a source of the contamination of the system. Since characteristics peaks used for qualification and quantification appears before carbon number C24, we added precut and then backflash function to the system to eliminate those unnecessary peaks. As shown here, unnecessary those solvent peaks and the high boiling compounds peaks are eliminated. Also, using backflash gives you the benefit of reducing the total analysis time as well. For the data processing, we develop qualitative and quantitative software. This is an enlarged pyrogram of a reference mixture sample at retention time in between 4 and 10 minutes. And this is a pyrogram of polypropylene showing characteristics pyrolysis peaks here and here. To qualify and quantify polypropylene, existence of these pyrolysis peaks in the pyrogram needs to be confirmed. Okay. On the other hand, like this. On the other hand, our searching algorithm is very unique. First, our software that automatically finds out if there is any polypropylene characteristic peaks on the pyrograms. And then also searching those peaks based on the, of course, the characteristic ion of each peak. And then sum up the mass spectrum information of each peak and create summation mass spectrum. And sum up mass spectrum of each peak and create, and then compare it to the summation mass spectrum information in the database, and then check the similarity. Okay, this is an example of searching result obtained by this software. You can see the table here. It shows the matching probability and also quantification result, and then also the ratio of the total samples. In this case, we use the model sample in the mixture of polyethylene and polypropylene. So we got the clear result that the 65 of the sample are polyethylene, and then 30, the rest is polypropylene. So when we look at the rest of the result, for example, nylon 6, the matching probability says 45%. It's quite high. But when we look at the quantity amount, it's 0.02 microgram. Actually, we set limitation of quantification. So if it's below this number, then nylon 6 is not included or contained in the sample. Also, you can check this mass spectra information and then also the peak information as well. So first you look at the resulting table and as well as mass spectrum information to make sure your result is correct. So we believe that the various problems will arise in the analysis of actual samples as they exist in various forms like this in the pictures. Woods, plastics, size is small, and so on. Okay, this is an example. So the top pyrograms here is when we pyrolyze 75 micrograms of 12 polymers mixture plus 300 micrograms pine wood. And the bottom one is just the pyrograms when we the pyrograms of the 300 micrograms of 12 polymers mix. So when we compare and then we try to quantify, what happened is that there was a problem that calibration curve did not overlap. Okay, here the blue dots are just a pure polymer mixture of the polyethylene. But when we add wood mixture, then what happened is those dots, the red dots, does not correlate to the blue dots. So in addition, this is a pyrogram of a sediment sample provided by Dr. Barbara. Although the sample details are unknown, the many crude oil related peaks were detected together with polyethylene, polypropylene, polystyrene, PVC peaks. So since we are analyzing real sample is the natural product, so we need to consider the matrix effect depending on what kind of the synthetic polymers are in the sample. So in summary, analysis of microplastic was not easier than we expected. So there are many challenges to accurately qualify and then quantify the real samples. So our company will continue research and then development for the analysis of microplastics to establish the proper methods. Okay, that's about it. Oh, the acknowledgement. I'd like to thank all people who have contributed to this study through hard work and valuable discussion over the years. I will not name everyone's, but thank you very much.
Okay, thank you, Dr. Watanabe. It's a very interesting presentation on the latest developments, advancements on the pyrolysis gas chromatographic system. Thank you. Guys, if you like to ask question, Dr. Watanabe, please post your question box, and please make sure you attend attention to his name, okay, so that he will answer it on the question and answer session. Thank you. Let me take over my screen. Here I go. Okay, now we are getting into the oral presentations. As you know, there are 4 presentations, as each of you has a maximum, including Q&A. So you have 8 minutes presentation, 2 minutes will go into the Q&A session. So please finish your presentation 8 minutes. Okay, let me introduce the oral presentation. First speaker is on the methodology for using chloride molten salts in a tandem micro reactor during the pyrolysis of lignocellulosic biomass. This presentation will be done by Adriana Estrada. Let me brief about her. Okay, here she is. She obtained a Master in Science in Environmental Sanitation granted by the Ghent University in Belgium in 2018. She is a second-year PhD student at Ghent University in the Thermochemical Conversion of Biomass Research Group under the supervision of Professor Frederick Ronsey and Professor Walter Prince. Her PhD is a part of the Horizon 2020 project EU called ABC Salt. Adrian's research focus on hydropyrolysis of lignocellulosic biomass in molten. Let's welcome Adriana to make a presentation, and let me ask her to share her screen. Here I go. Yes.
Can you see my screen?
Yes, right. Yes. Okay, put in the full presentation mode, please.
Okay. Okay. Thank you very much. Hello to everyone. I'm very glad to give this presentation here today. So my talk will be about the methodology for using chloride molten salts in the tandem microreactor for the pyrolysis of biomass. And this research is part of a project called ABC Salt. And ABC Salt basically has the objective to demonstrate a novel route to produce liquid biofuels. I would just put this. Yeah, to produce liquid biofuels from different types of lignocellulosic waste streams. And the main concept of this project, you can see it in the scheme on the right. It basically comprises 3 different process steps. The first one is the liquefaction of the biomass in molten salt media. Then the second step is hydropyrolysis of the introduced liquefied biomass. And the volatiles formed from hydropyrolysis go to a hydrodeoxygenation stage for further processing in order to produce the biofuels in the middle distillates range. Now, at Ghent University, we are using PyGCMS to study the pyrolysis of biomass in a molten salt medium. But what are molten salts actually? The molten salts are eutectic salt mixtures that have a low melting point in the range of 200 degrees to up to 260 Celsius degrees. And basically the molten salts, not only can they act as a solvent for biomass liquefaction, but they can also act as a heat carrier in pyrolysis, as well as a catalyst in pyrolysis of biomass. Now, in our laboratory, we use a tandem microreactor from Frontier Laboratories. And basically for ABC Salt project, we are interested in looking into the effect of carrier gases, so the use of helium as well as hydrogen in the TMR. We also look at the pressure effect. We want to look at the pressure effects, and as well as to perform ex-situ upgrading of the volatiles in the secondary reactor that are derived from the first reactor where the molten salts pyrolysis takes place. So for this presentation today, I would like to focus on 2 points. The first one, it's about the optimization. So indeed, how to use the molten salts in the TMR, what are the consequences. And for that, the feedstock that we use was cellulose, and the molten salts, it's a combination of zinc, potassium, and sodium chloride in different compositions, and then also zinc and tin chlorides in a different composition. So that would be the first thing. Indeed about looking into the catalytic effect of a single composition of chloride molten salt in the pyrolysis of different feedstocks. So for example, kraft lignin, pine wood, wheat straw. And how do we prepare our samples? We pre-mix the biomass with the solid salts, and we introduce it into the TMR, the tandem microreactor, at a pyrolysis temperature of 350 Celsius degrees. So let's look at the optimization. We have identified two main issues when we use the molten salts in the TMR. The first one is regarding hydrolysis. So we detected the production of hydrochloric acids in cellulose pyrolysis. And that is what you can see in these 2 pyrograms. So this pyrogram on the top is from cellulose pyrolysis in the chloride molten salt in this composition. And then we detected hydrochloric acid being formed. And then we repeated that experiment using another type of eutectic chloride molten salt in another ratio. And then that was even more drastic in terms of hydrochloric production. So you see that there was massive production of this gas. So this was the first issue that we encountered. And then the second issue was regarding the volatilization of the molten salts. So we noticed that after using the salts in the TMR, if we look at the degradation pattern of cellulose pyrolysis at the regular or more likely fast pyrolysis temperature, so at 500 Celsius degrees, the pattern, the decomposition pattern of cellulose was drastically changed. And that is what you can see in this graph here below. So this is before using salts in the TMR, and then after using the salts. And then typically before you have a high response of levoglucosan as well as other anhydrous sugars. But then after using salts, and then we test again the pyrolysis of cellulose, levoglucosan peak area, it becomes decreased for more than half, and then also other degradation compounds are appearing. So what we think is that when we use the salts in the TMR here, and this scheme on the bottom, they become volatile, and they entrain further in the TMR, causing a catalytic effect if we just test the cellulose here. And this here is just a picture that shows where potential spots of part the tube reactors inside the TMR where salts could deposit after using after performing this type of experiments. So how did we overcome this? So for this project, different types of of chloride salts, so zinc, potassium, and sodium chlorides, have been investigated for their hydrolysis results. So there was one composition that you can see here in green that seems more stable. So we test that in the pyrolyzer one more time. So it's this composition that you see here. So we tested the pyrolysis of cellulose in this molten salt, and then we noticed that there was no hydrochloric being produced in a way that we can safely use the salts in the TMR. And then what we also did was we decreased the temperatures in the TMR upon pyrolysis reactions in the molten salts took place in order to have a better environment for the salts, and we also limited the carrier gas flow in order to avoid any entrainment of the salts downstream in the TMR. And now I will show you the catalytic effects of the salts in the pine wood and wheat straw pyrolysis. So the main, the most important thing, if you can look at these two pyrograms in the left, the one on the top is from a regular pyrolysis of pine wood. So there's a lot of compounds being identified. But when we pyrolyzed pine wood in the TMR with the molten salt, there is a higher selectivity, in particularly for furfural and an acetic acid. And then if you look at the picture at the graph in the right, this shows the different chemical groups and their corresponding peak areas. For in yellow, this is pine wood, and in green is wheat straw, and then in the full colors is the raw biomass, and the pattern one is the response in the molten salts. So the main conclusions here, the main results here are that, as you can see, with the molten salts, there's an increase for both biomasses for the furans compounds. And now also, if you look at the phenolics, it's really clear that there's a catalytic effect of the salts that causes a decrease of the phenolic compounds when there is a presence of the molten salt. And then we also see that there is chloromethane formation from the pyrolysis in molten salts. And basically this is the potential reaction of the lignin fraction in these two biomasses, so in the pine wood and in the wheat straw. And now we look at the same. What is the catalytic effect of the salts when we pyrolyze kraft lignin? So again, the first in the left, the first pyrogram, this is for pyrolysis of hardwood kraft lignin. So you have a lot, a wider range of phenolics, lutein. But when we pyrolyze the hardwood kraft lignin in a molten salt, it's really selective towards guaiacol and syringol mainly. And then again, if you look at the graph to the right, the different groups identified, I think what I would like to stress here is, okay, in red you see the softwood kraft lignin, and in blue is hardwood kraft lignin. And then the pattern graphs are the responses of these compounds in the presence of molten salts. So the main results here, again, as for the previous feedstock, is that the phenolic compounds, they become more selective, yes, but in overall there's a decrease of the phenolics when molten salts are used in the pyrolysis of this feedstock. And again, we detect chloromethane formation from this pyrolysis experiment.
Adriana, can you please conclude? The time is up.
Yes. Okay. So our conclusion from this work is that PyGCMS is a advantage tool for assessing the effect of the molten salts in the pyrolysis waste streams. We see that the hydrolysis and the volatilization of the chloride molten salts can be suppressed, which enables a good use of this in the TMR. We also see that the pyrolysis products in the molten salts become more selective. And the last is that overall, the pyrolysis volatiles in the chlorine molten salts become limited or reduced, especially in regards to the phenolic content. And with that, I would like to thank all of you for your attention.
Okay, thank you, Adriana. That's a very good presentation. Let's, if you have any questions, guys, you post questions in the question box and we'll address it at the end here. Thank you, Adriana. Let me take over my screen. Okay, the next presentation is on the evaluation of pyrolysis behavior, pyrolysis kinetics, and product analysis of thermal protection system, TPS materials. It is by Burada Shravani. Okay, let me welcome her. Let me take her, ask her to share the screen. Okay, there we go. Yes, okay, yeah. Okay, Shravani, you have 8 minutes.
Yes.
Yeah, thank you.
Okay, thank you. Hello, everyone. Can you able to see my screen?
Yes, yes.
1 minute. Yeah. Here I'm going to explain my topic on evolution of pyrolysis behavior, kinetics, and detailed product analysis of thermal protection materials. These materials are used to protect the space from aerospace vehicles into atmosphere. Space vehicles that enter a planetary atmosphere like Earth, the Space Shuttle orbiter require the use of a thermal protection system to protect them from aerodynamic heating. The aerodynamic heating is generated at the surface of the entry object due to the combination of compression and surface friction of the atmospheric gases. The vehicle's configuration and entry trajectory in combination with the type of TPS material used define the temperature distribution on the vehicle. The space shuttle features a TPS system based on the use of surface material with a high temperature capability in combination with an underlying thermal insulation to inhibit the conduction of heat to the interior of the vehicle. The heat developed from the aerodynamic heating here in this picture. Yeah, here aerodynamic heating process radiated back into space by virtue of the high surface temperature. In this study, I mainly focused on 3 different materials like ethylene propylene diene monomer rubber and rocket case insulation and IR which is called polyisoprene rubber. Here I mainly focused on 3 different models like TGA and pyrolysis FTIR and pyrolysis GCMS. To study the kinetic behavior of thermal protection system materials, I have done TGA at 5 different heating rates, and I analyzed by using solid state kinetics. I have used Arrhenius equation to solve my kinetics. Here, model fitting kinetics and model free kinetics, 2 different methods are there. In this, I done my experiments in non-isothermal condition, and I have used my kinetics by using model free kinetics. Here, these methods I focused Flinwall-Osova, which uses logarithm function of heating rate and temperature. From this, I found slope and equate to this, and I found activation energy. And Kissinger-Akahira-Sonos, which is a graph plotted between ln beta I by T alpha I square and 1 by T, which is the slope equal to this. And I used Vasokin method to understand the iterative methods by using MATLAB. I used objective function to minimize the number of iterations, and DAM method to understand the experimental values and simulation values. So here I did basic characterization of fields which I have received from ISRO. from this table, we can see volatile matter is high in EPDM, Rocasin, and IR, and fixed carbon is very low in EPDM and more or less same in Rocasin and IR. Ash is like 20 to 30%. And elemental analysis to list out the what is the composition of different elements like carbon, hydrogen, nitrogen, and oxygen. Like in IR, there is no nitrogen and sulfur amount traces. So in Rocasin, nitrogen is present like 5%. And ICP-OS analysis to study the ash composition, metal composition present in ash. And this FTIR I have did for material before doing pyrolysis. Yeah. From these plots, I did TG, DTG simultaneously at 5 different heating rates, 5, 10, 15, 20, and 25 different heating rates. For these heating rates, for all materials, maximum mass loss peak is shifting towards higher temperature and following the same trend with increasing heating rate. So mass loss curves showed that like for all heating rates, the residue remained is like within plus or minus 1. And by using Vesokin, Kissinger, Akahira, and Plinwall Osava, I have calculated activation energy with regard to conversion. At different conversions, the activation energy is increasing with increasing conversion and at some point of time, and after that it is decreasing beyond 0.9. So I didn't put after 0.9 conversion. For EPDM and Rocasin, the conversion activation energy with conversion is following the same trend, while for IR, the activation energy is increasing gradually till 0.7, and after that it steep increasing is there. So I have observed that all these three materials followed like more or less same activation energy for all the isoconversional methods. In DIM experiments, here I used first order pseudo components to determine which pseudo component will suit for my material for differential thermogrammetric analysis data. I used MATLAB to simulate this and different components. For EPDM, I have used 3 components, and for Rocasin, I have used for EPDM, I have used 4 components, and third pseudo component best fit with 98.9% at 10 degrees C heating rates. I have done for all heating rates, all best suit with third component for EPDM, and for Rocasin, third component suits. And for IR, I have at 15 degrees C heating rates, the fit percentage is more. So I did for IR at 15 degrees C heating rate. Actually, to understand the functional groups present in the pyrolysis vapors of thermal protection materials, I have done pyrolysis FTIR, which is like pyroprobe connected with FTIR of in Brill cell setup. So here I have used Brill cell setup to heat pyroprobe coil. I have loaded my sample in quartz tube, 8 mg of sample. So by closing both ends with quartz wool, and I raised the temperature from room temperature to 1100 degrees C to understand the pyrolysis behavior during time. Here for EPDM, the pyrolysis vapors detecting starts at 8 seconds. This is due to the lag between Brill cell setup and the IR. So it reaches maximum at 18 seconds and then gradually decreased and remains constant till 300 seconds. So this I did to understand if there is any gradual decrease in the pyrolysis vapor concentration. Here for Rocasin, the concentration of vapors is not reducing, like it's not reaching the baseline. This is because still that vapors are forming on the condensable of the Brill cell setup. So this decreasing we are not observed. So here in IR, there is a steep decrease at 15 minutes for all the functional groups, and it reached the baseline and constant. So here in these, the major peaks are in EPDM and rocacin are nitrogen, carbon, hydrogen compounds functional groups, and carbon dioxide is the gas which we have found that it is due to pyrolysis of these materials, CO is forming.
Shravani,
So
have
here,
1 minute,
yeah,
please.
yeah, sure.
Are you concluding it?
Yeah, after
Please.
this slide, I am going to conclude.
Okay, thanks.
Actually, I did after my experiments in pyrolysis GCMS to really know the which functional groups are evolving from pyrolysis FTIR. I have followed the same program for pyrolysis, like from 30 degrees C to 1100 degrees C for all my materials by using 500 degrees C ramp for GC program. And I observed that aromatics are presenting more in all the materials, and in EPDM, aliphatics are dominating, while in rocacin, nitrogen compounds are high. It is observed in CHNS data, and in isoprene rubber, others represents including alcohol, OH groups, which is observed in pyrolysis FTIR. To really know the from DTG, I found that 3 major Maslow's regions I have observed. To the which compounds are these, I have done at different temperature ranges, and I found that where maximum Maslow's is there more products are evolving from pyrolysis GCMS. So here I'm concluding all the methods which I have used are the activation energy is same, and DAM model best fit with experimental data. Pyrolysis FTIR for major functional groups are evolving in the time range of 10 to 40 seconds, and these functional groups are detected in pyrolysis GCMS. Thank you.
Thank you, Shravani. It's a good presentation.
Yeah.
If you have any questions that guys ask, you post in the questions in the question box. Let's go to the next presentation. Okay. Okay, the next presentation is it's on the pyrolysis of Salicornia Visual V product characterization and apparent kinetic analysis. It's by Jinan Al-Jajiri. So let's welcome Jinan. Okay, let me share her screen. Jinan, you have actually 8 minutes. Try to finish in 8 minutes, please. Thank you. Okay, you're on. Yes.
Can you see my slides?
Yes, please. Okay. Put on the PowerPoint mode. Slide mode, please.
Sorry?
Presentation mode.
It's on presentation mode. Can you see it?
Okay. It's not. We see the seals. Yeah, now, yes.
Is it good now?
Okay, go on, please. Yeah, go ahead.
Okay. So hello, everyone. My name is Jinan Al-Jaziri. I'm a PhD student at King Abdullah University of Science and Technology. And today my presentation is about pyrolysis of Salicornia bigelovi, product characterization and apparent kinetic analysis. So today we'll go through the motivation behind the study, biomass characterization, product analysis, and then finally kinetic analysis. So one of the main issues limiting the use of biomass is that it requires, or that most types compete with agricultural products for arable land as well as fresh water. We are currently facing a decrease in the availability of arable land as well as depletion in freshwater resources, which makes the use of biomass as a source of energy even harder. Therefore, a new biomass crop is needed that doesn't require either of these two. And we've been studying the use of Salicornia bigelovi. So Salicornia bigelovi is a halophyte. A halophyte is a salt-tolerant plant. So that means that they don't require freshwater irrigation to grow. Salicornia has also been successfully grown in arid climates. So the vegetative biomass remaining after removing the seeds can be converted through pyrolysis into bio-oil, biochar, and biogas. This vegetative portion of Salicornia bigelovi has typical lignocellulosic characteristics. It has 46% cellulose, 15% hemicellulose, and then 2% lignin. So for the biomass characterization, we performed a preparation step. We did a thermogravimetric analysis, proximate analysis, elemental analysis, and then finally mineral analysis. For the preparation step, we chose to study the vegetative parts remaining after seed harvest, and we washed the biomass with deionized water to reduce the mineral content of the biomass. Now, this is our thermogravimetric analysis. This is the DTG we obtained. We noticed that the major decomposition is at around 200 to 350, and that's due to the decomposition of hemicellulose and cellulose.
Jinan, excuse me, your slides are not moving.
Really?
Yeah.
Are they still not moving?
No.
Jinan, I think you have to put it in slideshow mode.
I'm already in slideshow and I'm moving.
Now it seems to move.
Let me go back. Is it moving now?
No, it is in motivation.
Are you using the two screen? Yes, now it's okay. Yeah. No, it's not moving.
Is it moving now?
Now it's moving. Yes, yes. Okay.
So I'll just continue then. I was on this slide.
Yes. Okay. Go on.
Okay. So yeah, this is our thermogravimetric analysis. We then moved on to do approximate analysis, and in this we compared the use of the pre-treated Salicornia bigelovi, abbreviated as PSB here, and then the untreated Salicornia bigelovi, abbreviated as USB. And we noticed that the pre-treatment step was able to reduce the ash content from 24 to 7. It was also able to increase the volatile matter. Now, the increase in volatile matter resulted in higher carbon content for the pre-treated Salicornia bigelovi. Combining this result with the reduction in ash, we were able to obtain a higher heating value for the pre-treated Salicornia. For the mineral analysis, we noticed that the highest inorganic present in the plant was sodium. And with the pre-treatment step, we were able to reduce all of these minerals into almost half. So for our experiment, this is a schematic of the setup. We studied the pyrolysis in nitrogen atmosphere, and we did it at 600, 700, and 800 degrees Celsius. The products were biochar and bio-oil. For product yield, we noticed that the highest amount of biochar was obtained at 600 degrees Celsius, as you can see here. And as we increased temperature, the yield of biochar decreased, and that's due to enhanced cracking of volatile matter. And then for bio-oil, the highest yield was at 700. And then for going from the low temperature 600 to 700, we noticed an increase in the bio-oil, and that was due to thermal cracking and dehydration reactions. As we went on to higher temperatures from 700 to 800, we noticed a decrease in the bio-oil, and that's due to cracking of the gases. So for our bio-oil contained a mixture of about 300 to 400 compounds, and we characterized those compounds into the following categories, as you can see. We noticed that we obtained the highest amount of carboxylic acids at 600 degrees Celsius. Some of the major types were N-hexadecanoic acid, linolic acid, and stearic acid. We see a significant reduction in the carboxylic acids as we move to higher temperatures, and that's due to enhanced decarboxylation reactions that occur at higher temperatures. We also observed a high amount of nitrogen-containing compounds at higher temperatures like 800 and 700. For our biochar, we have the FTIR spectra of the raw biomass as well as the biochars at 600, 700, and 800. We noticed that the FTIR spectra features were generally lost in the biochars. We noticed the disappearance of this broad region over here for the OH stretching at 3320, and that's due to dehydration. We also have peaks at 1630 and 1589, which are due to amine bends, which owe to the presence of nitrogen in the biochar. And then the peak at 874 was due to aromatic bending. We finally performed a kinetic analysis, and we performed the TGA experiments in nitrogen as well as carbon dioxide atmospheres. And we applied the Friedman method to find the apparent activation energies. So we plotted the logarithmic term as well as the versus 1/T for multiple heating rates, namely 5, 10, 15, and 20 degrees Celsius per minute. And then based on the variations in the slope, we split the process into multiple reactions. And so upon splitting the reactions, we calculated the activation energy for each reaction. And we generally noticed that the activation energies were higher under CO2 conditions. And we attributed that to reactions of CO2 with the biomass at higher temperatures to produce carbon monoxide. So to conclude, our pre-treatment step was able to reduce the ash content from 24% to 7%. It was also able to reduce the sodium content to almost half. We noticed that we obtained the maximum biochar at 600 degrees Celsius, whereas the maximum bio-oil yield was at 700 degrees Celsius. We observed higher apparent activation energies in carbon monoxide atmospheres compared to nitrogen atmospheres. And then for future work, we plan to continue the kinetic studies for this experiment. We would like to find the pre-exponential factor as well as the function, the reaction function, and possibly explore the products of the pyrolysis under CO2 conditions. And that's all for my presentation. Thank you for listening all.
Okay, thank you very much, Jinan. It's a very good work. If you have any questions to Jinan, please post in the question box. Okay, well, now let me take over my screen. Okay, the next presentation. There's a presentation by Joel and Mr. Jun Tamura-san. He is going to make a presentation. Let me brief about Tamura-san. 2009 to today, he's been Mass Spectroscopy Sales Promotion Group, Scientific Instrument Sales Division at Geo. And in 1995-2009, he's also the MS R&D engineer, later as group manager. 1989 to 95 is MS Mass Spectrophotometer Applications Chemist at the Geo USA. 1985 to 1989. He's also the application chemist at the Geo, and he's graduated from the Tokyo Institute of Technology with a bachelor degree in chemistry. And also he received an award, Mass Spectroscopy Society of Japan Award for Technical Development and the development of orthogonal acceleration time of flight mass spectrometer. Let's welcome Mr. Tamura-san to make a presentation. Let me ask her to share his screen. Yes.
Okay, let me see.
Yes.
Okay, can you see my screen?
Yes, sir. Go ahead.
Okay. So the time is limited, so let's go on to my presentation. I'll talk about my company, JOL, and several solutions I think we can offer for the pyrolysis community. So our company is called JOL because it's originally called Japan Electron Optics Laboratory Limited because we started as an electron microscope company in 1949. So that's only 5 years after the end of World War II. Currently, we are located in the west suburbs of Tokyo, and we have revenue of about 117 billion yen. So this is my mic is too sensitive, so let me see. Let me see. Can I just? Let me see. Okay, let me move my microphone a bit further. Anyway, so we have revenue of about 117 billion yen, what that actually means about $1 billion US per year. We have about 3,000 employees worldwide. And we make many different instruments, scientific instruments, industrial instruments, and also the medical equipment that is actually in vitro diagnostic instrument. But I'm from mass spectrometer, so I'll talk about mass spectrometer, especially the GCMS and the gas analysis instruments, and especially I'm going to talk about these two instruments that I think we can offer some unique solutions for pyrolysis research. So the first thing I'm going to talk about the analytical pyrolysis GCMS. And as you know that when you perform pyrolysis GCMS on polymers, majority of pyrolysates, even the ones from popular polymers and plastics, are unknown compounds, so sort of they are not registered in DI mass spectrometer library. So we cannot rely on libraries for pyrolysate identification. So here we want to offer the combination of high resolution, accurate mass capable mass spectrometer that can be equipped with the combination ion source of electron ionization and soft ionization, such as field ionization, and the software to analyze the data automatically. So here's our hydrogen GC time of flight mass spec that can give chemical formula based on accurate mass measure. This can be equipped with soft ionization technique like chemical ionization or photo ionization. Sorry, let me. Photo ionization or field ionization. And we have a software to automatically interpret a pair of data acquired with electron ionization and one of the soft ionization technique. So here's the solution we can propose for the studying pyrolysis process in real time. Here is a challenge. I think many of these evolved gas components from pyrolysis process are isobaric. That means having same nominal mass or integer mass. So they cannot be distinguished by low resolution quadrupole mass spec that usually equipped. So we can offer again the same high resolution time of flight mass spec, combined with the Frontier Labs multifunctional pyrolyzer, or in certain case, combined with thermogravimetry equipment, such as the ones from NETCH, as shown in picture here. Here's one example. It's a developed gas from nylon 66, so that's actually synthetic polymer. But in this case, here's the overall mass spectrum from electroionization. This can be expanded here from the region of 10 to 50 Dalton. If you look at this peak at 28 and further expand, then you can actually find a peak for carbon monoxide, nitrogen, CA2N, and ethylene. So with the high resolution mass spec, you can independently monitor these isobaric gases at the same in real time simultaneously. Another solution for studying pyrolysis process under oxidative condition in real time. The challenge is that many of the commercially available mass spectrometers, actually including our own GC high resolution time of flight mass spec, cannot trade much oxygen. That our quadruple mass spec, Q1 1500 GC, which is extremely robust with a high capacity vacuum pumping system, which can allow EGMS or TGMS experiments with simulated atmosphere like oxygen helium 2080. So if you're interested in knowing the pyrolysis process under atmospheric pressure, atmospheric conditions, we can contribute with this system. So if you're interested in the solutions we can offer, please contact our local representatives in your region or leave your message on the request product information page in our global website. And thanks for your kind attention.
Thank you, Tamura-san. Guys, if you'd like to know more about products of the Tamura-san, please contact him. And okay, let's we get to the. Let me take over my screen. Thank you, sir.
Thank you.
Okay, I saw a lot of people ask some questions. You know, the time is short. I'd like to have like a rapid fire type of answers. I request Dr. Watanabe and also other world present speakers quickly come onto the line and answer these questions one by one. There you go. Yeah. Dr. Watanabe.
Hello?
Yes, you're on. Yes. So
Yes.
you see the questions? Yeah.
Okay, so the first question is how addition of inorganic diluents helps in polyurethane analysis. So when we pyrolyze polyurethane, we are looking at the MDI peaks to quantify polyurethane, but because of the MDI is highly active, depending on the situation, it turns into MAI or other compounds. So we want to get stable amount or the reproducible peaks of MDI. So using this diluent, we are able to get a good reproducible peak of MDI, and then we can quantify the polyurethane. And you have shown aromatic part of polyurethane. What about the polyol part? Diluted polyol gives many peaks in pyrograms. Polyol, I didn't, actually we didn't look at the polyol peaks. In order to quantify polyurethane, we just look at the MDI, the ion as well. I would like to know the metal content of the microplastics, please. This is good question. We haven't checked on that. And what is the advantage of PYGCMS process, and why is the sample not analyzed? Okay, well, I'm not sure what is the advantage of the pyrolysis GCMS process over other other analytical techniques. If so, well, if you use spectroscopy techniques, let's say if the samples are colored sample, if it's black, how can you analyze or quantify the sample? Well, if you use the pyrolysis technique, you just use the heat energy to break the samples. So the color of the sample doesn't really matter. So if for example, your sample has a black color, it doesn't really matter. PyGCMS, you can quantify the sample. Why is the sample not analyzed directly on the GCMS? Because the polymers, if you inject the polymer, well, the boiling point of polymer is much higher than the injector temperature. So you need to gasify or pyrolyze the polymer in order to turn the pyrolyzer into the gas form to inject into the GCMS. So you need to pyrolyze solid polymer sample first. What is the limitation of detection and limited quantification of microplastics by GCMS? So at this moment, our limitation of quantification of the microplastics, as I selected 12 samples, and it's varies, but it's around 1 micrograms, or the lowest is, let's see, 0.23, 916. Yeah, that's the lowest, the limitation of quantification.
Okay. Thank you, Dr. Watanabe. Adriana? Adriana, are you there?
I am here.
Okay, it's your questions for you. Please quickly answer them. Okay, it's a time is short.
Okay, so the first question is if we purchase molten salts. Yes, so we purchase the salts individually, the zinc, potassium, and sodium chloride. That's the one that we are working on right now. And we make the mixtures. I make the mixtures by myself. And the second question is what has been the temperature inside the lower reactor. So we keep it at the same temperature as for the first reactor. So it's also 350 Celsius degrees. And that reactor so far has been kept empty. But in the future research, we want to analyze like the upgrading of the vapors formed in the first reactor. So then we would place a catalyst in the secondary reactor. But I mean, this study is important because if we would have salts going further into the secondary reactor, they would reach the catalyst, which would be not a wanted situation, in my opinion. How did you handle the effect of hydrochloric acid vapors and toxic chemicals like furans? So regarding the hydrolysis vapors, what we did is basically limit the pyrolysis temperature. Normally for PyGCMS work, typically on average you use temperature of 500 Celsius degrees. But because at that temperature, so initially I started doing molten salt pyrolysis in the TMR at 500 degrees, and it was also a lot of hydrochloric acid being produced. So we limit the pyrolysis temperature to 350 degrees, and that suppresses the effect of hydrochloric acids. And then, yeah, it depends. I'm not sure if you would, from this point of view, say like, toxic chemicals like furan, because so the idea of the concept of using molten salts is that it acts as a catalyst, so it produces selective products, and that can be, in my opinion, interesting. And what was the other question is what was the ratio of salt and sample in your in situ experiments? Yeah, we use 1 part of biomass in a 20 parts of molten salts. That's the ratio we use. And yeah, thank you.
Thank you. Dr. Watanabe, you have one more question?
Yes. Okay, how do you prepare deactivated SiO2 This is good question, and then I don't know much the details, so I think I need to investigate and get back to you.
Okay, thank you. Next, Shravani, is for you.
Hello?
Yeah, it's for you, Shravani.
Yeah. Can the method be done using? No, actually here comes, we have to use more iterations, which is not possible in Excel. So I used MATLAB.
Okay, thank you. Jinan, is your question next? Thank you. Jinan, are you there?
Yes, I'm here.
Okay.
So the question is, I would like to know why the authors decided to study Salicornia. Okay, so we decided to study Salicornia because, as I've mentioned, it doesn't require freshwater irrigation to grow, and it doesn't require arable land. So we can grow it in coastal areas with salt water. So like seawater. And then the second question, why is the bio-oil yield decreases at 800? So the biochar decreases at higher temperatures because of cracking of organic matter. And then the bio-oil decreases because of cracking of the volatiles into non-condensable gases like carbon dioxide, carbon monoxide, and methane.
Thank you, Jinan. Okay, this is a question for Mr. Tamura-san. Mr. Tamura-san?
Yes.
Okay.
Can you hear?
Yeah.
Okay. TGGCMS. Okay. Actually, in Japan, we've been working with NECH Japan, the NECH representative. NECH is a German company making TG system, and we are working with them. And they have recently developed a very nice TGA GCMS interface that, in theory, can be used to connect any GCMS to NECH TG system, but they work actually. The NECH Japan owns our quadrupole mass spec in their lab, so they've been using our mass spec for the development. So I think the NECH will announce this system worldwide in the near future. So please keep eye on their announcement, I think.
Okay, thank you, Tamura-san. Okay, now I pass to the Dr. Vinu for further comments on this session.
Thank you. I think this was a very informative session on analytical pyrolysis, starting with the opening note on the developments in analytical pyrolysis for microplastic analysis by Ichi-san, followed by, so we had 4 short presentations covering multiple aspects of analytical pyrolysis of a variety of materials, starting from lignocellulosic biomass, TPS materials, and also macroalgae or seaweed type biomass like Salicornia, and finally with Tamura-san on the advancements happening over in Geol. So on behalf of the organizers, I really thank the speakers, all the speakers of this session, Ichi-san, Adriana, Burada, Jinan, and Tamura-san for the interesting and informative talks. And I also thank all the participants for your questions, and finally thanks to you, Param, for nicely coordinating this.
Okay.
And thank you. Over to you, Param.
Thank you, Vinu. Thank you. I appreciate this, joining this session. Thank you. Okay, now we go to the next last session. It's on the panel discussion. Okay, and it's on the analytical pyrolysis challenges and future direction. And the moderator will be Professor Shogo-san. Okay, I think you already met him already. Okay, and also we have other panelists in this panel discussion, Professor Otani and Dr. Watanabe, and also Professor Lim. And there will be one new speaker, which you didn't meet him yet. It's Dr. Mia Wang. Let me introduce about him. Okay. Just a second, let me adjust my screen a little bit. Okay, Dr. Mia Wang, he received his PhD from Emory University, majored in biophysics. In his research career, Dr. Wang participated in many high-profile research projects in various national labs, including Stanford Linear Accelerator Lab and Jefferson National Lab, funded by the U.S. National Institutes of Health and U.S. Department of Energy. Dr. Wang was assigned as the general manager of the CDS Analytical in 2016, as well as the vice president of lab tech responsible for its North American operations. Before joining CDS Analytical, Dr. Wang was a senior product manager from SP Industries in charge of the technical marketing team as well as the product R&D team. Dr. Wang has many scientific publications as well as receiving various awards, including citations from the Commonwealth of Pennsylvania and the U.S. House of Representatives. Dr. Mia Wang, welcome to the PYRO Asia 2020, and welcome to the session. Now I will pass the baton to Professor Shogo-san. Okay. And all of you open your webcams, okay? And I'm going to stop the screen so that everybody see each other well.
Okay, thank you, Param. So can you hear me?
Yes.
Okay, so good evening, everyone. So again, I'm honored to moderate the first day panel discussion on analytical pyrolysis, the challenges and future directions. So in this panel discussion, so I'd like to ask a couple of questions to the panelists regarding the challenges and future directions in analytical pyrolysis. So dear audiences, so please send your questions to Param during the discussion, and later I will open the Q&A session from the audiences. Okay. So today we have two experts from academia and two experts from companies that produce pyrolyzer systems. So first of all, I'd like to start a discussion on recent trends and development of pyrolysis instruments for analytical pyrolysis. So in the first session, actually, we could learn advanced analytical pyrolysis systems such as PY-APGCMS from Professor Otani and tandem microreactor from Professor Kim, and original online catalyst screening reactor from Dr. Kumar, and UV irradiator combined PYGCMS systems from Dr. Tantri. So Dr. Wang, can you hear me?
Yes, I can hear you loud and clear.
Okay, great. So Dr. Wang, so I'm glad if you could provide any information or opinion about recent trends in pyrolyzer systems. And Dr. Wang, so this is your first opportunity to talk, so it might be great to include your introduction in your talk. And if you want, you can ask Param to share your screen for presentation.
Okay, sure. First of all, I really want to appreciate Dr. Kumagai to organize this panelist discussion. I think it will be very beneficial to push the frontiers of the analytical pyrolysis community. So from any measures, I think we did a great thing to get together and sit down and really discuss what has happened in the past year, even though there has been a strong headwind from the COVID-19. But I'm really glad to see that we're holding hands together as a community and really progressing along with the goal that we set, which is basically to make a better world. So having said that, so I think it's a very great question to ask from the perspective of instrument manufacturer. What are the most exciting things that are happening? So from our observation, one of the things that is exciting is related to COVID-19. So because COVID-19, there has been lots of traditional methods to test the COVID-19 patient who has been confirmed positive. Traditional methods including swab your throat or your nose, or really get blood work, test your antigens. But is there anything that our instrumentation can help to analyze the biomarkers? So there was a really interesting idea. So actually, we have some projects ongoing, trying to use the instrumentation to test certain biomarkers from the so-called biopsy of the breath. So if you breathe, we can collect actually your breath sample to a certain volume. It's about 300 ml. And then because of the flexibility of a CDS system, we were able to take actually regular size thermal desorption tube and use the feature of CDS instrument, which has a very high temperature ramp, to analyze the sample into our ion mobility screener. And from screener, we basically put it to a high resolution mass spec. So this is a very interesting project that I'm overseeing. So if I'm to summarize, so actually I'm been seeing that there has been a shift from analyzing polymers actually into the bio life science field.
Thank you very much. So yeah, it's very hot topic, current hot topic. So that sounds really interesting. But so do you mean that related to pyrolysis, analytical pyrolysis of COVID-19?
Technology-wise, it's actually not. It's in the low temperature range. It's more like, as Ichi-san said, it's like a TED. Thermal extraction, desorption technique.
Okay. So do you think the pyrolysis is available? It's helpful to detect some virus or some biomarkers? I'm really not sure, but if you have any ideas to apply pyrolysis in biochemistry field, it might be great to share your opinion.
Oh wow! It's because we are this event is a very unique event that we share ideas, share observations on what's happening in the real world and what we can do by holding together as a society, trying to help build a better world. So basically, I'm sharing some kind of really unique kind of projects, but still 99% of the application are still on the traditional pyrolysis, which is basically we are using the high temperature to lead to bond cleavage in the long-chain polymers, and basically we can add value to the existing GC mass spec systems. So there are tens of thousands of GC mass spec systems has been already set up globally, and also every year there are thousands of GC mass spec systems, new systems being installed. And I think the challenge is that how can we improve the application range of these GC mass spec systems and maximize its productivity. So Pi is really a very unique way to add value, because you have lots of samples cannot be dissolved in organic solvent. You have lots of samples cannot be directly injected into the GC mass spec injection port, as Ichi-san said. So we're facing lots of challenges. But by simply adding a Pi as a GC mass spec sample introduction method, we significantly expand the application range in terms of the molecular dynamic range to the GC mass spec. Traditional GC mass spec is only from 0 to 1200 Dalton. Now you can expand to infinite molecular size. That's a big benefit. So from that measure, we are really contribute to the whole research society and also the industrial society to push the frontier of the research and also QA, QC.
Okay, thank you very much for your talk. So can I also ask Dr. Watanabe to provide any information or your opinion about instrumentation or recent trends of instruments?
Yes. Well, everyone talks about the recent instrument, for example, the pyrolyzer hyphenated with the different types of detectors. So, for example, atmospheric pressure, ionization, or also not only the electronic EI ion source, but also photoionization that the geo started to sell, and also other GC by GC or those instruments. As a manufacturing company, I would like to show some slide sets. Can I share the slide set with audience? How can we share the slide?
Please wait just a second.
Thank you. Can you see?
Yeah.
Yes.
Okay. All right. So, this is our multifunctional pyrolysis system. But what I want to emphasize is that the recently industrial side, people want to know the degradation period or how the air degrade their polymer products. So some people want to do evolved gas analysis under air. Okay, when you do evolved gas analysis, the carrier gas has to be either helium or nitrogen. But we came up with the evolved gas analysis under air, which was presented in the International Pyrolysis Conference 2 years ago in Kyoto. Okay, let me explain about the evolved gas analysis, those who don't know about that much. So this is the pyrolysis GCMS system, so pyrolyzer GCMS system. And then between pyrolyzer and mass detector, it is connected by a EGA tube, which is a deactivated stainless steel tube about 2.5 meter. So in EGA, what you do is you slowly or you heat up the sample at programming temperature, for example, 20 degrees C per minute from 100 to 600. So the evolved gas goes to the mass detector. So actually, you do the real-time monitoring of evolved gas. So this is a typical EGA thermogram. So the x-axis is the temperature, furnace temperature, so 100 to 600. When you analyze the polymer sample, you will see first volatiles, additives, compounds at the lower temperature zone, and then higher temperature zone, you see the pyrolysates of polymer compounds. So now you want to see how the temperature affect or degrade the sample. So this is again the instrument, the picture of the pyrolyzer and then GCMS. So what we came up with is that we add here additional flow path line. This is helium, okay? So usually when we do analysis, carrier gas is helium, okay? But here we use the carrier gas, first carrier gas, the air, and then we degrade your polymer sample at the your temperature. And then evolved gas goes into the GC injector. But here we add helium, and then we dilute air, and then the evolved or degraded gases go into mass detector. So although some certain amount of air goes into mass detector, which may damage mass detector, but because of the dilution of the air using helium, you can do or you can simulate evolved gas analysis under air condition. So this is our latest development of not the instrument but the analytical techniques using our instrument. Okay, that's it.
Yeah, thank you very much, Dr. Watanabe. That's interesting idea to conduct its combustion analysis in pyrolyzer, right? So, okay, so thank you. So we have limited time. So I should ask many opinion from panelists. So I'd like to move on to the next topic from Professor Otani. So actually, I'm really impressed that the potential of microplastic analysis in the microorganism, so which might be related to Dr. Wan's idea. So actually, which cannot be achieved by traditional spectroscopic methods. So PYGC has great potential to analyze all polymeric materials. So I'm confident that the analytical pyrolysis is advancing on a very basis. So I'd like to ask Professor Otani to share your knowledge about recent advancement in analytical pyrolysis field. So you have already talked about microplastic analysis, so it might be great if you could talk about characterization of polymer microstructures by pyrolysis techniques. So since you are a pioneer of this field.
Okay, so today I talk about the case of the microplastic analysis, but the basic concept for the analytical pyrolysis is same for another topics. So always the three factors for equipment or techniques are important. One is the pyrolysis device and related technique, pyrolyzer, and the optional techniques such as ultraviolet radiation system. And the second one is analytical instruments for the pyrolysis or degradation products such as GCMS. And in this case, the separation and the detection is very important to improve the applicability. For example, in the case of DC separation, recently DC by DC technique is often used to improve the separation. And as for the detection, mass spec development is very important. For example, I talked today for APCI, Q-TOF-MS, such specific ionization and high resolution and higher sensitive spec is very important factor. And the third one is the development of the data processing system. So this is also presented by Dr. Watanabe today, for example, as the evaluation of the microplastic analysis. So one of the very early stage of the analytical pyrolysis research, these three factors are very important, I think.
Thank you very much. Thank you very much. So yes, the advancement of equipment and also the techniques of detection systems are very important, so he said. So thank you very much. So maybe Professor Kim, you are also the specialist in this field. So do you have any comments on this, the development of instruments and pyrolyzer systems?
Okay, I just only know the Korean application areas. So I think many industrial people is asking for the possible application for developed application. For example, the sample is changed on the air atmosphere dramatically. How we can introduce the sample to the pyrolyzer system. So I think one of the solution of that is to use the reactive pyrolysis. So we do the glass capsule. So for example, Samsung Electronic recently requested that kinds of application. And in the environmental areas, so the analysis of microplastics, the specific application is tire tread in the road dust. So the effect of the matrix, the dust sample has to be considered. And another thing is the textile analysis in the laundry wastewater. So if I see many kinds of microplastic samples, so I want to emphasize the careful approach for the sample preparation has to be developed prior than the main PYRO analysis. So because in case of drinking water, it's relatively easy to transfer the target microplastic to the sample cup. But in case of humic soil and various kind of biomass matrices, and even in my cases, the laundering surfactant, so all of these kinds of metrics can make the different quantification result. So I think everyone researching on the microplastics using PYRO, the matrix elimination is very important. And as Otani Sensei emphasized, the additional development of a high performance TOP system also can be applied. Okay, that's my opinion for microplastics.
Thank you very much for sharing your opinion and the potential applications of pyrolysis. So Param, do you receive any questions from the audience?
Yes, I have a few questions here for these panelists. Let me post. Okay, here we go.
Okay, so all panelists, recently PYGCMS is explored for not only detection of trace level compounds, contaminants, additives, but also going towards quantification. Okay, microplastics and also additives in advanced materials. How we try to meet such demand as a researcher or as system manufacturer? So the question for all panelists. So, okay, so maybe from Dr. Watanabe. So what's your thought about this question?
Okay, this is a good question, and then I think the most difficult challenges that we are facing right now. So in my presentation, also we are trying to quantify micro level or PPT, micro or below levels of microplastics. At this moment, as far as we are still trying, and I think everything's, for example, sample prep also very important, and then also measurements, and then also the database and processing software and detector. So I think if we see that all the factors are advanced well, and or we utilize those systems, and then we can achieve this goal, but at this moment, it is very difficult questions.
Okay, thank you very much. Yeah. So how about Dr. Wang? So can you provide any comments to this question?
Oh, sure. I agree with Dr. Watanabe. This is a very challenging question. It's a very good question. The audience who brought up this question must be expert has a high level overview and knows the cutting edge progress of the analytical pyrolysis field. So as a manufacturer, I can provide some really tiny insight. Again, my input is limited, may not be as influential as as your perspective. So there are a couple of things that CDS Analytical is doing. The first thing is a keyword, quantification. So we know quantification is very important because in the old days, if you look back 30, 40 years ago, when the pi was first introduced, was only qualitative, not quantitative. So quantification, one thing we're doing is that to improve the temperature accuracy. So traditionally, CDS was calibrating the temperature only 1-point calibration. So moving from the 6th generation PYRO probe, which is the 6000 series, we're doing 2-point calibration now, which we can calibrate over a wide range of temperature from ambient to all the way to 1300, and with astonishing temperature accuracy with plus minus 0.1 degrees C. And also, another thing we're doing to help quantification is focusing on high throughput, which means we have launched the 3rd generation autosampler, specifically designed to the 6000 series, which has a remarkable reliability. So in the in-house test, we found that this autosampler is so remarkable. When we run 5,000 samples, that's almost a 2-year amount of samples. There was no jamming happened. So we're improving accuracy of the system to assist quantification. On top of that, we are assisting society with a better autosampler, with a better high throughput. So by combining the two factors, I think we are going towards a goal, as Dr. Watanabe said. We're helping the society with a better product towards quantification.
Thank you very much. So Professor Otani, I guess you have experienced the quantification of monomer composition using PYGC. So if possible, would you provide your experience?
Oh, so I basically agree with Dr. Wang and Dr. Watanabe. And in the case of much smaller amount, less amounts of sample, it is harder to determine precisely or accurately. In that case, of course, the ability of the instrument is important, but also the ability of the operator or researcher is also very important. So we need to consider this point.
Thank you very much. So Dr. Kim, so you presented tandem microreactor research in the first session, and I think we didn't hear your quantification method in the presentation. So if you have any good ideas to quantify the catalytic pyrolysis products in your system, so please share your idea, please.
Okay, please allow me to share my computer screen.
Just a second, please.
Okay.
Yeah.
Okay, this is the, I show the slideshow. So normally I use this kind of the yield calculations. So many researchers sent the email to know how you did calculate the yield of gas and oil and solid. So in case of solid, you can measure the weight difference after the reactions. So in these cases, you need the exact mass balance in your lab. And in case of gas, the direct quantification of gas is more easier than the oil, especially in case of bio-oil, pyrolysis of biomass. It's very difficult to get the chemical standard of all of the pyrolysate. I think almost impossible. So in my cases, I first quantify the gas and measure the solid yield, and finally conclude the oil yield by differentiating some yield of gas and solid from the feeding materials. So typical example is one of my publications. So if you apply my approaches, you can calculate the overall gas yield and solid residue. So cocoa also has to be considered as the solid residues, even in the catalytic pyrolysis, and the yield of target components. So for example, in my case, BTEX and other aromatics can be the target, and it can be make the calibration curve and quantified. So, and one of the other frequent question is for the reaction gas. For example, many researchers who want to compete the waste plastics as a hydrogen donor, and recently many people use the different reaction gas. So, and also some people want to use methane gas as the hydrogen donor on the catalytic pyrolysis of biomasses. So in that case, if we use the tandem microreactors, we can introduce the methane gas via the reaction gas selectors. So in my case, I switch it from helium to methane, and the specific amount of methane gas can be continuously provided between first and second furnace of tandem microreactor. And so also the methane can be supplied together with the pyrolysate of biomasses. So additional synergistic effect can be observed. So other kinds of reaction gas also can be added. So my challenge is the use of water and steam in the micro scale analysis. So I think Otani sensei can give an advice to me, maybe. So that's all that I think related with the catalytic pyrolysis work.
Okay, thank you very much. So I got another question about repeatability of the analysis. So Professor Kim, you showed your quantification results, and it looks good repeatability. So do you have any comments on this?
Yes. So actually, in my experience, the analytical instrument is very nice. However, most of the quantification error is made by the people who yes. So because in our laboratory, the repeatability depending on the student is quite different. So the exact weight and the repeated weight measuring of initial mass is very important. And also, if you want to the improved repeatability, I recommend to use the FID instead of GCMS. So sometimes you have to perform the long period experiment. So the mass stability can be changes. So direct comparison is very difficult. So, but if you use the GC-FID system together with the tandem microreactors, the long time stability is much higher than the mass. So it's my second recommendation.
Okay, thank you very much for sharing your very useful knowledge. So I'd like to move on to the next question for Otani Sensei. So what is the future of high resolution MS coupled to PYGC? Related to this, would you prefer to have a better chromatographic resolution like GC by GC combined with PYGC MS, or would be high resolution mass more important?
Okay. As for the first question, the high resolution MS is the promising technique even for the analytical pyrolysis field. So by using this one, you can get more selective information and more mature useful identification process. So it is very important. And as for the chromatographic resolution, unfortunately, I have not used the DC by DC equipment, but I feel this technique is also very useful as well as the high resolution mass MS technique. So both techniques are very important in the future analytical pyrolysis method. Okay.
Thank you, Professor Otani. And the next question. So it's I like this question actually. So analytical pyrolysis use very small quantity of sample to study the product profile, conversion or selectivity. So how true will this study remain when we shift to higher quantity of sample, for example, pilot scale? So maybe Professor Kim often receives this question. So I believe that the analytical scale PYGC-MS is a promising way to understand pyrolysis mechanism and screen the best catalyst for reaction. So what's your thought on this question?
So, okay, I think in a year, more than 10 times I asked why the repli. So if I apply to the government project, many people are asking about this point, but I always say I think the micro scale PYGC system, it can be the accelerating experimental tool for the researchers. For example, if we construct the pilot plant, the long time is required for one experiment. So in that case, you can select the best choice. So which is the best catalyst and which is the optimized temperature for these reactions. So fast and more exact experimental result may be required. So in our case, we can screen more than 50 catalysts in a week. Then suggest maybe these 3 catalysts will be the best candidate for your pilot plant or actual commercialization plant. And they make the actual experiment and succeeded the final constructions. So I think the direct comparison with pilot plant and micro scale plant is quite difficult. And each system has an advantage for the analytical societies. That's all my answers.
Thank you very much. So how about Dr. Wang? Do you have any experiences to fill in the gap between pilot scale and micro scale pyrolyzer?
Yes, Dr. Kumagai, again, this is a very, very good question. I agree. The challenge that we are all facing is related to homogeneity of the sample. For example, for the IEC method, when people are testing sites, we are forcing them to load a minimum amount of sample, the 100 of milligrams, micrograms, I'm sorry. So this brought a huge inconvenience to the testing staff. So how can we overcome this? So CDS, as a pioneer in the scientific instrumentation, we have a really remarkable group of R&D staff. And many of them were basically trained by US military. So we have one engineer from actually was trained by Navy. So they're bringing lots of different perspectives. We're going that we have a very healthy combination of not only the scientists, but also engineers, has a tremendous background in various projects, who are trained to resolve all these challenging questions. So that's why we launched the drop-in sample chamber system, the DIC system, about 2 years ago, which was a tremendous success for CDS Analytical. As where I'm going is, yes, we do have a roadmap in the next couple of years, trying to significantly increase the sample amount by continuous evolution on the DISC systems.
Mm-hmm.
So we have some good information for everyone in the next, I would say, probably a couple of years.
Mm-hmm. Thank you very much. So we have limited time, so we have 2 more questions. But the first question, Professor Otani, so can you answer to this question, the calibrations of a PYGCMS FID?
For this question, it depends on the compound. So in the case of highly volatile compounds, in the mixing or the setting processes, some components are vaporized and lost. So in that case, it is not useful for the calibration by using this technique. But in the case of less volatile product, it is okay, I think.
Mm-hmm. Mm-hmm. Thank you very much. So maybe this is the last question. So in a tandem microreactor operating high pressure flow controller, would it be okay to analyze what is NCG? NCG is by taking a sample from the back pressure to outlet and analyzing the micro GC. So Dr. Watanabe or Professor Kim, can you answer to this question? So I didn't catch the complete meaning of this question, but if you understand, please.
Excuse me, Professor Shogoku Magai. This is Adriana Estrada, and this is my question. So I was wondering if we could analyze NCG is for the non-condensable gases that we cannot see in the PyGCMS or PyGCMS FID. And so we had, I was thinking maybe I could take a sample from the outlets in the high pressure flow controller and then try it in a micro gas chromatograph. That would be a part, so not part of the system. I just had this idea and was wondering if it would be okay to analyze the non-condensable gases in this way.
Okay, thank you very much. Yes, I understand. Thank you. So which one, Professor Kim or Dr. Watanabe? Maybe Dr. Kim? Can you?
Okay. I guess it's possible because if you connect the vent line of BP2 to the micro dish or micro dish, maybe difficult. So I think I recommend to use the conventional GC. So in that case, you can put the capillary column to the liquid nitrogen. So like a microjet quadrat. So also another way is to check the non-condensable gas. So except hydrogen and methane. So you can put the main separation column of high pressure tandem micro tissue mass. You can see the separation of very light components, such as in my case, the carbon dioxide and ethylene and ethane and propylene. So such kind of very light components also can be focused and separated, even you use the high pressure systems.
Okay. Okay, thank you very much. So so time is up. So thank you for the active discussion. And okay, so this is panel discussion. So before closing the panel discussion, so I'd like to ask each panelist to briefly talk about the any comments about future perspective or expectation in the analytical pyrolysis field. And then I'd like to close this session. So, okay, so from Dr. Wang, can I ask you to make brief comments?
Oh, okay. Again, thank you for giving me the opportunity to be the first speaker to close this remarkable section. And I appreciate all the panelists' contribution, as well as I'm really delighted to see all this cutting-edge progress that everyone is making in their own research field. As I said, as a whole society, any work, no matter if it's a small step or big step, is going to add up and eventually contribute to the whole human society, whole human being. So anything we're doing here is good. So having said that, for my closing mark is basically as an instrument manufacturer, we are excited to share all these new ideas, and will be more than delighted to be contacted by any research group, saying that, well, I have this new idea. Can you assist me to accomplish this? So CDS is a mid-sized company. We are very dynamic. As I said, we have a healthy combination of application scientists as well as distinguished engineers. So we are aimed to help you guys to resolve any technical issues so that you can focus on own research. So that's basically my small remark. Okay. So
thank you.
That's all.
Thank you very much. So Dr. Watanabe from Frontier Laboratory, please.
Okay, thank you very much for selecting me as one of the panelists. I really enjoyed especially the question from the audience, and some of them, the questions are very nice. And as a instrument manufacturer, well, what we can do to support your research is that, well, we can train you how to use our system, utilize our system. That's all we can do. And then with that, you will advance your research area. So if you have any questions, it's tiny questions, fine. So like why we cannot get good reproducibility, we can answer all the time, anytime. So if it's tiny question, please let us know. We can always help. And then also through our business partners all over the world, as well as the researchers, collaborating researchers. Thank you very much.
Thank you very much, Dr. Watanabe. Professor Kim, so please.
Okay, thank you so much. First, I highly appreciate it for the invitation as a panelist. So actually, when I worked as your service engineer in domestic PYROASIA company, most of applications is focused on just the quantification, purification of polymer. So one or two kinds of polymer identification is enough for the use of PYROASIA. However, now the related market is dramatically expanded. So some kinds of regulations such as IEC method for the phthalate analysis and various kinds of another application, photo-oxidative catalytic pyrolysis and the reactive pyrolysis. So this indicated the role of PYROASIA expert is very important in nowadays. So as Otani Sensei already indicated, I want to recommend more effective training program is highly required in this time. So yeah, that's all my inquiry for this conference. Thank you so much.
Thank you very much, Professor Kim. So, Professor Otani, please provide your comments.
Okay, thank you very much. So first of all, I am glad that I can feel the pyrolysis research field is still very active, like this today's discussion. So in the analytical pyrolysis field, the sample amounts are very small, the micro scale. On the other hand, the applied pyrolysis uses a much more sample size. But both fields are still pyrolysis. So it is much more important to connect more tightly both fields in the near future, Thank you very much.
Thank you very much for your important comments. Okay, so thank you very much for all panelists. I express my big thanks to the all panelists and also audiences to join this session. So, so we all through this session, so we could share the significant potential of this field. And yes, I hope this Pyro Asia community contributes the progress of this field. Okay, so time is up. So thank you very much for your active participation. Thank you very much.
Okay.
Thank you, guys. See you.
Okay. Thank you, Professor Shogo-san. Guys, officially, this is end of day one. Okay, thank you all. Thank you all the speakers, audience, and all organizers and committee members to make this first day is very interesting. I'm sure that you guys find it, you learn a lot of things. I'm sure maybe your head is heavy with all the information on the pyrolysis now. So we'll start tomorrow at the same time at 1 p.m. Singapore time. Okay, please see you then. Have a good night and good evening. Bye-bye for now.
Bye.